Hi, and welcome to Kubernetes Fundamentals and Cluster Operations. My name's Mark Allenbaugh, and I'll be your instructor through this course. Let's go ahead and dig right in. So the first thing we want to talk a little bit about is who do we think is the right person that this class is targeted for? And regardless of what Kubernetes runtime platform you choose to use ultimately to run your Kubernetes containerized workloads, everybody is going to need to have a core Kubernetes basic foundational knowledge to be able to successfully implement, maintain, patch, and update their ultimate Kubernetes runtime environment. So hopefully you'll choose a Tanzu, one of the products out of our Tanzu portfolio, which we'll briefly talk about. But this course is not going to be teaching a specific VMware Tanzu product. This course is designed to teach you the fundamentals of Kubernetes, which will apply regardless of which Kubernetes platform you end up ultimately deploying or supporting or migrating off of or managing. So if you could imagine a scale from a 1 all the way over here to a 10, and we said a 1 is somebody who is a complete beginner, okay, on Kubernetes. They've seen a few things about it, but they really don't have much depth at all as to what's going on. Versus all the way up here at a 10 would be somebody that maybe has a certified Kubernetes administrator certification, and maybe they've got years worth of experience running a Kubernetes or dealing with Kubernetes. In the middle here, if we said this is our 5 point, what this course is designed to do, just so we can set a little bit of the framework or the expectations, we're thinking the majority of people taking this class are somewhere down here. Probably between a 1 and a 3 when it comes to their Kubernetes knowledge. And the goal of this course is to take these people with what we're going to cover in this course and drop them somewhere up in here between a 5 and a 6. So it's going to definitely push you over the intermediate into the solid intermediate category when it comes to Kubernetes. We also think most people taking this course have some vSphere experience. I will be making some analogies back and forth to how something works in vSphere, and then I'll kind of correlate that over to how it behaves inside Kubernetes. So if you don't have the vSphere experience, that's okay. So let's go ahead and get started. It is important for you or anybody that's going to be doing anything with Kubernetes, regardless of which Kubernetes platform they choose. If they choose vSphere with Tanzu, if they choose Tanzu Kubernetes Grid or Tanzu Kubernetes Grid Integrated, or one of our competing products, one of our competitors, OpenShift, Mesosphere, any one of the other ones, Rancher, if they choose one of those solutions, regardless, you're going to need a core knowledge of Kubernetes. And those solutions that we talked about are basically an enterprise Kubernetes solution. And in order to successfully maintain those, install them, deploy them, manage them, you're going to need to know how Kubernetes works. And that's what this course is about. It's going to be about vanilla Kubernetes. We're not going to talk about a specific product. We're going to talk about open source Kubernetes and how Kubernetes, if you installed it yourself manually or the hard way, how it would behave. And by the way, Kubernetes is the same Kubernetes regardless of which runtime platform you're using. Okay, if you use one of our Tanzu brands, again, we're taking open source Kubernetes, packaging it, and providing it for you so it is Kubernetes. Same's true with the other vendors' choices as well. So the goal of this course is to help you develop your knowledge and skills so you can build that highly scalable Kubernetes clusters. And in most cases, when people are running Kubernetes, it might not just be in their own environment, they might be actually running it on a cloud environment. And again, Kubernetes consistently behaves regardless of where you're running at. There'll be a few subtleties that we will talk about. So here's our objectives. Kubernetes is about running containerized images. So we're going to start with giving you some core basic experience and knowledge about a container image build tool called Docker. You're actually going to go through and build an image and actually push that image up to some container registry. It's important that you understand how that behaves, what it does, even though you're not probably a developer. If you are, we're going to go over it at a very surface level. You're going to probably need some additional training on Docker. But for most of us that are just running Kubernetes environments, we're a site reliability or a Kubernetes operator, we're not typically building container images. But we want you to see how that works and how that behaves. We're then going to jump in and take a look at our kubectl tool, our CLI tool. That's the primary tool you're going to be using, that command line tool, to interact with Kubernetes. So you'll use that tool to create, inspect, update, and delete various Kubernetes objects. Speaking of Kubernetes objects, we're going to go over what the basic objects are and their corresponding services, how they are going to end up getting defined in a YAML file. Now, in this course, we're not going to create any YAML files. We're going to look at them, we're going to use them, but we're typically not going to be editing a YAML file. That, in the majority of times, is done by the developer, and it's pushed down the pipeline to us as somebody who's going to ultimately end up deploying the application on our Kubernetes environment. We're going to talk about how DNS is used inside Kubernetes to locate services. We're going to explore that both within a namespace and across a namespace so you can see how it behaves. We're going to talk about the difference between stateless and stateful applications. We're going to take the application that we are using through our class, which when we start off will be stateless, and then we're going to actually go ahead and turn it into a stateful application so you can see how that actually works. We're going to talk about these things called resource quotas and probes that you would typically want to use inside your Kubernetes environments. We're going to talk about some security features inside Kubernetes, security context and a network policy. Those are going to be important to understand. We certainly want to secure this new robust environment. How would we implement that? We're going to talk about various monitoring and logging solutions. And then we're going to wrap it up doing some troubleshooting and some details that you're going to need to know when it comes to performing maintenance on your Kubernetes cluster. So this is the flow of the class. There's 10 total modules, and we're going to end up going through them, and they're broken down into various different lessons. Some modules only have one lesson, some have 5 lessons. So we'll go through each one of those. The flow of the class is going to be, we're going to shoot for somewhere around, I'm going to say the 12 minute mark before we take a break. I am going to strongly encourage you when we get to a break, try to stand up at least every other one that we go through. Stretch your legs, get some coffee, get a drink of water, and just take a break for a few minutes away from the computer. It will be easier to digest the information. So, Kubernetes. As I said to you, this is an open source project. And what is it about? It's about a cluster management tool or orchestration tool that's going to help me deploy, manage, and scale my containerized workloads. That's what the tool's about. It's not a product from a vendor. It's an open source project that's being managed by the Cloud Native Computing Foundation. So this is a group of like-minded people that are all into Kubernetes. They have come together from everywhere across the globe. The whole project's broken down into smaller aspects. They're called special interest groups. You can join one of the SIGs and help contribute to Kubernetes. They do everything from validating that a reported problem is a problem in a release. Sometimes there's people actually going in and fixing the code. Okay, so it's not one vendor deciding what's going to be the next thing for Kubernetes. It's the CNCF across these group of special interest groups that are collaborating together, deciding what's going to be happening in Kubernetes. What's going to be it? What are they going to try to include in a version down the road? When they're going to pull something out of a version? Which direction they're going in? It is a very well-supported project in the community. There's a lot of people inside of it. It's got a lot of movement. Originally, Kubernetes started from some former Borg engineers. These are Google-related developers and engineers that were working for Google in the decades before, as they were building out that whole Google infrastructure of all the things that you could think Google's, was doing. They were probably the first ones to talk about doing cloud computing. They took the best of what worked for over a decade from everything they learned from Borg in production, which was the code name that they were using inside Google for how they were managing their physical servers all the way up to running applications. They figured out what didn't work, threw that away, and came up with a better solution. And that's how we started with Kubernetes. The first release of Kubernetes that was released was not quite 10 years ago, around the 2013-14 mark. Okay, so it's a relatively new product, although it's pretty much so been the most popularly implemented solution for running containerized workloads. We're still, regardless of what we're doing, ultimately down here at the bottom is a physical server. Okay, this physical server is giving me CPU, it's giving me RAM, and then depending on how I install it, there can be various layers above that until I finally get my containerized workloads running. When Kubernetes is being deployed and installed, it could be set up to run on bare metal, right down here. We maybe have a hypervisor layer in between. We could even maybe have some cloud provider implementation separating us from a respective hypervisor that they're using. Now notice, I'm not saying vSphere. I'm just saying a hypervisor. So we've been going at this already for about 12 minutes or so. Why don't we go ahead and take a break here? And when we come back, I'm going to go ahead and briefly introduce a few of the VMware solutions, and then we'll get started with our next module after that. Thanks. Hi, and welcome back to Kubernetes Fundamentals and Cluster Operations. Let's go ahead and pick up where we left off at. vSphere with Tanzu. This is one of the VMware solutions that allow us to run Kubernetes and in turn our containerized workloads on top of it. Now, this particular solution from VMware only is able to run on a platform of vSphere 7. So for some customers, this could immediately be a, nope, we're still on 6.7. We're going to be there a while longer. This product is immediately ruled out right away. If you are on vSphere 7, it is very tightly integrated with vSphere 7. And one of the beauties about it is you can actually use the vSphere client to do some interactions with Kubernetes, which for a lot of people, I'm going to tell you, this is probably the easiest button to be able to get Kubernetes up and going if you're running vSphere 7. Now, another thing about this particular product is this particular product is sometimes what people refer to as a 2-for-1. You buy vSphere with Tanzu, and you also get another product called TKG, Tanzu Kubernetes Grid. So it's a great product to start off with if you have vSphere 7. Now we're going to talk more about these products at the end of the class and try to summarize certain features that we've just talked about over the last period of days of this course and how those particular solutions are being implemented in the various products. So for now, this is as far as we're going to go. Know that vSphere with Tanzu, vSphere 7 only, and it's by far the easiest way to get Kubernetes up and running. The next solution that we offer is Tanzu Kubernetes Grid. In Tanzu Kubernetes Grid, just like vSphere with Tanzu, does provide for us an upstream compatible implementation of Kubernetes. So what are we actually doing is we're taking Kubernetes from the open source community, we're downloading it, we're validating it, we're signing it, and we're repackaging it inside of our offering, and we're supporting it. So what you're getting is support from VMware on your Kubernetes implementation. Now, one of the nice things about when you're looking at TKG is, and again, TKG is the acronym you're going to hear people referring to it as, is TKG could not only run on vSphere, including version 6.7 plus, but it can also run on AWS. It can also run on Azure. And just like vSphere with Tanzu, it does do lifecycle management of our Kubernetes clusters. So that's how I do deploying of a cluster, upgrading a cluster, patching a cluster, scaling a cluster. Both products do that, both vSphere with Tanzu and TKG. The big difference between TKG is TKG can run on a very wide selection of that bottom layer that I spoke about. What's down here, we're going to call this our IaaS, our infrastructure as a service. This down here can be any one of these three platforms. And then on top of it, I start making my Kubernetes clusters. TKG is going to include some popular additions to Kubernetes that Kubernetes open source out of the box does not include. They provide a mechanism for you to either plug certain things in or you simply just add whatever additional features you would need to your cluster to it. Like what? Well, do you want some way to authenticate people into your Kubernetes cluster? Probably, yeah. I would call that a mandatory. Okay. Kubernetes off the shelf does not include that. TKG includes additional open source applications that would provide this additional functionality, in this case of authentication. Do you want to log stuff? Do you want a universal logging solution? Yeah, I want all my logs gathered in one spot. TKG includes what we call extensions to be able to do that. When you're looking at other vendor solutions, including some of the ones from VMware and even our competing products that are offering Kubernetes solutions, several of them have made an opinion of what they think is the best, and their solutions simply including, this is what we use for logging, this is what we're using for networking, this is what we're using for monitoring, and you don't get a choice. TKG, you do get the choice. You can choose a variety of different solutions, and if you don't like the ones we're providing, you could certainly plug in a different one, but then it comes a question of, are we going to support you on that additional solution? Our third and final way that we have for you to run Kubernetes is TKGI. This is the old product that used to be called PKS. Okay, PKS Enterprise is what it was called. It's been renamed now to TKGI, Tanzu Kubernetes Grid Integrated. This is the product that's been around the longest. So this is a 5+ year solution. It's got a lot of history to it. At the time, a technology that our other two solutions use and implement called Cluster API, which we're going to talk about in Module 3. We're going to talk about what is Cluster API. At the time that we came out with TKGI, Cluster API was still on the whiteboard, let's put it that way, okay? It was still on the whiteboard. It wasn't baked enough to actually implement it. So they couldn't use Cluster API to help build and manage Kubernetes clusters. So this solution actually ended up using a technology called BOSH, okay? BOSH is, again, one of the evolutions of things from the Borg engineers. If you take Borg and you +1 down here to the last two in the alphabet, R becomes an S, G becomes H, the invention of BOSH. Okay, it also came from the Borg engineers. And that with using BOSH is how TKGI actually spins up and manages and does lifecycle management of your Kubernetes clusters. He can also do it across a wide variety of IaaS platforms. Again, lifecycle management is done using BOSH versus the other two were using Cluster API. And as of now, as of this point in time, if you need Windows worker nodes, TKGI is the only platform that we have that supports doing Windows worker nodes. We'll talk more about what the worker nodes are when we get to our Kubernetes architecture. So, got a few typographical conventions, nothing really worthy of talking about other than if you see something with a less than and a greater than sign around it, you don't type it. It's a variable placeholder. Okay, so just study the directions a little bit more and you'll see that you probably captured information earlier, and that is going to be a substitution that you're going to make. If you're trying to get, let's say, the word from the horse's mouth, where do you want to go look at to find the definitive truth? And that's going to be on Kubernetes.io. Now, if you're considering taking your Kubernetes certification, which is a hands-on exam, it's not a multiple choice, it's not a multiple guess, you're actually giving working and sometimes broken and sometimes to be built Kubernetes clusters, and then you get a mission to say, fix this, break that, change this, build this. You actually have to go hands-on keyboard and do stuff to a Kubernetes clusters, okay, to get things working, and that's how you'll be graded. During that exam, hint, hint, during that exam, you are able to access the Kubernetes.io docs. So almost anybody help coaching you to get your CKA certification is going to tell you you gotta get familiar with the Kubernetes.io docs, because let's face it, you can't memorize everything you need to know. So you want to be able to get comfortable on navigating that and finding stuff quickly. Now, Tanzu is a brand. And as you've seen me talk about various products from Tanzu, if you go to the tanzu.vmware.com, you could see the various different solutions we have. We are going to review a bunch of them at the end of the class in our very, very last module, okay? But we've got ways to help people build containerized workloads. We've got different ways you can run containerized workloads, and we've got different tools in the Tanzu portfolio to help you manage your Kubernetes environments. So we got 3 different major buckets, and we've got different editions of Tanzu offerings that offer different products to help you achieve those respective goals. So that's where you could find that information out. Most of you are already familiar with things like the communities, hopefully. Your lab environment will be good for 30 days once you start it, I believe, in this class. If you want to play around with other solutions, not what's in our class, maybe you say, you know, hey, this TKG looks interesting. I want to go take a peek at it and play with it. take a look at the hol.vmware.com. Hands-on labs give you a short little hour-and-a-half teaser on some of the products that we've spoken about. Different ways to learn. Okay, different ways to learn. You are right now in an on-demand class, which is actually, this particular class is paired with a Lab Connect. So the Lab Connect is where you're going to end up doing your labs. A friend of mine, Joe Cooper, is going to give you an overview of how to connect with Lab Connect when that time comes. Our labs will be done in Lab Connect. Big thing for you to remember, once you start your labs, you've got 30 days to finish them. Okay, the on-demand course will be around. You can revisit it, replay it, go back and do whatever you need to, pause it. You know, hey, I got a pressing project. I got to shelf this for 2 weeks. You can do that type of stuff for the on-demand courses and the recordings. But once you start the labs, they're going to be valid for 30 days, and then they will expire. So please budget your time accordingly. We've got different certifications that come along with the different pillars that we're offering. The pillar that we're inside this particular offering is going to be falling underneath application modernization. So some of you've got probably a decade plus of experience in vSphere. So I would imagine there's some of you that probably have one of those 3 certifications, and your certification's probably down here in data center virtualization. That would be vSphere and our ESX hosts. Maybe some of you've got it over here in network virtualization, which would be our NSX, V&T offerings. This, for application modernization in the Tanzu portfolio, is going to be over here in app modernization. So again, you could pick up another certification over there once you've mastered some of the necessary skills that you would need to pass the exam. If you do get your certification, remember we offer you a way to be able to advertise that certification on things like your LinkedIn and Facebook page. This is via the Acclaim platform. So once you've achieved the certification, when you go to add it there, there'll be a particular URL that you can copy out of your VMware profile, and it actually validates that you currently do have the certification, the details. It's not just a simple icon graphic somebody's copying and pasting. So with that, that concludes this particular module. So go ahead, take a break, stretch your feet, and when you come back, we'll dig into our next section where we're going to talk about containers. See you soon. Hi, and welcome back to Kubernetes Fundamentals and Cluster Operations. My name's Mark Allenbaugh, and we're going to go ahead and get started with our next module, which is Module 2, and we're going to be talking about Containers Overview. So, in order for you to understand what Kubernetes is doing to your containers, it would help you to have a core or a basic understanding of how do containers work and recognize their benefits. And then we're also going to explore inside here some basic Docker commands that, even though you might not be the developer creating the application, having a core understanding of what basic Docker commands are will certainly help you when it comes to administrating your Kubernetes platform. So again, we're going to look at the benefits. We're going to talk about the relationship between containers and microservices and explain to you a little bit how the various container components interact with each other. So this short module of doing an overview of containers will kind of help fill in the blanks when we get later into actually running our containers underneath Kubernetes. So when we look at where you're at today, if we said you're sitting over here with some older monolithic, if I could spell, monolithic application, and what we're trying to get to is over here to a new containerized microservices-based application, it's going to be a journey to get you from here to there. And realize these cloud native principles are a goal. You might end up stopping, in various sections. You say, okay, here's my phase 1, here's my phase 2, here's my phase 3. The goal is to eventually get to these cloud native principles. You might not get there on your first iteration. Okay, so just the idea is understand what we're trying to shoot through. So the goals are any unit of work that you're deploying should not have any OS dependency requirements underneath it. Okay, a common area where this comes into place is when people are porting their applications from .NET style applications, trying to go to containerized microservices. Some of that .NET code is very dependent on something inside, for example, a Windows OS. Your workload should be actively scheduled and managed by an orchestration process. This is going to be our Kubernetes. And by the way, I just used the abbreviation for Kubernetes, K8S. You'll hear people sometimes refer to it by pronouncing the acronym. They'll say KATES, okay? But again, our goal is to teach you Kubernetes. Your containers should be something that are actively scheduled and managed by that orchestration process. I think you could see it would be beneficial to have a basic understanding of how containers actually get created and the tools and the command lines you would use to do that. Your containerized workloads should be loosely coupled from any dependencies. Imagine a multi-tier application. Yes, for it to work, it needs from the web tier to call the app tier to call the DB tier, but they're loosely coupled from each other. It shouldn't prevent one from running or not running. They should be using microservices. So instead of your code doing, let's say, your monolithic application today doing 50 different functions, when we go to using microservices, each container does one function that would be more pushing you more towards refactoring your application to do microservices. The benefits that we get when we look at our containers, these 6 benefits, the biggest one that you're going to hear people zero in on is velocity. How many updates can we do and how often? You might be today doing a monolithic update to your application once a quarter. As you start containerizing and refactoring your application over to be using containers, the velocity might pick up. There might be certain sections of your code that you might say, listen, we can do a daily update if you have one. Your containers are going to go from, we've got portability today with our virtual machines, but when we go forward with fully containerizing our entire application stack, I'm going to say that we get ultra portability. Today, our virtual machines are dependent on us running on a particular hypervisor where we created our VM app. Containers, doesn't matter where they're running at, they're super ultra portable. As you shoot towards the cloud native principles of doing microservices, you're going to actually increase the reliability and efficiency of that one microservice. For me to test one function is much easier than me to test 50 functions of a monolithic application. So your reliability of your containers start going up as well as their efficiency. Your developers can do a lot more self-servicing, not so much depending on us to do some things. Our isolation goes up. I know if you're doing one function, I know what kind of TCP traffic should be coming in and out of you. So the isolation that we get in our containers would also give us a better security control because I know exactly what that one microservice is doing. Here's the example I was trying to show you inside here. So this is where I'm at today with an older monolithic application that I've developed. Inside of this one VM, I've got clear, distinct functions inside my code. I've got code that does API service, the web UI, business logic, data layer service. All of that is happening inside my code. When I start switching this over to my microservices containerized workloads, you'll notice a few things start to happen. One, if I see that my web UI maybe is slowing down, it would be nothing for me when I go to microservices. Oh, look, I've got 3 of them now, not 1. Which also means I have a higher degree of reliability because now I can my degree of high availability just increased, because if all 3 of these, let's say for one reason, for some, were sitting on one ESX host, this ESX host failed, it wipes out all of these services. You'll notice I still got additional web UI, business logic, and data layer services that can go ahead and continue to keep my application up. So these are some of the benefits that you're seeing. These are some of the benefits and how they're going to end up getting implemented when we start looking at taking this workload that we've containerized and deploying it underneath Kubernetes. We're going to explore all of these in more details over the duration of this course. So we're going to talk about, well, how do I put a load balancer in front to be able to distribute my work? How does this microservice reach this microservice? So we're going to talk about services and service discovery. Again, that's everything we're going to be covering through the duration of this course, all the basics of Kubernetes. So looking at what does a current application, let's say this monolithic application, what does it look like at runtime? Well, it's going to have a guest OS. So somebody comes to me and says, hey, we've got a new timesheet application. We want it deployed in our environment. I say, great, send me the details on it. I take a look at the specification sheet. They tell me which operating systems it would do. So what I would do is I would spin up a new VM with the appropriate guest OS to support that application. Further down on the configuration and installation sheet, it tells me, oh, you need to get these various middleware application dependencies. So maybe I need a specific version of .NET. Maybe I need a specific, JVM or PHP or Perl. I need to download some middleware and install it on my application. Notice it's all manual. That's another thing we want to talk about is reproducibility. Me installing those application dependencies isn't being done by a script. I'm actually manually downloading it and installing it and running it. And then ultimately, I would install the application on top of these application dependencies. What it needs is on top of this OS. My VM, my application, is now all of these components and that's what's required to run my application. So the VM is encapsulating all of these components. Those components are going to include things like device drivers, daemons, libraries, middleware, etc. Yes, it's portable. I can pick that VM up and I can move it anywhere provided my hypervisor stays the same. Versus when I look at containers. Containers start on top of whatever the guest OS is, my container image. It's going to be the application dependencies in the application on top of it. And in this particular case, I would actually have inside here 2 different containers running on this one guest OS. They are ultra portable in the fact that as long as there's a compatible guest OS for me, I could run this particular container image on it. Now, how do we create the containers? You're going to need a container engine to be able to do that. The most common container engine you're going to hear is Docker. Okay, Docker has a very large percentage of market share. We're going to take you through the basics of Docker. And again, our focus is not on all the details of, don't get hung up on, the details of how the image is actually constructed, etc. Our focus is really more just giving you the basics so we can focus on the Kubernetes running these respective images. So when you're looking at this guest OS that is the host OS that's running my containerized workloads, this is going to be simply an operating system which can run containers. Okay. Now, how do I make this? Do I put it in as a VM? That's going to give me the most amount of flexibility if my container hosts are virtual machines. I could make them bare metal. Okay, so I could put that directly on physical CPU. So my container host, it can be a standard OS with a container engine installed. The most common one you're going to see is Ubuntu with Docker. That's what we're going to do in our labs. Some of these OSs can be specialized OSs, things like Photon, specifically developed with containers in mind. Beauty of that is it decreases your attack footprint because it doesn't have all the excess luggage potentially of a standard OS. Where do you install it at? Well, our preference and what we're going to do inside class is going to be inside of a virtual machine. You could install it bare metal, but you're going to find that's the minority of your workload, okay? 95% of the containerized workloads are running on top of some type of virtual machine with the appropriate container host OS inside of it. So you can see VMs have all the benefits that we've come accustomed to for management and scalability. So we've been going at this for a while. Why don't we take a break here? And when we come back, we're going to go ahead and jump into what would be the typical workflow a developer would do to actually create a container image for us to use. So go ahead, stand up from your desk, take a break for a few minutes, and I'll see you back shortly. Thanks. Hi, and welcome back. Let's go ahead and pick up where we left off at. Before our break, we ended with introducing what would be the typical container workflow that a developer, for example, would go through, or really anyone that was trying to create a container image. So an important piece for you to understand as you're administering your Kubernetes platform is where's the intersection point between what the developers are producing and how do they end up ultimately giving that to us, and then in turn, what do they have to go through to do their testing? And then where do we pick up at and start taking that code and start running it inside of our infrastructure? So let's start with the beginning. Somebody needs to create a program. So what would typically happen inside here, as you can see in this slide, is they're going to start over here on the left-hand side with creating using their appropriate language that they want to, the source code they need to create their application. A lot of times creating an application, they're going to include some type of dependencies, libraries, packages, middleware, etc., that is required to help their application run. They're then going to use a text file. This is how containers get built. This text file, which is case sensitive, default name, Docker file. In the Docker file, they're going to describe what the dependencies are and where their source code is. Using a container runtime engine, they will actually go ahead and do in this case, a Docker build statement, which would actually build the image that represents their source code with its dependencies into this image. That image then would typically be pushed into some type of image registry. Now, this image registry right here is part of that line where we're sharing, that's a boundary part or a demarcation point where the developers, after they're done developing stuff and they're ready to do it, they would typically push that into some type of corporate container image registry, which then they would say, hey, I'm done with mine, here you go. Let's go ahead and start getting this tested and deployed inside of our Kubernetes platform. However, the developer was going to probably need to test it themselves. Now, if they have a container engine, right, some type of container engine Docker, for example, installed on their desktop, they could actually, using Docker, actually go ahead and run their container so they could actually do their standalone testing right on their laptop. We're going to go through these steps in our first lab here so that you can actually experience what is it like. Now, you're not going to actually do any programming, so don't get too worried about, well, I'm going to have to write some code. We're going to give you everything that's needed. We're going to give you an example Docker file to use, but you will actually use the Docker build command, and you will actually go ahead and build the container image that's going to represent our test application through class. You will actually go ahead and do the Docker push command, and you'll actually end up pushing it into an image registry. And then you're actually going to end up running it over here with the Docker run command. When we're looking at container engines, right, it's the control plane, in our case in Kubernetes, that's installed on each of our container hosts. It doesn't have to be Docker. There's other choices to use, but any container engine should be able to, 1, build a container image, 2, it should be able to run the container image. And there's going to be other things that you're going to need from your container engine, your command line interface, your CLI. You're going to need it to be able to do things like commit a running container to an image. You're going to need it to be able to save an image, push it to a repository, stop, remove it, suspend it, restart it, and report its status, okay, besides building it. Now, all of these things that I've underlined and read, they're simply some format of the Docker command. So Docker build to build the image, right? Docker push to push it into a repository. I could do an RM or an RMI to remove a container. I could go ahead and Docker stop to stop a container that's running. Docker PS to report its status. So we're going to go over what those commands look like next. But first, let's back up and talk about what's inside of a typical Docker file. And one of the beauties and great things about working with containers, right, when it comes to working with containers versus working with virtual machines, for me to have built that application as a VM before, that VM creation, for me to be able to redo that, to reproduce it, is not necessarily guaranteed. Why? Because when I built the original VM that was running my timesheet application, I did it manually. I cloned the VM from a template. I went ahead and I grabbed some instructions. I typed in the commands manually to actually set up my dependencies and install the application. The beauty of using containers is it's always reproducible. Why? Because the information for me to build my container is inside this Docker file that's going to define each stage that's required to build the container image, which means now I have not only consistency, but I also have reproducibility. So if something goes wrong with my container that's my running version of my image, I can simply delete it and recreate it. So inside of a Docker file, we have in this example several commands. This Docker file would be used with the Docker build command to actually create the image. I could then use Docker run command. Now there'll be additional arguments behind it to actually run this image so I can test it. An important thing for you to be aware of, and this is something as you get more advanced in Kubernetes that we'll be talking about, is what do we want to allow and not allow? And for example, in this one, this is a pretty good syntactical standard that was followed in the Docker file. What do I mean by that? If you'll notice over here, behind Ubuntu is a :1804. Behind PHP, we've got an =808. Behind Nginx, we've got an =, and we're doing 1.20.1. it would be important for us from a standardization point to say we won't allow somebody to build a container image where they're not specifying the version. So they're going to leave this off. Well, if they leave that off, the equal sign behind the Nginx, which version of Nginx are you going to get? Well, the default is you're going to get the latest version of Nginx, which then I'm going to ask you, does that mean this is necessarily going to be reproducible? If I built it 2 weeks ago and I built it again today, and Nginx has actually updated their current stable version, the image that I'm building today is going to be using the latest version of Nginx, so I'm not guaranteed to get the exact reproducible image that was originally built. So you'll see inside later in Kubernetes that there's actually a way for me to say, disallow any image to run that was built from latest. It has to have specified the specific version so that I'm guaranteed it will be reproducible if I had to recreate it. I think we can understand the significance of that. Now, when a container image is actually being built, and if you did some type of inspection of that image, the image is actually built in a series of layers. And this specific example that we're showing you is an extra add-on that we added to Docker to be able to interrogate what an image looks like. Actually comes back to over here. This from Ubuntu, this is my layer 1. That's layer 1. I next came over inside here and I did this run statement. That's layer 2. And this right here is actually layer 3. So if you compare it inside here, you could see this is the base OS information. That was part of my container image that it's going to need. Here's my application dependencies. And then up here is the application code that was actually copied over. Okay, so it's used, it's a little bit like a snapshotted VM. Okay, with each layer inside there being an additional snapshot. How can I see what images I currently have right now on my workstation? So I'm running Docker. If Docker's been installed on my workstation, if I did a Docker images command, it would list out the images that I have. So right now I've got 3 images. Here's my image ID. When were they created? And then this is the size of the image. Actually, if you look over here at the images 2 and 3, they're actually the same image. But what we've done is we've given them different tags, okay? Different tags were added to them. If I wanted to see what containers are, what images are actually running as a container, I could do a Docker PS. These would be images that I'm running locally on my workstation. You could see inside here, this is the image that was actually ran. It's right now running. We're calling it, we gave it a name, My Website DB. We can see right inside here that it's listening on port 3306. We're going to be going through some basic Docker commands. This is not a course on Docker. This is just the basics. If you want more information, there's plenty of resources out there to learn Docker. But when it comes to running a Kubernetes platform, what we're covering here is probably enough knowledge for you that you would need to be able to defend yourself when it comes to trying to troubleshoot some type of problem. So here's the basic Docker commands. Docker run. Now, there's going to be additional arguments behind these commands. So when I do some Docker command, typically over the second parameter is going to be some verb, and then there's going to be additional arguments over here. The syntax-wise, if you just simply did a -- help, wherever you've built the command up to, would give you a listing of additional options that you could do. So Docker run what? I'm going to have to specify via these parameters what I want it to run. Docker stop, I'm going to need to give it an argument to say which container do I want it to stop. Docker rm would delete a container that was running, okay, that had been stopped. So if you want to remove a container out of the Docker runtime platform, you would first need to stop the container, and then you would remove the container. Now, it doesn't mean your image is gone. your image could still be persisting out there in the images section. So if I wanted to skip doing both of these steps, I could simply do a docker rm -f and the name of my container, and that would both stop it and remove it. How can I manage my images? Okay, so my images, all of these commands inside here would be things I would do against an image. Docker images would give me my list. RMI, build, tag, pull, and push would be how I would be either pushing them into a registry or pulling them out of a registry. Additional commands to go over, see what's going on with the containers. I could do a docker ps. That would show me any container that is running. If the container ran and it errored out for whatever reason, or somebody stopped it, it would still be inside the Docker platform as showing as a container, but it's a stopped container. If you want to see those stopped containers, you would have to use a -a. If I wanted to see why did my container stop, what was the error, I could do a docker logs to give me my standard error, standard out that would came from my container. I can do a docker exec, would actually allow me to run a command within the container so I could see what's going on. Like I could do an exec and actually start a shell and get into the container and actually do some diagnostic information inside there, as well as I can create a Docker network. So if I'm running something on my workstation and I've got Docker installed there, I could run a container here and go about testing it. Maybe my container's listening on a particular port. I could run the container image and I could go ahead, open up a browser, connect a local host on the appropriate port, and I would be able to connect to that container. What would happen if I had two containers and these two containers needed to talk to each other? I would need some type of network to have the two of them able to communicate with each other. So what would I do is I would actually use the Docker network command to create a network to have my two containers talk to each other. And that's what's going to be inside of your lab. That's what you're going to actually be creating. So when you're done creating when you're creating an image using the Docker build command, we obviously need to get it off of the developer's workstation. So where would we push it through? This is where that container registry would come into play. Okay, this registry is a central location for people to store their container images. There's a variety of different container images that registries that are popular. We've listed a few inside here underneath hosted and self-hosted. In our classroom environment, we're going to be using a test registry called Registry 2. It's not meant and designed for production, but it will be adequate for us to get through our class. Okay, your registries can be public or private, and this is where the developers would be pushing their container images to, and this is where in turn our Kubernetes platform would be pulling them from to actually run them. When you're looking at container registries, it's going to be important that you have features that would fit for an enterprise deployment. Things like being able to scan images to see if there's vulnerabilities inside them. Things like being able to sign them, so if there's a signature on them so you know the bits weren't mucked with. Okay. Harbor is a project that originally started inside VMware, and that project was completely donated to the CNCF. It is an enterprise class registry, and you're going to see that this is the solution that's integrated with several VMware products. Now, it doesn't mean you have to use a customer has to use Harbor. They could use something else that they felt is a better solution, but from a supportability standpoint, if they used Harbor when they called VMware for support on their Kubernetes platform, VMware support would support the customer in Harbor-related questions. Here's some of the features it has. It has RBAC features built into it. So maybe I have one developer working in one particular repository in Harbor and another in another, and then maybe I can have a different one that this is where they're supposed to dump their images at when they're ready to QA and test them. It has the ability to do vulnerability scanning either via Claire or Trivy. It has a way to sign the images via Notary. It has a way to do image replication. So if I've got a Harmer registry in Atlanta and I got another deployment of Kubernetes over in EMEA, I can have it replicate so people are only posting it once to Harbor, and then I could have it replicate that image over to my EMEA data store. It also does do Helm chart management. We'll talk more about that later, but that's how we install our code. So there is some additional references for you to take a look at that we've listed out here. I'm not going to review each one, but if you want to dig a little bit deeper, these are some excellent references for you to go through. And this right here represents our application that we're going to be using through class. It is imperative that you do this first lab, get it up and going, because this is the container images that we're going to be using through the rest of class. So you're going to end up building 2 container images. You're going to build the front end application, which was going to be our UI interface that you're going to open up a browser and connect to. And that's going to be connecting to a back-end application over here, which is my database, my MySQL. So when people request an account on my application, they'll be able to set up an account, username and password. They'll be able to log into the account. They'll be able to write stuff on their notepad and save it. They'll be able to let things go for a while, log out, be able to log back in, and they'll be able to continue to access their notepad. All the information about users and what they've been writing to their notepad are getting stored in the back end. So initially, after we're done building our 2 container images, you are going to have to create that Docker network so these 2 can connect to each other. And we're going to test this just like a developer would right on their workstation using the Docker run command. So we're going to get going inside lab number 1. Now I'm going to give you a brief, quick overview of the lab here on what you're going to be doing, and then you're going to see another video right behind this where my coworker Joe is going to walk you through how to gain access actually to your lab environment. Now remember, once you start the labs are only going to be available for you for 30 days. So hopefully you're going to finish this class within 30 days and the corresponding labs that go with them. Okay, so what are we going to do inside here? Once you gain access to the environment, you're going to see that there's 3 VMs after you log into your vCenter server. You're going to have 3 VMs that are not running. You're going to need to go ahead and start all of the 3 VMs, and the book's going to walk you through that. One of these VMs has the name of SA-master-01. That VM is going to simulate for us, in this case, the developer's workstation. So you're going to log into this VM, the SA master. You're going to review the application structure of our application. There's 2 key subdirectories. One subdirectory is going to be for the front end, and another subdirectory is going to represent all the assets for the back end. You're going to build 2 container images, and then you're going to go ahead and test them locally, including testing the application. Once you see that you've built it successful and the application's run, we're going to clean up for the next labs, and then we're going to tag the images and push them into a registry. So this is going to represent for you what it would look like, the workflow for a developer. So this is what the environment's going to look like once you get logged into it. And again, my friend Joe has a video that you're going to watch now. It's going to show you how to get into this. On the left-hand side, once you get logged in, is going to represent your desktop. We're calling this the student desktop. Your manual for you to go through the labs is going to be over here on the right-hand side. If it's collapsed, you just simply click the manual button and it will swing it out for you. So as I page through the various pages inside to get to my starting lab number 1 inside here, you're going to advance the slides forward or the pages forward for the lab guide. And you could see inside here it says access the student desktop. This is where you are over here. Step 7 over here is going to tell you to go ahead and launch Chrome and go ahead and get logged in. So I'm going to show you the start of it. Here I am, I've launched Chrome, and then they're telling you that you do have a bookmarks toolbar that I would simply use up here to access my vSphere client. The username and password that I'm going to use to log in is listed down here in your lab guide. So I'd go ahead and log in. And once I'm in, you're going to see the 3 VMs that I spoke about. So you're going to continue your way through getting these 3 VMs started so that you could begin your lab. So here's my vSphere client that's being loaded up. And once it's loaded, I could go ahead and expand out the inventory tree, go to my cluster, and there's my 3 VMs. I'm going to need to follow the instructions in the book on what it's telling me to do with these, right? I'm going to need to go ahead and power them on. And before I consider them ready to be used, after I've powered them all on, I'm going to want to confirm that their DNS name is added to the summary tab. And you could see that inside the lab instructions. So after you power it on, you can see here in step 6 under VMware hardware on the summary tab of each VM, verify the network adapter is connected, and then on the summary tab, verify that the VM's DNS name appears. So I'm going to click on SA Master 01. And inside the summary tab, I'm waiting up here for the DNS name to populate. So I think from here, you could probably go ahead and follow through with the lab guide and continue the rest of your lab. So go ahead and take a break if need be. Go ahead and take a break if need be. Come back after you're done with your break. Watch the video from my friend Joe on how you're going to gain access to our Lab Connect platform to do the labs. And then we're going to start on lab number 1.
Welcome everyone. This is Joe Cooper from VMware Education, and I'm here to walk you through the VMware Learning Zone lab environment for your courses. Hopefully doing this and watching this little walkthrough will make it a whole lot easier and answer a lot of your questions before they even come up about the VMware Learning Zone. Once you've enrolled in a course, you'll see the list of all of the different types of content that we have for your particular course. In this case, I'm looking at the vSphere Install, Configure, and Manage version 6.7 course, where there's some on-demand content, there's the lab, there's the assessment, and the evaluation. We're here to focus on the lab. So once you've logged into the VMware Learning Zone, and I'm going to assume that the fact that you have found this video tells me that you have logged in, okay? It's at vmwarelearningzone.vmware.com, okay? Hit the play button, and what'll pop up is the lab environment here. Now, it does take some time to get the labs fired up. At this point, the system is actually deploying an entire virtualized environment for you. So you should expect, depending on the course that you have enrolled in, for this to take a significant period of time in some cases. Okay, like it says over here on the right-hand side where your entire lab manual is, this could take as long as 10 minutes. Okay, so make sure that you're patient with this. And when we come back, we'll walk you through the process of actually completing these labs and actually also getting some help when you need it. Well, that didn't take very long at all. Now, let's have a look at what we've got here. Notice that I'm in a browser here, and there's a bunch of stuff going on. I've got a bunch of applications, and I've got a desktop system right here in the middle pane, and it gives me some notes, okay, you'll note that what we are looking at here is a host name called student-a-01. And for most of our courses, this is where you'll start by doing the labs, okay? You'll notice a few things on here. On the left-hand side, we have a console. And this gives us access to all of the systems that make up your lab environment. In this case, I have a domain controller and access server. This also will typically act as your default gateway. For the vSphere Install, Configure, Manage version 6.7 course, I've got 2 ESXi hosts, I've got a vCenter server, and I've got the desktop that I'm working on right here, Student A01. And I can actually switch between the consoles on any of these systems. Notice when I click on this particular console, as it loads, it will actually be an ESXi host, and you can see that right now, this host is actually currently firing up. So again, be patient with this, even though you've gained access to the system here. Okay, student A01 is fired up and you're logged into this. The rest of the systems may be still currently starting. Okay, so this console gives you an idea as to whether they have finished starting and you're ready to begin doing labs. Let's head back over to student A01 and we'll collapse the console tab and we'll look at a few other things. I actually like to view this in a full screen mode. So let's go ahead and we can maximize this. And if you're really clever about it, you can also hide the ribbons and things like that in your own browser if you like, or you can always scroll up and down. Note here though, that if I'm scrolling up and down, that I don't necessarily have full access to the menu bars and things like this on the bottom of the screen. Okay, so be aware of this. You may actually want to move into, for example, you can exit full screen mode here. Let's do that. Exit maximized mode. Okay. You can place this in the center of the page if you like. Okay. There's lots of different things that you can do with this. Also, note that you can, on the right-hand side with your manual, notice, first of all, there's 123 steps or 123 pages in this particular manual. Okay. You can increase the font size. Okay. Don't forget that you will have a scroller here. Okay. You can create a floating window for this that you can drag around if you like. You can change the pages using the arrows and things like that. Very nice. Lots of different ways to manipulate this window. Note that if you want to actually collapse this back to the side, just hit the X here and you can expand the manual again. Now, as you begin doing work in the labs, you will notice that as you go through these, you'll start a lab and that there will be a guide me video for each of these labs. So if you get stuck in any of these labs for any reason, don't try to, for example, open a console and reconfigure the entire environment. Okay. One of the things that you can definitely do is go through the guide me labs for each of these labs here. Okay. So you'll note you've got a number of these labs. All of them have a full guide me video, and it'll walk you through the process of
VMware
each
tools.
of the more complex components of
identified
the labs
by VMware
themselves.
ESXi, top left.
Now, if you're still stuck, there's always live help available for you during regular business hours. Okay. Don't forget, scroll up to the top of the screen and go ahead and find the help tab. There are a number of support options that are here. Okay. There are tips. You can download the user guide here for the VMware Learning Zone lab environment itself. Okay. Let's take a look at some of these support options. You can test your speed. If you're having trouble here at all with the environment. If it seems slow to you, you can head over to the speed test, where it actually allows you to start a test looking at all of the different components that make up the performance in your environment. Notice the speed of the learning zone, cloud speed, cloud latency, and VLP latency. So these are all different components that make up the performance in your environment. You can also email education support at edulabssupport@vmware.com. Okay? And you can have a look at some of the troubleshooting FAQs. Now, when you are done with the course, okay, you have the ability to end the particular lab setup. You've got 30 days for most of our courses to complete the course and all of the labs, like it says here, okay? You can exit the labs and return later, or you can hit the end button. Now, if you hit the end button, you are done with these labs. Hitting the end button says, I'm done with the labs, I'm done with the class, I've completed all my labs, right? Once you hit that end button, you cannot come back to these labs, even if you're within that 30-day period for which you have access to the class. Okay. Also note here that it says that in this case, I have not met the criteria for completing the class. You actually have to hit at least 50% of the entire lab environment in order to do this. So please keep that in mind. Here's an interesting trick. As you're going through the labs, the lab manual will give you things like credentials, or may have a series of commands that it asks you to type in, or set up a series of scripts. Okay. If you highlight text in the lab manual, you're able to drag that text into the console, where it'll actually fill that straight in for you. So you don't need to even worry about copying and pasting. A drag and drop does a great job, and then allows you to do things like log in to the vSphere environment. Oh, and one last thing. Don't forget, during normal business hours, you can chat with support. It's Inderg. Well, that does it for me. I hope you are really enjoying the online classes and you're having a good time with these labs. Of course, you can always reach out to us if you need any further support. I thank you for your time and attention, and have a great time. Take care.
And that concludes this second module that we've gone through about the benefits of containers, the relationship between containers and microservices, the various components inside your container platform, and the basic Docker commands. So I'll see you in the next module. Thanks. Hi, and welcome back to Kubernetes Foundations and Cluster Operations. My name's Mark Allenbaugh, and we're going to go into module number 3, Kubernetes Overview. So again, we've already spoken a little bit about what is Kubernetes, and the key thing to remember, it's an open source platform, and it's all about being able to manage containers. And it's going to be imperative that you've got a good skill set in place to be able to help you design, deploy, configure, and operate this container orchestration solution, which is Kubernetes. So we have 3 lessons in this module. The first lesson is an overview a little bit deeper about the Kubernetes architecture. So we're going to get started with this one next. After that, we're going to come back and actually look at the tools that would help us build a Kubernetes cluster. And we're going to be able to actually do a lab there where you're going to start with some simple virtual machines and do the appropriate commands using the kubeadmin tool to set up an open source Kubernetes cluster. Again, we're not going to be installing a particular VMware product that runs Kubernetes. We're going to use the native vanilla open source version of Kubernetes. And again, the skills you learn doing that will apply regardless of which Kubernetes solution you ultimately end up using for your company. Then we're going to come back after that lab and dig into this thing, which is the Kubernetes command line interface called kubectl or kubectl. So let's go ahead and get started. The first lesson here in this module is the Kubernetes architecture. We're going to talk about why you would be using Kubernetes, what's the purpose of using it, and then we're going to talk about the various components that are inside Kubernetes in which functions those components run or do for us when it comes to our orchestration engine. So remember, we've spoken about it several times before. We've got these cloud native principles, right? And if we follow these cloud native principles, we should be able to have our application run anywhere on any cloud platform. We should have a high degree of automation. We shouldn't be scared about doing an update daily or even hourly. Okay, so some of those principles is first of all, whatever your application is, it should be ending up being container packaged. Okay, each container should be an isolated unit of work. It doesn't require any OS dependency. It should be dynamically managed. So once you've created your containers, we're going to end up giving these containers to some type of orchestration process that process would actually handle the scheduling and the managing of those containers. So where do they get scheduled at? If one is not behaving well or it's no longer running, the management of it would say, I'm supposed to have this running, it's not running, let me correct it and make it running. We're going to go into the details of how that works in Kubernetes. And it should be microservice oriented. Now again, these are our principles, so where we're starting at and where we're trying to get to, it might be a journey through there. Maybe you can't have everything the first iteration through when your monolithic application's getting refactored. Maybe we're not going to be able to have everything as a microservice initially. But the goal is, these are the goals that we're trying to shoot for, and ultimately you'll get there once you start your journey. So, about Kubernetes, you've seen this slide before, so it is an intentional repeat. Again, it's an open source cluster management tool. The purpose that we're using Kubernetes is we need something to help us automate things like deployment, management, and scaling of our applications. This open source initiative is being managed by an organization called the CNCF. And those are the people representative from a variety of different countries all around the world that are contributing and actively participating. That team of people that are involved with the CNCF are the ones that are steering the direction that Kubernetes is going in. New features that should be added, things that they're going to deprecate, and the reasons why. It was started about just a little bit shy of a decade ago when some former Borg engineers, people from that were working on the Google project, had all this experience of what they did at Google to make up all the various Google data centers and the functionality that we've seen that Google has been running. They learned some pretty good lessons over about a period of a decade. They took the best of the best and they put that inside Kubernetes, and we saw that first release of Kubernetes coming out a little bit shy of a decade ago. My Kubernetes cluster does need physical CPU and RAM. Now, how do we expose that into Kubernetes? We could do it bare metal. We could do it based upon a hypervisor between the physical server and what's going to be our host OS that's going to be running on our worker nodes. We could actually run Kubernetes on a variety of cloud providers. Everything you're learning in this class would apply to you regardless of where it's actually being ran at. So this one slide, we need to spend a little bit of time on this and make sure that you fully understand this. A key part of Kubernetes is its declarative nature. Most of us that have been doing stuff for as long as your IT background is, we're pretty much so used to doing it this way, the imperative way. So if I said right now, hey, I'm feeling a little cold, instead of me just setting the desired temperature of what I want the room temperature to be, I'm going to need to come inside here using the imperative way, and I'm maybe going to have to grab the temperature control here, and maybe I would slide it some over to the right. I'm going to say, well, I need a little more heat blowing on me, please. I could go ahead and raise up the fan control so that it's blowing a little bit harder. And I'm probably going to need to take the system from an off state to actually maybe move it over here to the heat section, and then I can control where I want the heat blowing out of. And then at some point, it might get a little cold or might get a little bit too hot. And I go, oh, no, this is too hot. Let me go ahead and slide the control back down. As you can see, who's doing all this functionality is me. I'm responding to something, some state, and I'm saying, I don't like this current state. Make it a different state. With Kubernetes, cloud native principles, we should be doing everything in a declarative nature. So I simply declare what I want. I'm going to say, you know what? I want it to be 72 degrees. I would like to have the environmental system blowing this air more up at my, chest level and maybe at my feet. And you know what? The person on the right-hand side of the car, they also would like it to be 72 degrees as well. I've declared what I wanted. Now what happens? Well, there's going to be some systems that are actually evaluating what it is I asked for versus what it is right now. So this declarative control over here, something inside behind, this car, there's some CPU, some process running something that's sensing what is the temperature now? What is the desired temperature? Do I need to blow cool air to achieve that? Or do I need to blow warm air? Or am I all good? Let's just slow things down and just, relax. Well, this side here pretty much so is a good example of what's going on inside Kubernetes. In Kubernetes, we're going to declare what I want. I want my application running. I want this amount of copies of my application running for high availability, for better throughput. Then something is looking at what is the desired state. I've declared what I want in this declarative file versus the current state, which means we've got some processes that are constantly running, evaluating current state versus desired state. And it's important that you grasp this concept. I've taught several classes, that involve Kubernetes clusters, and there's a lot of questions or bewilderment happening on people. It's like, yeah, I don't understand why this is happening. I don't understand why this is happening. Right here's the reason. Understand that we declare what we want, and there's going to be Kubernetes processes that are going to be automatically doing things for us. And that's what we want. We want this degree of automation. Now, how is that occurring? Here's the basic Kubernetes architecture picture, which is important for us to make sure that we're kind of saying, okay, now I see what the architecture looks like. Around the red box that I just drew is my Kubernetes cluster. So normally when we're going through some slides, you're going to simply see a box that says this is a Kubernetes cluster. What's inside the box? Well, inside of a Kubernetes cluster, you're going to need a control plane VM at a minimum, single. For production purposes, we should have 3 of them. Again, high availability and throughput. Then we're going to need these things on the right-hand side, which are called my worker nodes. This is typically where my workload is actually running at, my pods. Now, each of these are going to be a series of virtual machines. You notice we're saying VMs. Now, how many worker nodes do you need? I don't know. How much workload are you going to put at them? They're VMs. How big are you making them? How much CPU and RAM are you giving each of the VMs? They're all good questions, and obviously it is going to affect how many pods you can run. We want to focus at this point in the architecture about some of those processes that are running. The first and most important piece we have in our Kubernetes cluster is this guy called the API server. This is how we interface with Kubernetes. Now, the common tool we use to interface with Kubernetes is our command line interface, CLI, called kubectl or kubecontrol. That would be installed on your workstation. There's distributions for Windows, Linux, and Mac. You would go ahead and install that, and then I'm going to run some kubectl command, and that kubectl command actually ends up talking to the API server. The API server is going to take what you told it to do, validate it, and if it's valid, we'll post it to a persistent database called etcd. That's a key value store that we'll talk about that stores my desired state. Then what's going to happen is we have these processes across the top, the controller manager and the scheduler. So if I said to the system, hey, I would like 3 pods running, down here in the etcd database, it would say, I want 3 pods. Also, the worker nodes out here are communicating back also to the API server. And what are they posting is they're posting down here into etcd the current state. Now, what's going to happen? The controller manager, in its variations of different loops that it's running, is going to be comparing, is the current state equal to the desired state? If it's not, it's going to say, I need to fix that. So ultimately, what will end up happening is the scheduler would get woken up and saying, hey, I only have 2 pods. I'm supposed to have 3 pods. Initiate scheduling a 3rd pod. The scheduler is going to end up looking across the worker nodes, just like our distributed resource scheduler does, and seeing which one of them has the most amount of capacity available, where would the pod fit at the best, and then ultimately the API server and the kubelet that communicate with each other would say, on this worker node, you need to go ahead and fire up another pod. So just to quickly summarize this. When you're looking at any pictures that we're going to be doing in the class, you're going to see a box that comes around that we're depicting in the box. And in that box, we're just simply saying, this is a Kubernetes cluster. That's what we're going to be saying. Inside of it, we're not going to be depicting all the components that make up the Kubernetes cluster. What makes it up? At least one control plane VM. Typically, it's either 1 or 3 VMs would be sitting out here. 1, development, test, QA. 3 would always be your production deployment. And then a series of worker nodes. And this could be, anywhere in a range from, let's say, 1 to 50, depending on the amount of workload. Architecturally, we've got processes that are working, which we're going to be reviewing in more detail in the slides coming up. So let's go ahead, take a break here, and when we come back, we'll continue on a little bit further with some of the problems that Kubernetes is solving for us. Thanks. Hi, and welcome back. Let's go ahead and continue where we left off at before the break. So we're going to talk about the problem solved by Kubernetes. When you did lab number 1, one of the things you probably noticed is that you can actually run your containers just by using Docker. So what is Kubernetes then doing for me? Well, I want you to kind of imagine if you had a series of ESX hosts, but no vCenter to manage them. Could I run my virtual machines just using the DC UI of ESX? And the answer is yes, I can. But I'm not going to be able to do all the additional features that vSphere does bring to the table. And that is a pretty good analogy when you're looking at what is Kubernetes and why do I need it. Docker, although it can run a container, it's focusing on a single container host. What happens when I start getting, as we illustrated earlier, if I had multiple worker nodes, now I have 3 or 10 worker nodes. What's managing the workload across all of those respective worker nodes? That's where Kubernetes comes in. So when you start getting a large number of containers that you want to be concurrently being ran, you want something to be able to restart a failed container, you want it to be able to potentially scale containers up to meet capacity. That's what we call auto scaling inside Kubernetes. If I see that the 3 instances I've got working or deployed of a particular workload, and I see, let's say, its utilization reaches some threshold, I could have Kubernetes automatically scale up additional number of those pods to accommodate the additional workload that's coming on. That's only done inside Kubernetes. How do you handle things like networking and load balancing? All of these are problems that Kubernetes is solving for me via its orchestration layer and the various watch processes that are going on inside Kubernetes, which we're going to explore. So, one of the things we learned a few slides back was we need to declare what we want to Kubernetes. And how do I declare that? I'm going to make my declaration of what I want by using these things called manifest files. Manifest files are written in YAML. They have a syntax that actually declares the configuration that I want. And it's going to be achieving that via some basic API primitives that you'll see that are added inside each of your manifest files. So we will go ahead and explain to you what those basic Kubernetes object types are. So once I've declared what I want in a manifest file, and then I've passed it over to Kubernetes and said, this is what I would like, it's Kubernetes and its processes that manages the actual creation of those requested primitives and ensures that I have that desired state running in my current state of my Kubernetes cluster. So here's an example of the first and most commonly seen object you're going to see inside Kubernetes, which is my pod. So a pod manifest file looks like the example we're illustrating for you here. It has 4 distinct sections inside of it. The API version, which is important for us to actually include that. So in the future, if we upgrade to a new construct or a new primitive for pods, we can now say, okay, this is version 2, this is version 1. My old version 1 stuff would continue to work because I've declared the version that this declaration is using. What kind of object do I want? So you'll see here there's a kind key value pair. That's what's making this a pod object. I'm going to include some metadata about my pod. One of the important things here is what's the name of my pod? What labels is my pod going to have on it? We're going to explore that a whole bunch more. And then finally down here at the last section here is my specification. I want a pod, and in my pod, I want some containers running. Here I'm defining just one container. I could have defined multiple. We'll talk more about that a little bit later. My pod name is going to be Nginx. It's going to use my container image, which is my Nginx 179, and it's going to be listening here on this respective port. Now at this point, we're not going into each of the objects. We just want you to see a basic manifest file. What's in it? What does it look like? It's going to be in YAML, and it's going to have a strict syntax that needs to be followed. When you're looking at a pod is the thing that is actually running your container. Additional containers could be ran in that one pod, so I could have another container over here, another container here. Normally, what you're going to find is, as you deploy your workloads, is you're typically going to see a pod and a container are in a one-to-one relationship. So it's normally one container per pod. The pod, when it's being created by Kubernetes, gets its own IP address. That's being assigned from the Kubernetes infrastructure, and there's an actual CIDR block that is being declared that you're saying, here, Kubernetes cluster, assign your pods an IP out of this range. These pods, this pod and this container live and die together. So if something happens here and I say I don't want this pod anymore, then when this all goes away, so does my container that's running inside of it. You could put additional containers inside the pod, and we'll give you some use cases a little bit later on why potentially you would do that. What we want to focus at is the architecture inside Kubernetes that is going to be the infrastructure that's actually running your pod/container. So again, when we're looking at our Kubernetes building blocks, okay, your building blocks inside Kubernetes are going to be these things called pods, these things called nodes, and then this thing called a cluster, and that would be your Kubernetes cluster. Okay, so you can see the picture down here. This blue box that's around here is my Kubernetes cluster. And again, inside my Kubernetes cluster, I'm going to have a series of nodes. How many? The size? That's up to you when you're creating the cluster. In this particular illustration, we have one control plane node. And again, typically these are going to be running as a virtual machine. And then we're going to have 3 worker nodes that are sitting over here, and they're also typically going to be a VM. Again, size of them is up to you when you're creating your cluster, your Kubernetes cluster. My worker nodes, if we want to think about this, represent my data plane. This is where the work is happening. My control plane is controlling what is being ran in my data plane. So there's that intercommunication between control plane and data plane. On a particular worker node, you could have several pods running. So I could have had a third pod over here. So a question comes up. Well, how many pods can I run on a worker node? I don't know. How big are your containers and how big did you make your worker nodes? Same, formula equation you would say is how many VMs can I run on an ESX host? Well, I don't know. How big's your ESX host? How big's the hardware? How big are the VMs? Right? That's all going to come into play. How much overcommitment do you want? Okay, all of that we've already learned about running our virtual infrastructure somewhat applies inside here in Kubernetes. So let's dig even deeper. Inside of our Kubernetes cluster, you saw on the architectural picture a little bit earlier that the API server, which is the main REST entry point into Kubernetes. This is how I tell Kubernetes to do something. I'm telling it via a command line interface that I'm making a call to the API server to say, here, this is what I want, this is what I'm declaring. The API server on the control plane nodes and the kubelet process, which is running on each of my worker nodes, are talking back and forth to each other. If some new work needs to come into my cluster, it's given to the API server. The API server, in turn, is going to ultimately hand it off to the scheduler to figure out which worker node to run it on. And if need be, then, maybe a third pod would be created here and a third pod would be created over here. Let's dig into the control plane known processes a little bit deeper. So the API server, it is the front end of the control plane node. This is the RESTful interface that I'm using to be able to make either command line interface commands calls to, or I could write a program that's going to be using API calls into the API server to invoke the same thing that I'm trying to achieve. So you could actually have some automation system in front of Kubernetes and have it making API calls to Kubernetes to achieve whatever your business objective is. These calls that we make into the API server, we're going to be passing in a JSON representation of our declared state that we want, and then the API server in turn is going to return to be the objects that, for example, if I did a kubectl get pods, so that command call that I make into the API server, I've asked for a listing of all the pods. It's going to return a JSON file back to me that represents the pods that are currently right now defined in that respective cluster. The information about that what is supposed to be there is actually being stored in the etcd database. So that's my key value store. It is a leader-based clustering system. Normally, I would have 3 control plane nodes. All 3 of them are running etcd, so I don't have a single point of failure. They're using a master election leader role-based structure to do that clustering. He's also in the etcd database going to have the known state about the cluster. That's where kubelet's talking back to the API server and saying, hey, I got 3 pods running. I've got 3 pods running. I've got 4. So all the worker nodes, if we go back to this structure here, all of these are reporting back to the API server, hey, this is my current state. This is what I have running. That information is being persisted also out to the etcd database. The controller manager, he's running a series of control loops that's going to be always looking at the current state versus the desired state, and if need be, making the changes that are needed. Say, oh, current state is 3, desired state is 4. I'm missing one. I need to go ahead and make the appropriate change so that I could bring the desired state and the current state into an equal state. When it comes time to scheduling a pod, who does that? The Kube scheduler. So he's topology aware about your cluster. He's able to do things which we're not going to cover in this class, guys, things like affinity and anti-affinity rules, okay, to actually make sure that maybe my pods are not scheduled on the same worker node. He has all that capability built into him. So our next module that we're going to take a look at is going to be etcd. etcd, again, is the database where the desired state is being stored at. It's considered the one source of truth. This is what the cluster's supposed to look like. It might not look like it now, but this is what it's supposed to look like. Okay, it's a distributed key value store. So in a production environment, again, I would have 3 control plane nodes here. So I would have 3 copies of the database distributed across the 3 of them. The functions that it's performing, you will get into it the observed current state of the cluster. So kubelet and the API server are constantly communicating back and forth, and kubelet is actually feeding up the current state of each worker node over to the API server, and then in turn the API server stores the current state as well in the etcd database. Via one of the controller loops, it's going to be finding the differences, again, between desired and current state. And that configuration data is what is used that we would actually use to configure the nodes. So I'm going to be saying this node needs to have this type of workload running on it. And again, as we said, it's distributed across all of the control plane nodes. You could, if you were trying to locate a service, use etcd for that. Okay, so etcd does know what services are running. We'll talk more about how service discovery works in a later module. So we've been going at this again for about 15 minutes. Why don't we go ahead here and take a break? And when we come back, let's do the same thing for our worker nodes. All right, I'll see you back in a few minutes. Hi, and welcome back. So before the break, we had gone over what is some of the details about a Kubernetes control plane node and the processes that were running on it. So if I go back one slide, you could see we've taken the control plane node and we've kind of picked it apart. What are each of the key main processes that are running on the control plane node, and what do they do, so we've got a better understanding. And then we also explored what's going on inside our etcd database. We left off here, and this is where we're going to pick up doing the same thing through our worker node. So the kubelet process that's running on each of our worker nodes. This particular Kubernetes node agent that's running is going to be responsible for ensuring the containers that we said we wanted running, which would end up getting running inside of a pod, are actually running and healthy. So when the API server told this kubelet, hey, I want you to run this pod with this respective container inside of it, and also here, kubelet is going to be constantly watching over those pods, make sure that they are running, and in turn reporting that status back up to the API server. Kubeproxy is going to be involved with service discovery and the IP connectivity that's coming inside the worker node. We're going to explore this particular in more detail in a later module when we talk strictly about Kubernetes networking. But for right now, you want to be aware that it's responsible for doing things like creating virtual IP addresses for external access and making sure that, if necessary, the IP tables on that particular worker node are actually updated to reflect that. Okay, that's, again, we'll cover him in more detail in a later module. Then we've actually got our pod. So this is our unit of work that we're running. And a pod is a key object inside Kubernetes. It's the smallest unit of work that Kubernetes is actually managing. And it's going to be one of those key objects that we're going to be spending a lot of time talking about. Finally, at the bottom here, we've got our container runtime interface. What runtime structure or process are we going to use to actually run our pods in our containers? Containerd is very popular. It used to be Docker, but Docker's much more of a front-end UI building tool than it really is more of a back-end running tool. So you'll start seeing now Containerd, which was actually a initiative originally underneath Docker. They actually split it off on its own project, and it actually is what we use to run our containers. You can also use other runtimes like CRIO, for example, would be another example of what you can use, but you're going to need some process that's capable of running your containers, and the most popular one you'll probably see now is Containerd. If we're looking at our layers inside of what we're going to have running in our infrastructure, this layered environment kind of it helps us understand what's happening at each layer. Obviously, you have a physical layer. You're going to have hardware. You're going to have physical servers, routers, switches, etc. You're going to need something on top of that hardware. It could be a virtualization layer. We think that's the most efficient way to run workloads is via this virtualization layer. It's got a lot of benefits. You notice we're not saying specifically vSphere here. It could be any virtualization layer. On top of that, if we want to get here to Kubernetes, we need some mechanism to create that particular layer. We know down here on the virtualization layer here, we're going to end up using vSphere, potentially vCenter Server and ESX hosts. They would need their appropriate installation and configuration that would happen to them. If we want Kubernetes, we're going to need something to install Kubernetes, manage it, and update it. One tool that we're going to talk about in our next lesson is this thing called Cluster API and why we could have Cluster API actually create Kubernetes for us. Once we have our Kubernetes platform, then in turn we could start having Kubernetes deploy and run for us our containers and our applications. If we start to put to the right of each one the various different components and software layers or applications that would be involved, you could start to see inside here the things I've already discussed with you. At the hardware layer, we've got our servers, switches, routers, and arrays. Virtualization, we're going to go ahead and give you examples in the vSphere, VMware offering. For Cluster API, that would be the thing that would actually orchestrate the creation, updating, patching, and management of my Kubernetes. Kubernetes then in turn falls into this section here. And this is where we're going to be focusing the majority of our time. We're going to talk to you about what happens once we have our Kubernetes platform up and how does it do things like deploy a particular application? How do we update a particular application? So the users are up here connecting to the application. The infrastructure below that is what is actually running your application. Kubernetes is responsible for the stuff above in the layers. Beneath the Kubernetes platform, we're going to have various components that someone's going to be managing, upgrading, patching, etc. So when you're looking at a full stack of Kubernetes, which is, this would be a full stack of Kubernetes. I've got my hardware, my virtualization, my cluster API potentially. you got to start asking some questions. So on your physical infrastructure, how are you going to manage your physical infrastructure? Again, we're not here to discuss that, but it's a question that needs answering. For your virtualization layer, right? That's where you're going to do things like managing hardware contention, failure and changes, updates, right? Your virtualization infrastructure should have those tools to be able to do that. Okay, we're all familiar with this, so we can kind of leave this behind us and say, okay, let's move forward. I want Kubernetes now. I understand how to manage this stuff beneath me. Well, when it comes to start managing and doing stuff in Kubernetes, there is some additional questions you're going to have to answer. And depending on what you're having beneath this layer is going to potentially dictate what can and can't be done. So inside Kubernetes, we're going to have to address how are we going to handle container persistency. We have a whole separate lesson that we're going to go through over container persistency. So how are you going to handle doing and mapping through into Kubernetes persistent storage? What are you going to use for container networking? Okay, there is going to have to be a choice that's made. So how are you going to handle the communications between the various pods/containers? You're going to have to choose a networking solution to do that. In our class, we're going to choose a particular one. We're going to explore your options in that networking section, which will be coming up a little bit later. We're going to need to understand what tools can we install here that's going to monitor the health, the healing, and even the lifecycle management of my platform that I've deployed, which is way up here, Kubernetes. Am I going to have better monitoring tools that could actually look at a container running in a pod, running on a worker node? What type of logging am I going to end up using? What type of tools, monitoring tools are going to let me know, listen, you're out of capacity of worker nodes. You need to make more worker nodes. Or this particular container is very bloated. It's sucking up all your CPU and RAM. So again, over here, how do you monitor till you're running Kubernetes? How are your VMs and your Kubernetes systems going to be healed and potentially restarted? We're also going to need to take a look at how are you going to handle a new release of Kubernetes. Kubernetes rolls out about every 3 months. There's going to be a new minor version. How are you going to handle updating and patching? We're going to cover that in almost our last module to show you the things you need to be aware of when it comes to doing monitoring and patching. Finally, way up here at the top, we actually get Kubernetes. Kubernetes is certainly going to be doing our scheduling and our orchestration, our service creation. But you're going to also need to make a decision here as to how are you going to secure your images? Well, how I secure my images is I'm going to have some container image registry that's going to store them, sign them, and do vulnerability scanning against them. All of these things are going to come into play when it comes to running a Kubernetes stack. You're also going to need to know, regardless, of which choice you make here, core Kubernetes. And that's really what we're focusing at in this class. But all these other pieces are going to come into play. And when we're looking at core Kubernetes, we're going to need to have to understand what did you use for networking in Kubernetes, because it is going to affect what type of objects and what kind of services you're going to be able to consume when it comes to networking. When it comes to persistent storage, there's a standard way we do it in Kubernetes, but that's going to be affected by what solution you use to do persistent storage. So how does Kubernetes handle these different choices you can make? Kubernetes is using a thing called a plugin architecture. So what we have in various parts of Kubernetes is the standard interface that's going to allow us from within Kubernetes it all appears the same. But outside of Kubernetes, depending on what you chose for either the runtime interface, the networking interface, or the storage interface, it might result in different API calls being made to those various systems. We've got 3 areas of plugins that we want you to be aware of. The first is the container runtime interface. That's where Kubernetes is able to talk to the container runtime engine, something like Docker, Containerd, CRIO, to say, I need you to run this container now. So there's a standard way in Kubernetes that we make that happen. We go to the container runtime interface, and it will handle the peculiarities of dealing with a various different container runtime that you've chosen to use for your engine. Same thing's true for networking. When we go to take a look at our CNI, which our CNI stands for our container networking interface, this is how Kubernetes, when we say, I need a pod and it needs a port connected with an IP address, depending on which CNI you've chosen, it could have been NSXT, Calico, Antria, that would plug into the CNI interface inside Kubernetes, and it would handle the peculiarities of how we do networking in Calico versus Antria. Same thing's going to be true when we look at our storage interface. So inside Kubernetes, I'm consuming this thing called a persistent volume claim, or a storage class. Well, depending on which type of storage you use, that is going to be implemented potentially different, and the storage interface would handle the peculiarities of dealing if it has to make an API call to a NetApp, to an EMC, to a Hitachi, to an NFS base. The storage interface would handle that, or even a Cinder storage, or an S3 bucket, or an Elastic Block in EBS inside AWS. It handles the peculiarities. And why is this so important? We want portability of my application stack. If I've defined things inside Kubernetes, I should be able to pick that definition up, my manifest files, and say deploy it on cluster A. And cluster A might be running on Hyper-V, it might be using NFS storage, and it might be using Calico. My applications should still deploy and run. And then I could say, no, I now want to run it over on cluster B, and cluster B might be running on vSphere with vSphere-based storage policy-based management and running NSXT. It should still run successfully and function perfectly fine. The idea is, by using these respective different plugins, you're going to get that portability of running it on any various Kubernetes stack, and it will run unchanged. And that's the beauty of what we were looking for inside this Kubernetes stack. So, we've covered a pretty big whirlwind of various things about Kubernetes. We've covered the basic architecture. We've told you why you're using Kubernetes. We want that degree of automation. We've looked at the various Kubernetes components, the things that have comprised our control plane, the things that comprised our data plane, and then we got into the different layers of Kubernetes that you need to be aware of. Again, this class, we're going to be focusing on core Kubernetes. We're not going to get into a lot of the specific details as to why you would use one plugin over another. We'll give you some choices that could be typically used, and then ultimately the choice would be up to you. So with that, let's go ahead and call this lesson a wrap. Stand up, take a break, stretch your legs, and I'll see you back in the next section. Hi, and welcome back. Let's go ahead and get started with lesson 2, which is going to be talking about the tools we could use to build Kubernetes clusters. And the objectives of this lesson is we want to show you the various tools. This is not an exhaustive list of all the tools possible, but some of the most common ones that you would use. We're also inside here Earlier, I had introduced to you the concept of this thing called Cluster API. So we're going to dig into this lesson. How does Cluster API actually work? And what is it doing for us that should pique our interest? And finally, we're going to end this lesson with actually building a Kubernetes cluster. So that we'll conclude with lab number 2. So again, this course is talking about core Kubernetes. We're not specifically going to be talking about a VMware product solution that you would use to run Kubernetes. However, we're going to give you the overview of how Cluster API works, which is how 2 of our products use to actually, the tool we use to provision Kubernetes clusters. So first of all, let's do a general overview of some Kubernetes tools. Depending on what you're trying to achieve, there's going to be different tools you would typically use. If you're trying to come up with a development environment, then tools like Minikube and Kind would be very popular for you to use. However, if you're trying to build an enterprise-grade Kubernetes deployment, then tools like kubeadmin and Cluster API would be much more commonly used. Now, regardless of what you're going to end up trying to build, in either case, you're still going to need the kubectl CLI tool installed on your platform to be able to have your command line interface to interact with Kubernetes. So let's talk about kubeadmin. Been around for a while. What is the purpose of kubeadmin? We want to bring up a minimal viable Kubernetes cluster. So it's going to be about setting up the control plane, the creation of the control plane, and getting it set up and operational. It's also the tool you would use to join your worker nodes to the control plane. It does do certificate creation and management so that my control plane nodes and my worker nodes have certificates to authenticate each other. And it will do the initial creation for us of an account so that we've got credentials to be able to authenticate against our API server. What doesn't it do? Well, it doesn't provision the actual machines, or VMs in our case, that we would be using to install the kubeadmin tool in and to make our control plane node or our worker node. So he has nothing to do with provisioning the actual machines that we would need to run our Kubernetes cluster. It's also about not installing nice-to-have add-ons. A very common add-on would be maybe I need something for logging, or I need something for monitoring, or I need even a solution for authentication. Those would be all admins or additional add-ons. kubeadmins are not about helping you install those or helping you set those up. Each of those respective add-ons have their own mechanism to install them. kubeadmin is the tool we're going to use in our lab. And it's going to be very simply, we're going to run a kubeadmin command line that will actually set up our first control plane node and initialize our Kubernetes cluster. And then we're going to turn around and run it 2 other times, but instead of doing an init command, we're going to do a join command. And that's how we would get our 2 worker nodes to join our cluster. And then we'll end up with an operational cluster. So there's another way you could create an enterprise cluster, and that is using Cluster API. Now, Cluster API is not a product. It's actually a sub-project of Kubernetes. And what does it do is providing me the ability to basically have Kubernetes managing Kubernetes. If you think about the declarative nature that we've got inside Kubernetes, where I have a desired state and I've got a current state, and Kubernetes tries to reconcile so that they're equal, I could now have Kubernetes watching another Kubernetes cluster and making sure if it was supposed to have 3 control plane VMs and 3 worker nodes, that it's always in that state. I could have it do things like do lifecycle management for me of another Kubernetes cluster. So how this is going to end up working is we're going to create one Kubernetes cluster. This management Kubernetes cluster we would then use to have it deploy another Kubernetes cluster, and etc. I could have it deploy another one as well. It kind of could, some people have given me, it's kind of like nesting ESX. Somewhat, yes, it's a little bit like that. So with Cluster API, you can actually go ahead and you would first create one cluster here that this first cluster is the first element you need to create. This is what has a special term on it called the management cluster. This cluster in turn is also running Cluster API, so there's some additional stuff that actually would be installed on it. This particular cluster performs the role of the primary management, and it's going to be the main operational center to manage lifecycle of these clusters over here, which we're going to call these our workload clusters. That's what we're going to call them. Those are my workload clusters. So that's where your applications actually run. So this particular management cluster, after I have it set up, I would actually do some type of kubectl command to this management cluster, and that would instruct him to create this cluster. Now remember, when we have a blue box here with a picture of a cluster in it, what's inside the cluster? Well, this cluster could be 3 control plane VMs, if it's going to be production, and then it could have a series of worker nodes down here. So these could be my worker nodes. This would be my control plane VMs. So one blue box is potentially going to have multiple VMs inside of them. And those VMs are now configured to talk to each other and actually provide us Kubernetes functionality of a cluster inside of it. Who did that? The management cluster. It's going to actually go in and provision this cluster based upon the specification that I gave it. So workload clusters are the clusters that you deploy from the management cluster. The life cycle of these Kubernetes clusters over here, patching them, upgrading them, scaling them larger, they're all done via the management cluster. So I would do some command to the management cluster and say, hey, this cluster, I want a 5th worker node, please. I would just give it a command, and this management cluster then would in turn make the appropriate API calls to actually spin up a 5th worker node in that particular cluster. So realize that these clusters, all of these clusters, are running on top of some infrastructure. This infrastructure at the bottom could be vSphere, right? It could be a vSphere environment. It could be an AWS environment. It could be an Azure environment, and the list goes on. These are my cloud infrastructures. We're going to refer to this as our IaaS system, our infrastructure as a service system, and it could be whatever fits, the requirements for your project. Now, how does this cluster API functionality running on my management cluster actually communicate with the infrastructure as a service? Because it's this infrastructure as a service where we would actually create the virtual machine. So before we get into looking at how the cluster API is actually able to talk to our infrastructure as a service, we need to first kind of lay out for you the various functions and layers inside this cluster API architecture so that you've got a better picture of how this is going to work across different IaaS platforms. We've got three distinct layers we want to focus on. On the right-hand side of this, we've got from layers 3 down through layer 1. So you could see down at layer 1, at the very bottom of layer 1, we've got different actual infrastructures. Azure, Amazon, vSphere, even OpenStack, Google, they're all showing up as valid infrastructures at the bottom tier. On top of those infrastructures is where we're actually going to create these things called machines. Now you notice we're not calling it a virtual machine. That's a name that's been coined, that vSphere is more indicative of a vSphere as a virtual machine. On AWS, it would be called an EC2 instance. So we need a universal way to refer to that layer, and that functionality is going to be called a machine. Now, how do I actually get Kubernetes up and running on top of those machines? The most common way to do that is via a process called bootstrapping, which is going to involve me using kubeadmin. Now, where does kubeadmin actually operate at? It's all about, in this layer 2, using kubeadmin is about getting Kubernetes running on top of the respective nodes beneath it. That's what kubeadmin's about. So where do we start looking at Cluster API? Well, Cluster API is living up here at the very top up on layer 3. And Cluster API is going to be able to make specific calls up here at the Cluster API implementation and actually reach all the way down to the infrastructure and actually have things invoked like provisioning of actual machines. He can actually reach down there and say, infrastructure, provision a machine. In order to do that, we're going to need to do some extensibility, which is going to involve us coming up with a new API spec, new custom objects, and define what is a cloud provider. So, let's talk about our infrastructure providers. This is something that would actually be installed inside the Cluster API depending on what infrastructure you want it to talk to. So if my underlying infrastructure that I want my Cluster API to talk to would be VMware vSphere, I would install an infrastructure provider referred to as CAPV. And that's a particular package that would end up getting installed. There would be configuration parameters so that we would know how, in our case, to talk to a virtual center server. If I was going to end up talking to AWS, I would install the CAP-A. I would have to go ahead and get information on how to get to the AWS console, and I think you're getting the gist of the rest of the providers. So Cluster API by itself is not going to operate until I install an infrastructure provider so that it knows how to talk to the underlying IaaS system. And each one of them is going to have a series of custom resource definitions and additional processes or controller managers that are going to need to be installed to be able to watch over, are those machines actually provisioned? How, is the desired state equal to my current state? And the custom resource definitions are unique to that platform. So in vSphere, for example, the CAP-V is going to be able to give me an object that I can define as a vSphere cluster, a vSphere machine, template, and an actual vSphere VM. This would look different if I had installed, for example, the CAP-A. Now, we're not going to review all of them, but I wanted you just to get a taste of what Cluster API would actually end up looking like. Cluster API has its own set of CRDs. So when you're running Cluster API, there's always going to be these additional custom resource definitions. these custom resource definitions are actually being implemented in the respective infrastructure provider. So a cluster API cluster would actually be implemented as a vSphere cluster if I was running on top of vSphere, right? If I took a look at a machine here, describes a machine using a machine spec, it would have in turn been implemented out here by using a vSphere machine and a vSphere VM. That's how it would actually be implemented. So it's how we abstract away the uniqueness of each of the underlying infrastructure providers is handled in their relative packages. The cluster API CRDs are actually linked to those respective implementations based upon the IaaS that you're running. You're also going to have some additional controllers that are going to be defined when you do cluster API. These controllers are looking over, again, desired state versus current state. They're going to overwatch those. So the main cluster API controller manager is going to, in general, just look over the overall cluster API functionality. Then you're going to have unique ones, the Cap Kube Admin Control Plane and Cap Kube Admin Bootstrap. Each of those are going to be, one's going to be handling my control plane nodes and the other's going to be handling my worker nodes. So Cluster API is a much easier way for us to be able to get Kubernetes clusters up and running and to be able to, in general, oversee their lifecycle. When you look at different solutions from different vendors on how they're implementing Kubernetes, you're going to find the majority of them today are going ahead and using Cluster API. VMware's, the first two products we covered, actually use Cluster API. So vSphere with Tanzu and Tanzu Kubernetes Grid are both using these Cluster API controls in sub-project to actually do the lifecycle and management of Kubernetes clusters. We're going to jump in and do lab number 2. However, we're not going to use Cluster API. We're going to use the simple kubeadmin command to actually build our Kubernetes cluster. So what you're going to start with in lab 2, when you log into your lab environment, you're going to see that we've got 3 VMs created for you. You powered them on in lab 1. So we got one VM, which is called SA Master 01. And then over here, we're going to have 2 other VMs called SA Worker dash, one will be 01 and one will be 02. Now, what are we going to start with? You're going to first SSH here into the SA Master 01, and you're going to run a kubeadmin init command here. And there's going to be some additional arguments. Follow the lab instructions and make sure that you're copying the command out of the commands.txt file, which is on your student desktop. When you run this command, it's going to initialize your control plane VM on the node where you ran it at, which is our SA Master 01. We're going to have to do some additional commands to get our kubectl so that it would work. We're going to then go ahead here and install the Antria CNI because we need a networking stack in order to get Kubernetes working. Once we're done with that, we're going to go stay on our SA Master 01 and we're going to copy out a kubeadmin join command, which you're copying it. You're going to copy the command from the master is where you're going to get the command, but then you run the command on each of the 2 worker nodes. The lab instructions are pretty clear, so I'm just going to tell you, go slow, methodically through the labs. Let's go ahead and get our cluster set up, because that's the environment we're going to end up using for all of our future labs as we go through class. Alrighty, well, go ahead, enjoy the labs, and I'll see you back in the next module. Hi, and welcome back. Let's go ahead and get started with our next lesson, which is lesson 3, going over the kubectl command line interface, the CLI. This is going to be the primary tool that you're going to use when it comes to interfacing to your Kubernetes cluster. So we want you to go over inside here how to use that command line interface, and we are going to review the common kubectl or kubectl commands. So throughout the rest of the class, I'm going to pronounce this command kubectl as kubectl. You'll find there's a very high percentage of people that also refer to it as kubectl. My preference is kubectl. You can make your own determination on how you want to pronounce it. So first of all, this tool is going to be talking to our API server that's running on our control plane node. So when you are trying to make calls to it, what the kubectl CLI does, based upon a command that you type, is it's going to convert that command into the appropriate API calls and call the API server, which will in turn take the API call that's coming in and respond back with a JSON formatted output, which the CLI will then take that JSON formatted output and reformat it into something we could read on our terminal. So this particular REST API call that you're seeing here is actually the result of somebody typing in kubectl get pods. You type that in on the CLI, what's happening behind the scenes is the command line interface is going to extrapolate that out into the appropriate API call. This is the API call he's actually making to the API server. The API server in turn is going to respond back with a series of with a JSON payload that's going to represent the pods that it's running. And then the CLI is going to take that JSON file and reformat it into something we could read on our terminal versus trying to read JSON gobbledygook. This is an example of what just happened. So when you typed in kubectl get pods, this happened behind the scenes by the CLI. The API server again responded with the JSON formatted of the representation of this data. The CLI took that and reformatted it for us so that it would be easy to read for us onto the screen. Now, as you start to use the kubectl CLI, you want to start paying attention to some of the output that's coming back to you. I think it's obvious to understand what the name is. But now there's this ready column. What does that mean? Equal numbers, good. Unequal numbers, bad. So in this particular case, I've got a pod that's supposed to be running one container, and it is running one container. So 1 and 1, good. It could be 2 and 2, 3 and 3, 4 and 4. As long as the numbers are equal, everything's cool. What's the status of my pod? It's running. Did it have anything, any restarts on it? Anything greater than 0, bad. That's telling you something in the container, a process, you're having, a runtime error, something's bending. And then Kubernetes is looking at that going, hey, that pod container are supposed to be running. And what does he do? he restarts the pod. So if you're starting to see some count up here, 171 restarts, you got something wrong. Something's not behaving well, and we would want to investigate that. We'll talk more about troubleshooting later. How old is the pod? How long has it been running? Okay, so a lot of good information when we get our output back from the kubectl command. Now, the kubectl CLI, just because you have it, doesn't mean you're going to be able to talk to the API server. You're going to have to be authenticated. And then there's going to be a whole aspect of role-based access control that's going to determine what you can and can't do. We're going to talk about the authentication and the RBAC in a later module called security. So we'll talk about that a little bit later. However, a point that we do want to address here is if this side over here is my API server, if this is my API server, and I'm over here on my laptop and I'm running my kubectl command that was installed on my laptop because the kubectl CLI is available for the appropriate OS that I'm running, these two now we want to talk to each other. But a piece you need to be aware of is they're two different systems, which means they could be two different versions. If my API server, my Kubernetes cluster, let's say is running 1.20.1, and I installed the kubectl CLI and I installed it a while back, and let's say I'm running 1.19.6. Now, guys, I'm not positive of the lowest number there, but the first two, major 1 and minor 20 and 19, are valid. I'm not sure on the individual patched version, which would be the third digit. That's not the important point. The important point is I've got one side, my workstation side, running 1.19, and the server's running 1.20. Okay. Will that work? Yes. But, there's always a but, if there was some new feature in 1.20 that came available, and I'm running 1.19, my kubectl CLI doesn't understand those new objects, arguments, or whatever. So if I wanted to use something that came after the version I'm running, 1.19.6, up on my Kubernetes cluster, I would have to upgrade this to match my version here. So that's what we're talking about here. It must be compatible with the API service version you're using up on your API server. Typically, it's okay to be running a later version on the client and an older version on the API server. Just know anything that's beyond what the server has will not be able to be implemented when it comes to features that Kubernetes provides. Now, the general syntax that you're going to end up using when you do a kubectl command is you're going to be the second argument that you're putting here is typically going to be some type of a verb. So my typical verbs would be things like apply, get, describe, delete. Real simple, common ones that you'll end up using. Then you're going to need to include some additional arguments. So over here would be my additional arguments. In the apply, I'm doing a toggle of -f, which says I'm going to supply a file to you, and then I could specify the full path to my file, or if it's already in my current subdirectory, I can just specify the file name. If I was doing a get command, it's going to ask me, well, what object type do you want me to get? Get pods. I could just do a plural get pods and it would give me a listing of all my pods. If I'm interested in a specific pod, I can do a kubectl pod, get pod, and my pod name, and it would give me details about that pod. You can see inside here, we're taking a look at the kubectl describe command. So I could do a describe, what object type do I want? Third argument. and then that object name in my fourth argument. And you can see there are two different commands there. One's a describe, one's a destructive delete, right? I'm going to delete the pod. And all the commands are going to follow that general syntax. If you simply just did a kubectl -- help, he's going to give you, all the possible commands you could use at that point. Things like, I want to run something, create something, I want to get something, delete it, I want to auto scale it, I want to coordinate, I want to drain it. We're going to cover up the majority of the commands I'm highlighting here in the lessons to come up. Page 2, I want to describe stuff. I want to get logs on something. I want to go ahead and apply something. I want to patch something. I want to go ahead and annotate something. I want to go ahead and look at my version. Okay? All of these are various commands that you're going to end up using when you're using the kubectl CLI. We're not going to be able to cover all of them. We're going to cover just the basics, give you an idea how to get started. Remember, the goal of this class is not to take you from a beginner all the way up to an expert. Our goal is we want to get you to be a solid intermediate so that you would be able to continue your Kubernetes journey at the end of this class and continue and hopefully get your certified Kubernetes administrator certification. So here's some typical examples. Very common one, kubectl get nodes. So what is it going to come back and tell me? It's going to tell me a listing of my nodes. Are my nodes ready? What all does my Kubernetes cluster think it has? Does it think it has one worker, two workers, and are they ready? Also, I want you to look inside the example command here. You see the -o wide additional argument you could have. You could choose to use that, and what it's going to do is it's going to basically just add more columns to whatever your command is. So if I did a kubectl get pods -o wide, again, it's just going to add more columns with more additional information. So that's a very common additional set of parameters to add behind a kubectl command. You could see here I'm adding another argument. I'm using a -- all namespaces. So we're going to talk about what namespaces are coming up in a few more slides. So here's a kubectl get pods. If I include it with -- all namespaces, what I've got is I've got another column at the beginning saying which namespace this pod is running in. Notice our output. My ready column, you notice you're seeing some with 2 of 2. Again, as long as the numbers are equal, it's good. Status is running, good. 0 restarts, good, right? These pods all, on first blush, look like they're healthy. So we've been going at this for a little bit now. Why don't we go ahead and take a short break here? And when we come back, we'll investigate some more what namespaces are and how you would end up using them with your kubectl commands. So again, stand up, take a break, and I'll see you when you come back for the next section. Hi, and welcome back. Let's go ahead and pick up where we left off at before the break. Where we left off at was talking about namespaces and using kubectl commands that would allow us to navigate through various namespaces. So what I'd like to do again is go over again what is a namespace and how are they used inside Kubernetes. So let's say this red box here represents my Kubernetes cluster. Now, we know that the cluster is made up of several VMs inside of it, right? We've got our control plane VMs and we've got our worker nodes. Now, inside the cluster is where we're going to run our pods at. However, Kubernetes has another construct that you need to be aware of, and this construct is called a namespace. kind of a little bit like networking. If I wanted applications from a networking perspective to be separated from each other, in the networking world, I would create and use this object in networking called a VLAN. Inside vSphere, if I created a vSphere cluster and I wanted several people to work inside of my vSphere cluster, I would create these things called resource pools. And in that resource pool, I could allocate a finite amount of CPU in RAM. And then in turn, I could give certain people access to that resource pool. And they could do what they want with the resources that I've given them. In Kubernetes, we've got a similar construct, and it's this thing called a namespace. So when I create a Kubernetes cluster, there's going to be a series of namespaces that are going to automatically be created. Okay, they come as part of the default setup. One of them that we're going to see is one called default. Okay, there's going to be another one that's called kube system. And depending on whose platform you're using to create your Kubernetes, there could be more and several different ones. Some of them have unique ones that they're using on their respective implementation of Kubernetes. Now, anything we run or we define inside Kubernetes is going to be in a particular namespace. So if I'm running a pod, right? If I'm going to run a pod, my pod is actually running in a particular namespace. If I said I wanted to create a config map, okay, the config map again would be created in a particular namespace. As we start creating our Kubernetes clusters and start putting people to work to be able to do stuff in Kubernetes, a developer, for example, developer needs access. Maybe I'll create a namespace for the developer and say, hey, Mark, here's your namespace. You could do work in your namespace. So it'd be my little isolated world. You wouldn't normally create a Kubernetes cluster for each developer. You instead would create one Kubernetes cluster and group together a series of developers to work on that particular cluster. Maybe they're working on a common project. So how do you get a listing of your available namespaces? Command to be familiar with is kubectl get namespaces. That's going to show me all the namespaces that I'm authorized to see. Now, if I have access to several namespaces, right? Let's say I have another namespace up here, and this particular namespace is called test2. And let's say they've given me access to both the test2 namespace and the mark namespace. How do I define where I'm trying to create something at? Well, you could typically, behind most Kubernetes commands, include the -- namespace equals and the name of the namespace where I'm trying to send that command to or create something or delete something out of by just using -- namespace. If I want to set my default context, so any commands I do, and I don't have to include the -- namespace command, I would use this command, kubectl config set context to whatever the current context is. That's identifying, and we'll talk more about it, the actual Kubernetes cluster and my username. But then I would say -- namespace equals, and I would specify the namespace that I want to set as my default as of right now. Now, any command that I type in, let's say I did a kubectl get events, I'm actually doing the events that have occurred in the namespace that as my current context. Kubectl get events is an interesting command. Okay, it's going to tell me from the cluster perspective wise events that have been occurring. Maybe, for example, a node got a particular worker node had failed because of an ESX host failure, and suddenly the node's coming back online. I would see a series of commands coming, or a series of events coming through here saying, listen, this node is now back online. It is ready. What is its status? As the node's booting up, you would see the various components of a worker node, for example, coming back online. If somebody did some command against your Kubernetes clusters and it caused Kubernetes for some of those controller loops, various things to do something, those respective events would appear in this event log. Now, it's important to know that events by default are only stored for an hour. So when we're setting up a Kubernetes cluster, there's going to be some logging that we want to make sure that we're aware of. And that logging would be is say, okay, listen, not only do I want logs of my pods, but maybe I want an audit log. I want those audit logs tracked to know who did what on the cluster. Maybe I'm going to want to grab the event logs so I could things that Kubernetes had fired off internally inside itself, or things that it felt happened to its cluster. We'll talk more about logging when we do module 8, I believe. Here's another common kubectl command, right? Kubectl get pods -o wide. Remember, the -o wide is simply coming inside here and adding in some additional columns. Okay, when you do the -o wide, it's just basically saying include additional columns. So again, it's good to review. Ready, numbers equal each other, good. Not equal, bad. Status running, again, that's good. 0 restarts, that's good. How old is this pod? How long has it been around for? What is the pod's IP address comes when we include the -o. And then over here, which node is it running on? Is it running on my worker node 1, my worker node 2, whatever you called the nodes? The A portion of the FQDN, or the host name, is what would appear underneath the node column. If I wanted more information about a particular pod, so if I'm seeing inside here, okay, I got a listing of my pods. And guys, we're going to play a little bit around in this lab that's going to be coming up in a few minutes. So we want you to be able to feel comfortable doing some of these commands. This is how you're going to be able to troubleshoot things by these commands. So it's imperative that you understand how to construct the proper command syntax. When I came in and I did a kubectl get pods, I got the names of all my pods that are currently running in the namespace that is my default at this time. Maybe I see some pod over here is in, some error condition. Okay, it's in some error condition. So, I'm 0 of 1, not 1 of 1. How do I find out, well, what's going on with that pod? How do I know? Well, what you would do is you would do a kubectl describe. I want to describe a pod, and then I would put in that pod's name. That's going to give me more details about the pod. So I could see the namespace that it's in, the node that it's running on, when we attempted to start it, what is its labels, what is its status, what is the pod's IP address. How did the pod actually come into existence? We'll talk about what replica sets are and that stuff in the next module. This is the second part of it, the same command, but it's just scrolling down a little bit further. What is the image that was pulled? What is the container ID as it's running inside my Kubernetes environment? And then we've got an image ID as well that's going on in here with a signature attached to it. And then we've got a series of events down here, what's happening. If my pod, for some reason, couldn't come online, what you would typically see down inside here is you would see some type of error condition, and it's going to lift out some explanation. Can't find the image, can't connect this. Whatever the problem is, this is how you would identify what the problem is, by doing the kubectl describe pod and the pod name. Now, how do we actually create an object using kubectl? Well, if we go back to the very beginning, one of the things when we talked about the Kubernetes platform, we talked about the two different the environmental controls styles. The one over on our left side was the whole imperative, right? I got to move the dials up and down to do what I want. I'm the brains that say make it hotter, made it cooler, etc. Versus the declarative approach was over on the right-hand side, where we just set what we want and we let Kubernetes do the rest for us. Well, the kubectl command also has both declarative ways to achieve a goal and imperative ways to achieve a goal. The imperative approach over here, you normally should not be using. Okay, you're violating a lot of rules if you're doing stuff with like kubectl create, replace, edit, patch. If you run one of these commands, you're making some change to your Kubernetes cluster, to the workload that's running. How do I know and track and what's my one source of truth? My YAML file that I used up here to deploy something, you're now coming down here and you're changing what I declared in my YAML file. The source of truth should be those YAML files that we're applying to Kubernetes. Those YAML files in turn get posted to the etcd database, and that's what Kubernetes uses to go ahead and say, this is my desired state. Let me get the current state equal to this. If you start running these kubectl imperative commands, creating, replacing, editing, and changing stuff, how do you know what the infrastructure is supposed to look like? So as you could see, the declarative approach is our preferred approach. Now, it doesn't mean that you'll never use these commands. You will at times. Maybe I'm troubleshooting something. I'm debugging something. Let me see if this fixes it. Let me try to find something down. From a troubleshooting perspective, absolutely, you'll probably use them. But in ongoing production, you're probably going to want to avoid using these particular commands. Now, if I'm still troubleshooting a particular container, let's say I've got a pod with a container in it that is starting, it runs for a little bit, and it stops. It crashes for whatever reason. There's another kubectl command called kubectl logs. That will actually fetch for me out of my pod the standard error and standard out logs and display them for me here. Now remember, a pod could have two containers in it. So if this is my pod could have container 1 here. And if it's the only container in the pod, then simply doing a kubectl logs and my pod name would give me the logs for my container. If my pod has multiple containers, then I would have to use the -c command and include my container name so it knows which container logs that you want me to retrieve. So we've talked a lot about troubleshooting. When you deploy a pod using the kubectl apply -f and the YAML that defines your pod, what you're going to see is that pod is going to go through different phases. Okay, so you're going to see that the pod maybe is pending. We're waiting for the pod to actually, for the image to pull down and for it to get started, the container to get started inside the pod. It could be running. This is the most normal state to see your pods in. You can also have a pod in what is called succeeded, okay, or it could be completed. Now, what that means is normally our containers are in a perpetual running state. So if I've got a web server, it's always running. It doesn't start and then stop, because if it stopped and somebody issued a GET request to it, there's nothing there to accept the request and to reply to it. So most of our workload's going to end up being running. However, there is some different types of constructs or jobs that we can look at, and those particular style of components actually get started, they run, and then they finish and they're done. Maybe I want to do cache initialization. Maybe I'm just, going to go check if something's in a directory. If it's in the directory, email somebody and then move it to another directory and then wait until the next time I'm run. Those types of pods could show a status of succeeded or completed. You might see either one of those. That is still okay, and that is normal. The last two down here, failed and unknown, again, that's probably some undesired state, and we would use the commands we just spoke about to go take a peek through those. So with that, what we're going to go ahead and do is we're going to go ahead and explore using our kubectl commands and practice the syntax against our cluster that we created in our previous lab. So we're going to do two things inside here. We're first going to set up auto completion. Because Kubernetes commands are very command line driven, we're going to be able to do partial typing and then just hit the tab key and let it auto-complete for us. So task 2 is going to be setting up auto-completion. So go ahead through and follow those steps and make sure that's working for you. And then the second part of task 2 is we're just going to run a variety of kubectl commands. And as we're going through doing those commands, I'm going to encourage you to practice using the tab or the tab key to watch how it auto-completes. So in that particular one, I might start typing cube, C, and then I'm simply just going to hit the tab key. And it would auto-complete for me the second I hit tab. It will fill in the CTL for me. Then I'll do a space, and then I might say something like GE and hit tab, and it would complete the T for me. And then I'll do a space, P, hit tab, and it will automatically complete for me pods. When it comes time to doing something like getting or describing a particular pod or a node, again, I'm going to start typing cube, C, hit tab, it will fill out kubectl, G, E, hit tab, and it will do the T, space, N-O, hit tab, and it will auto-complete for me nodes, space, and then I don't know what one of my nodes names are. If right here I hit tab, right, a double tab, quick in succession, it will give me a listing down here of my available choices. So if it's able to resolve the name and there's no conflicts, I could just hit a single tab and it will autocomplete. A double tab will give me my choices. So I'm going to ask you to go ahead. Let's play around with those commands in the lab, and then you could join me again and we'll get started in our next module. Thanks. Hi, and welcome back to Kubernetes Fundamentals and Cluster Operations. My name's Mark Allenbaugh, and we're going to start here with Module 4, which is Beyond Kubernetes Basics. So let's go ahead and dig right in. If you're going to be able to run this new cloud-native enterprise application stacks, you're going to need to be able to understand what inside Kubernetes are the building block objects that would be used inside Kubernetes. Once you understand those objects, what are we going to have to do to those objects? Well, we're probably going to have to do updates to them. It's inevitable that we're going to have updates, patches, and services to those objects that we've deployed. Maybe we're going to want to define CPU and memory restrictions on them. What's the minimum they need to be viable? What's the maximum? So how would we go about defining those? We're going to cover some of these pieces that we just spoke about across the next 3 lessons inside this module. The first one that we're going to start with is just going over the basic I would say, core Kubernetes objects that you need to be aware of. Then we're going to jump into a lab. We're going to come back from our lab and we're going to actually talk about deployment management. How would we do upgrades? And then again, we're going to follow that up with the lab. And then we're going to jump into our pod and container configurations and talk about some of those things we spoke about. How can we do resource definitions, maximums and limits, and maybe look at some of the other things we could do to our pods and our container configurations to make them much more functional and useful for us in our Kubernetes clusters. So let's go ahead and get started. Our first lesson is going to be about our Kubernetes objects. So what are the basic Kubernetes objects? And then how would we deploy applications actually using those Kubernetes objects? Here's the basic Kubernetes objects. The first 5 of them are the key ones that you need to be aware of. And then labels are actually things that we do across all of them. Each of them would have their respective labeling key value pair that you would create. Think about some type of data dictionary so you could track what's what and maybe even standardization of those labels. We're going to cover each of these objects in more details. We're going to cover what is a pod. Why do we have these things called replica sets, which actually creates our pods? And then why do we have this thing called deployments, which deployments actually create replica sets, which in turn create our pods? Why are we doing something like that? Once you understand it, it will make perfectly logical sense, and you'll have a good understanding of those first 3 objects. Then we're going to talk about services. That is going to be a necessary component we need to be able to access our applications. So it's going to have something to do with networking. Then we're going to once again talk about namespaces. How would they be used? Give you some examples. And then again, labels is something that we're going to want to come up with some type of standardization that we could do across all of these components. So, first of all, how do we define those objects? Those objects we just spoke about are actually being defined in what we call a manifest file. So the manifest file is where we declare, once again, that key thing, the desired state of our objects. Your manifest files are going to be written in YAML format. So we're going to want to have some type of editor to help us validate and write good YAML. It is very persnickety about syntax, spacing, tabs, etc. We're going to have to come up with the appropriate syntax to actually declare the type of configuration we want of that object. And what are the desired API primitives that are actually involved to do it? And again, this is just a standard construct of one of the manifest files, and we'll give you some examples, and I'll illustrate just maybe some tools you might want to take a look at to help you create these manifest files, if that's your job. Remember, for a lot of us, we're operating the Kubernetes cluster. Now, you could be a developer attending this class, and everything you're learning here is definitely valid, but we're not actually going to create any YAML files. We're giving you the YAML files to use, we'll review them, but we're not actually creating them from scratch. Once I've got my YAML files done, what I then do at this point in time is I would do one of those kubectl commands we spoke about in the earlier lesson, and I would simply apply the manifest file, kubectl apply, -f, and specify my YAML file that is my manifest. And then Kubernetes will take over managing the creation of that requested primitive and the ongoing watching over that desired state and current state are always equal. So the first object, you've already seen this slide before. It is an intentional duplication. We're going to go ahead and talk a little bit about our first object, which is a pod. The pod is the smallest unit of work that Kubernetes can actually execute. It's a pod, which it alludes to there's larger units of works that Kubernetes can also maintain, deploy, and manage. Inside of your pod, you're going to have down here a container. Now, you could have a single container or you could have multiple containers. We're going to give illustrations of both. In this particular manifest, this specification, my pod has a label of app with the value of Nginx. So here's my pod definition. The metadata here, I'm adding a label section, and I'm saying my key is app. That's my label. And then my value is Nginx. This is the information about my container image that I'm telling Kubernetes to run, and I'm telling it it's going to be listening on port 80. When you're looking at a pod/container in that relationship, the pod is created by Kubernetes for one purpose. It's created to run the container. The container represents a component of my application. So the container is the reason the pod exists. Kubernetes will create the pod. The pod gets an IP address from Kubernetes. So Kubernetes knows the range of IP address to give out to pods. It's going to go into its pool, grab an IP address out, assign it to the pod, and then in turn, we went through this a little bit earlier, he invokes the container runtime interface to say, hey, run this container in this pod. Now, could I have multiple containers in a pod? And the answer is yes. Okay, we typically would call this type of thing either closely related containers to this one container, which it looks like that's the main container why it's running. Or they could be some type of thing that we'll talk about later in logging called sidecars. Or actually, we've got some slides coming up talking about a sidecar. Why would you have multiple containers in a pod? So in this particular example, the reason I have multiple containers in a pod is because this container is doing some type of monitoring of the MySQL container. You can see it's connecting here across local hosts. If you have multiple containers in a pod, they're all using the same IP address, so they all got to be on unique port addresses. They could certainly talk to each other. As long as there's not a port conflict, they would talk to each other over the local host. So this monitoring agent that's sitting down here, he could go ahead and monitor this container to see what's going on with it. And then we could see the architecture of this. This container agent is actually sending those monitoring details off to a centralized monitoring system. This is one example of how you could achieve this. There could be better ways to do that. We'll talk about that in more detail when we get to our logging and monitoring section coming up later. I have a third container over here. What is this container doing? It's a logging agent. So as the MySQL container writes logs out to the shared volume, this other container in turn is reading those logs, and what is it doing? It's forwarding them off to some type of centralized logging. Now, how do people actually reach the main container, which is the MySQL container? Again, when the pod's created, it's given an IP address. This particular container is listening on port 3306. So they would simply connect to the IP address on port 3306, and they would be able to then access the MySQL container. The concept of sidecars, I kind of gave you, a hint a little bit earlier about this, right? So maybe inside my one main container, I've got these extra kind of functions that are going on. I've got something that's managing my TLS certificates. I've got something that's maybe feeding metrics, it's monitoring my metrics and feeding them off somewhere. Something that's dealing with maybe my application has some type of retry that has to, loop back around and do again because maybe it couldn't post something or connect to something. Well, what I could do is I could bust that functionality out into its own sidecar container. And then maybe this is application container 1. I could have written another pod down here, right, that had application container 2, and then I could have just reused that sidecar down here to handle the same TLS metrics and retries for that application container. That's typically what sidecars are. There's some specialized functionality, typically in our system, things like logging and monitoring, that I would add to each of my pods to be able to get that functionality out of that pod. Again, this is one way to do it. We're going to have a separate module where we're going to go through looking at logging and monitoring and compare the various different ways we can do that. So this next slide's talking about the pod to worker node relationship. Where do my pods run at? Your pods are actually running on all of these here are worker nodes. These are all my worker nodes. As you can see, a worker node can run multiple pods. This pod is a one-to-one relationship. This one has 2 running in it. This one has 4 running in it. This one has 1 running in it. Okay? A pod will always be contained within a single worker node. Okay? It can't span across multiple worker nodes. It's always going to be in one worker node. Which worker node does the pod actually get scheduled on? We went over that earlier in the architecture. There was a control plane process or service that did that. It was called the scheduler. Scheduler's looking at the load on the worker nodes, and it would say which worker node these pods should be getting scheduled on to run. So, with that, we've been going at this for about 12, 13 minutes or so. Why don't we go ahead, pause here, stand up, stretch your legs, come on back, and we'll continue on going through the Kubernetes basic objects. Thank you, and I'll see you back from break. Hi, and welcome back. So let's pick up on our lesson about our core Kubernetes objects. This next object we're going to talk about is the replica set. And the replica set introduces for us this concept of how and what's going on inside Kubernetes about being able to give us this automation. And in particular, what the replica set does is it allows me to go ahead and declare the number of replicas that I want for a particular specification down here of a pod. So this is how we're able to make our pods scalable and more resilient through redundancy by making multiple copies of them. And it's up to Kubernetes orchestration engine to make sure that those pods that I've declared there are kept running. So that concept of desired state versus current state. So in this particular example, this example right here, we're going to create 2 pods based upon this number here. They're going to have a specific label on each of them. So all of the pods will have this labeling standard applied to them. And down here is the specification for my pod. Same specification, same image we was using before in our pod example. What it would look like is something like this. When somebody did a kubectl apply of that manifest file and sent it into Kubernetes, Kubernetes is going to go ahead and create for us 2 copies of the pod. When he hands it off to the scheduler, The scheduler will normally attempt to keep the two pods away from each other, each of them being on a different worker node. Now, he tries doesn't mean it's guaranteed that they're going to be on different worker nodes. So the replica set is actually pretty cool. It does this great piece for me of being able, with one manifest file, I could have multiple objects. And it kind of sets up this example of a scenario that we're trying to solve. Let's say I've determined a particular website based upon its specification is going to require 20 Nginx servers. So I think we could immediately deduce how many pods would I need to deploy. I would need to deploy 20 of them to be able to do that. Well, one way I could certainly do that is create 20 pod manifest files, simply copying the original pod specification I had, that pod manifest file, over 20 times. Obviously, each would have to have a different file name. I'd have to go into the manifest file and make sure that the name inside the manifest file from my pod was unique. We just learned, wow, I could have instead just used the replica set manifest, did one manifest file, just specified my number of replicas to be equal to 20, and Magic Kubernetes would go ahead and deploy for me the 20 pods. However, there's a key piece that's missing from the replica set, and that is, how is that going to handle doing updates to my code? Currently, my Nginx is running a particular version. I believe it's 1.7.9. Let's say a new version comes out and I need to upgrade my container to use 1.8.1. A replica set by itself is not going to help me roll that out. At least not without having some type of outage. So we need a higher level construct to be able to help us with the being able to roll out new updates in an organized fashion and ideally not have any application outage. That higher abstraction level or objects called the deployment. The deployment is the most commonly used object inside Kubernetes. What he has built into them is an update strategy here. You see this strategy underneath the spec? What that's going to provide for me is the ability to simply update down here my image line, reapply the file, and Kubernetes will automatically go through and create another replica set that's using the new version of code, and will automatically start destroying the old replica set, and that in turn will start decreasing the pods running there. So this degree of automation we're going to cover in the next lesson, where we talk about doing deployment management, which would be how do we roll in new updates. For now, we're going to leave the concept of the rolling update and that update to that lesson a little bit later. We're going to come back and just focus on what does the deployment do. Again, the deployment creates a replica set automatically. The replica set in turn creates the corresponding number of pod specifications automatically. This is what a typical deployment would look like. When I created my deployment, it ultimately ended up, in this case for me, having multiple Nginx pods being created. Indirectly, what we're missing is inside here is we actually had a replica set that got created by the Nginx deployment, and it's the replica set that actually did the work to create the 3 pods for us. So hopefully this is starting to come together for you. We know pods are our unit of work. Unfortunately, we don't create pods directly. Actually, it's fortunate that we don't, because if we did, it would require a lot of manual work on our parts. Instead, we've got this construct called a replica set that will automatically create the pods for me, and I could just specify how many I actually want it to create. However, we need some automation for our replica set. So we have this higher degree of automation, this higher degree of a construct called a deployment, which again is the most commonly used object inside Kubernetes. That in turn will automatically create the replica sets, which are going to create the pods for us. Now, if we pause here for a second and say, great, we've got 3 of these Nginx pods all running here. There's 1, 2, 3. They're pods, which means when they get created on the fly, they're going to get a random IP address assigned to them. How are we going to connect to them? And that leads us to our next section here, which is about services. Services are how pods, if we have a pod-to-pod communication, how pods would discover other pods, and also how potentially external networks can reach into to talk to our pods. So if we think about a typical multi-tier application, we've all seen this a million times. We've got the web tier, we've got the app tier, and we've got the DB tier. And of course, on each tier, we have a series of application modules that are running. Now, this represents some application. This is some application. All of this represents a single application. How would I get people in from the outside to the application? And how would I have the pods or the containers inside the application reach the next level? So in this particular case, let's say I need to have this represents my web tier. How do these guys know where to reach the app tier at? This is where services come into play. So we would define a service here that would represent my app service. We would define another service here that would represent my DB service. And what would happen is the layer above it would reach out and connect to the service, which the service then would get us connectivity to the respective pod. Now, there's different types of services that we can implement. We're going to cover those in a lot more detail when we get to networking, but right now we're going to attempt to introduce some of them for you. The first one that we're showing you here is a service type of load balancer, and this is what the YAML file would look like. Now, how does it know what pods it's supposed to connect to? That's done via this selector key value pair that you're seeing here. So I'm saying it's selecting any pod that has the label app with the value of Nginx. A load balancer is typically going to be done outside of the cluster, and it's going to have an external address that is reachable, and then it will reach inside the cluster and connect to the pods there. You can see what port it's listening on down here and what port it's actually forwarding to. Another kind of service that's available for us is this thing called cluster IP. The cluster IP is typically going to be used inside of your cluster. Now, regardless of what service I'm using, all of the services are going to have this selector section where we would specify how are we selecting the pods that this service is going to load balance our flows through to. That's done via labels that are used to determine the target pods. In this picture that I drew back here, both of these would be my cluster IPs. Both of these internal in my cluster would be of service type cluster IP. You've got the service types of node port, cluster IP and load balancer, as well as we've got a fourth type, which is called an ingress. Now, it's not technically a service, but it resembles a lot of what a load balancer is doing. So in this case, this is what my service would look like. My service up here is such as a load balancer. This could be external to my Kubernetes environment. This could be a physical box that we've integrated with Kubernetes. When somebody defines a load balancer, we actually make API calls over to, let's say, an F5 box and have it actually instantiate a new load balancer and do the load balancing. It could be software running. It could be NSXT, Avi Load Balancer. There's a long list of solutions we could use as a load balancer. So we've been going at this for a bit now. Why don't we go ahead and take a break here? And when we come back, let's go ahead and dig into namespaces, because those are also very important basic objects that we're going to need to understand how they work in our Kubernetes cluster. So get up, stretch your legs, and I'll see you when you come back. Hi, and welcome back. Let's go ahead and pick up where we left off at, which was talking about namespaces. So a namespace is another object inside Kubernetes. And what it does for us is it provides a boundary that we could use inside of Kubernetes. And that boundary, we can do things like specify a specific amount of resources that we want. For example, how many pods, how many deployments, how many replica sets, how many services can be deployed in that namespace. We could set up authorization on the namespace, who can get into it and what they can do inside that respective namespace. Remember, all of the objects that we've talked about up till now, my pods, my replica sets, my services, my deployments, those are actually being deployed into a namespace. We went over the kubectl commands on how we could specify which namespace we're trying to do the deployment of those objects into. Namespaces will span across all of your Kubernetes nodes. Okay, just like a resource pool inside a vSphere cluster, it spans across all of the nodes here. So it could end up that maybe only namespace A is right now using resources on that one node. Namespace C here, as you'll notice, is spanning all the way across all three nodes. B is only spanning across two. That could change. Okay, that can change, and there's ways to do things like tainting and annotations and whatnot that you could do some restrictions on where certain things can and cannot be deployed, but that's a little bit beyond the scope of this class. Your namespaces, again, it's a construct in Kubernetes that we use to divide up the cluster resources, or in a fashion to get multi-user access. So I could have one Kubernetes cluster here. Here's my Kubernetes cluster. And in my Kubernetes cluster, I start creating namespaces, and I can get developer A one namespace, developer B another namespace. I can create another namespace that both developer A and developer B have access to. And then I could set up resource controls on those respective namespaces by capping if I want CPU and RAM, or I can get more granular and say a finite number of deployments, a finite number of services, a finite number of secrets or config maps, whatever objects I want, I can put a cap on those and then cap that namespace so that only that number can be defined inside of that namespace. Now, all of the objects that we've spoken about up till now, we are going to be putting labels on them. Labels are very important inside your Kubernetes environment. What you want to do is you want to come up with some standard key value pairs that you're going to be using across maybe within one cluster, vary it on a different cluster, kind of the same but slightly different, or consistent all the way through all of your clusters. Remember, your label selectors is what we're using to specify the pods that we're going to apply a particular service or a replication controller to them, or even a security policy against. So you're going to end up assigning these labels to all of your objects. You can do it during creation, or you can modify or add them at a later time. Now, some general rules about when you go to create your labels. Don't come up with compound labels. You don't want to do that, okay? So don't use a label something like this. He's using one label of app as my key, and my value is blog dash front end. The better way to have done that would have been to create two labels. I would have used app blog and then created another key that I want to use with a set of values tier backend. Trying to select stuff based upon a compound isn't going to work real well. So you want to come up with a good data dictionary of what all your keys are going to be and what possible values each of those keys are going to be. And there is actually a way that you can enable what's called an enforcement of that, okay? You could write your own admission controller to do that, or if you take a look at a solution that VMware offers called Tanzu Mission Control, I could write a label policy that's already kind of a sample's already done. I would just fill out my values and it would push it out and it would basically do that for me. It would enforce that if somebody tries to apply something and it doesn't either have the correct labels or it has the correct labels but doesn't have the correct values in the labels, it will reject that object that they're trying to apply and not allow it to come into the cluster until compliance is reached. They would have to change their manifest file and put the correct values in. So labels are an important piece to try to start laying those out and planning for them and getting them defined. Now, we've kind of seen the whole picture here a little bit. Now, we haven't gone deep in any of the objects yet, but we've seen how do we create a container image. Hopefully, you've all completed Lab 1 because those images you created in Lab 1, we're going to now start to use them in the lab that was going to be coming up in a few more slides. The big workflow that would end up happening with your developers is depicted here. So what happens over on the developer's workstation, they're going to go ahead over here and they're going to build an image from source code and its respective dependencies. What would happen next is they would test their image, obviously locally, make sure that it's working, and then what would they do? They'd end up pushing that container image up to an image registry. They're saying, I need now to test my container and see how it runs on Kubernetes. So over here, the developer's workstation, they're going to run a kubectl command, and they're going to apply the manifest file that they wrote to test out their container. Now, they might need multiple manifest files. They might need a deployment manifest file, a service manifest file. That example is what we're going to do in our lab. Each of our container images that we want to test is going to require a deployment manifest file to deploy it and a service manifest file so that we can do service discovery and locate that pod and connect to it. They would, step 3, go ahead and do their kubectl apply, and then all of this stuff over here that's going on actually happens automatically. It's not a manual step. The manual steps are over here. These are the manual steps where somebody's actually typing something on their keyboard. Step 4, as you could see, is that the scheduler would assign the pod that they applied inside step 3. Now, again, they're probably not going to do a kubectl apply manifest with the pod. They should be writing their deployment manifest spec, applies the deployment creates the replica set, which in turn automatically creates the pod. The pod now needs to be scheduled. The scheduler actually handles that and chooses which worker node it would go on. The kubelet process on the worker node would actually accept that specification coming down, create the pod instance, get an IP address assigned to the pod, and then hand that information off to the container runtime interface, which is probably going to be a container D typically. Container D would reach out over here, pull the container image, go ahead and start the container inside the pod construct that was created for us. So the specific commands that would be happening here on each of the steps, step 1 here to create the image, that's where we've done the docker build command. That created the image, the container image for us. Then what did we do before we pushed it up to our registry? We had to do a docker tag, and then we did a docker push, and those are the commands that would have been used to actually push the image up to the corporate registry. Next, the developer would have written and developed their deployment YAML file or their manifest file. They would have done a kubectl apply, and that would have been the command to have passed it to the API server. API server would have persisted the information to etcd, woke up the scheduler and say, hey, you need to schedule this. Scheduler would go through, find out which of the nodes would it make most sense on. He would have that information communicated from the API server to the kubelet process running on that worker node. That worker node, the kubelet, would then go ahead and create a pod, get an IP address, hand the information over to the container runtime. It would go off, pull the image, go ahead and start it inside the pod sandbox where the container would run. Notice it says here the remaining steps, all of this is happening automatically. All of that's going to happen automatically. Let's go see it happen. Let's go watch it happen. So, our mission that we're going to do on this lab is we're going to take the same Go Web application that you worked on in lab number 1, and we're going to go ahead and deploy it as Kubernetes pods in tests that we can connect to it. So, you've made an image that we're going to use here for our front-end application called Go Web. So, we're going to need in front of it some services to be able to connect to it. We're going to have the same thing going on in our backend over here. We've got our backend application, and we're going to need a service in front of it to be able to connect to it. So we've given you 4 files that you're going to end up doing kubectl apply commands against. But before you do the apply command, first cat out the file and take a look at the deployment manifest file and the service manifest file. After you've reviewed them, go ahead and deploy each of them for the back end and for the front end. And then out here on your student desktop, go ahead and test using your Chrome browser on the desktop to see if you can get into the Go Web application. So enjoy the lab. Here's the basic steps of the lab. Now, once the application is actually running, we're going to go a few steps further. We want you to go ahead and investigate some more kubectl commands that we talked earlier about. So once you get the application deployed and you're able to see it operate, I would suggest you go ahead, try to log in. From there, you can create an account since you don't have one. Simply register yourself with your email address, make up a password, go ahead and log into it, write something on your notepad, save it. You can even log out, log back in. You can see that the data is there. Then what do we want you to do? We want you to go ahead and simulate some issues. So in task 5, what we're going to do is we're actually going to deploy, we're going to kubectl apply a bad deployment manifest file. Watch what happens when you do that. It gives you a great chance to use the kubectl describe command. Go look at what's going on inside of it, maybe even kubectl logs commands. Go take a look and see, do a kubectl get pods? Why isn't my pod running? And you could do some investigation. At the end of it, we're going to clean up the problem after we identify it, and we're going to shoot down to the second part of the troubleshooting, which is troubleshooting a service. So again, what are we going to do is we're going to break something. So we're going to apply a specific file that has some bad information, and you could observe what kind of behavior will that surface up when you're doing your basic kubectl commands. Kubectl get pods, get a service. Why can't I connect to my application? You'll do a series of commands and be able to troubleshoot it. So take your time, enjoy the labs, and when you're done, I'll see you back in our next module where we're going to be talking about our deployment management. So in this lesson, we've talked about the basic Kubernetes objects, and we've talked about deploying applications using those objects. So I'll see you in the next module. Thanks. Hi, and welcome back. Let's go ahead and get started on our next lesson, which is going to be about deployment management. Now, what we've done in our lab before this is you actually went ahead and you did 2 deployments. You deployed one deployment for the Go web app and another deployment for the Go web app MySQL container, which represents our backend. Let's say, for example, that there was a new version of the Go web app that we wanted to release. How would we go about actually doing that? And that's the objectives of this lesson. How would you perform an application update inside Kubernetes? What tools are available to help us do that? So we're going to actually do an update to an application, and you can see how the deployment object is helping us automate that rollout of the new code. So remember, one of the things we said about our deployment object is the deployment object actually results in creating replica sets. So the deployment handles the creation and modification of replica sets automatically. Obviously, those replica sets are going to be deploying pods for us. Now, replica sets that have been created from a deployment, they're going to be owned by the deployment, and you should not manually be editing or changing those replica sets. If you do, you're going to find out the deployment's going to come right behind you and modify it back. So you shouldn't be editing them. Now, when we look at a replica set, if we actually did a kubectl get replica sets, or RS for short, you could see the name of the replica set, and you'll notice over here, what are we seeing? We're seeing all the numbers are equal, so that's good. Desired's 3, current's 3, up to date is 3, available's 3, all good. You'll notice way over on the right, it's telling me what image it's actually running in this replica set. So when we created our deployment, one of the constructs or one of the key value pairs that we could have done inside of our deployment is we could have defined our update strategy. Now, the default update strategy of a deployment is going to be a thing called a rolling update. And we're going to have a slide coming up right behind us that's going to show you how that works. This is good that this is the default. This is probably what everybody's going to say, yes, this is what I want. So what happens when you go to do an update? The deployment will automatically create for us a new replica set. It will go ahead and scale that replica set up in count. So the replica set will start off as replica 0, and then it's going to go to 1 and 2 and etc. until it gets to the desired value that was in our deployment. At the same time, it's going to be scaling down the old replica set to the point to where it gets to be 0. There's another update deployment strategy we could have chosen, which is not the default. We would have had to have manually selected it, called recreate. Most of us are not going to want a recreate deployment. You'll see how it works, but pretty much so you can count on an outage, because what does it do? It removes all the existing pods in the existing replica set, all the way down to 0. Now, I think you can see this, your application's down. Then what does he do? He creates new pods by creating a new replica set. And until that first pod gets online, our application would have been down. So let's walk through an animation that kind of guides you through this process. This first one, this animation, is my rolling update. So in my deployment manifest file, I've specified my image version as Nginx 1.13.1. I've said I wanted 3 replicas, so when my deployment got applied, it automatically created a replica set using that image of 3 pods. Now what happens? Now there's a new version. There's version 1.13.2. So how would I actually go about applying that? I would edit my original deployment manifest file and simply change the values to point to the new image. I would apply that manifest file. What happens next? Kubernetes takes over. Kubernetes will automatically create another replica set. Notice the new version. He will then begin to scale the replica set up. So now I've got 1 pod online. Originally, my replicas only counted for asked for 3, but now suddenly I'm going to have a 4th pod. But it's not going to stay that way for long, because what is he going to do? He'll automatically decrease the original replica set. So now I'm down to 3. And then we just continue going forward this. We create a new one using the 1.13.2, get rid of one of the old ones. Again, create another new one in the new replica set, and then ultimately get rid of the original pod that was running in the original replica set. And a piece we're going to talk about, we leave the replica set in place, the old one. Why? Oops, something went wrong. Now it's very easy for me to roll back to an older version if I see something went awry. Let's talk about the other option for our update strategy. That would be a recreate. This is not our default, and it's good that it's not, because look what's happening here. You could see that I've got my original replica set using Nginx 1.13.1. I've got my 3 pods, and what am I going to do? Well, again, I edit my deployment manifest file. I tell it I want 1.13.2. And now what happens? Well, recreate. we're going to start decreasing the pods in the original replica set. Still haven't created a 113.2. Get this all the way down to 0 pods. You're down. Your app's down. Create a new replica set of 113.2 and start bringing up the new pods now. During that window, you would have experienced an outage. Eventually, this replica set would get up to the number of replicas that was specified inside of our deployment. So, as you can see, there's 2 different choices to do your update strategy. Okay, the rolling update's the default if you don't specify it. If you're not seeing a strategy defined inside the deployment, then it's going to be using a rolling update. This is structurally how they work. Now, in some cases, people are going to ask for, or maybe you're just going to say, listen, I want more control over my update. It's great that it does this all automatically, but how do I know that first new version's actually working? Well, there's 2 other deployment strategies, but it's important that you understand inside here that you're going to have to do some YAML file manipulation. You're going to actually have to come up with 2 deployment manifest files. You're going to have to come up with some changes inside labeling. Same thing's true if we did a blue-green, right? Same thing's true if we do a blue-green style deployment. Now, these 2 styles work in conjunction of what we just spoke about. And you'll see how they work. And it's all about having more control. But with more control means more work on your part. So what's happening between the 2 of them, the difference is, one of them, the canary, we're going to deploy a new container for a subset of traffic. And we'll go through what it looks like and you could see what that's about. And then if everything's good, you could say, make it so, continue the rest. The other one is we deploy all new containers. We figure out how we can test them, and then we flip or switch the traffic to the new containers. So let's dig in with the animation, with the slides and the pictures drawn, so you can see this in your mind of how these are going to work. So here I'm doing a canary strategy. I've got my original Nginx stable deployment here. I've got replicas equal to 3 inside my deployment. I'm right now running the 113.1. Obviously, in front of these pods, I've got some type of service that's front-ending getting to these pods. I'm adding in an additional label, and I'm saying, okay, this track is stable. Now, I want to try the new version. So what do? Well, hold on. It's not as easy as it was before. You're going to have to manually copy this manifest file over, and you're going to create another deployment from it, so you'll actually apply it. When you copy it over, you're going to change your track, you're going to change your number of replicas to 1, and you're going to change your image to point to the new version. So what happens at this point in time? Well, if you look at my current my services selector, my current selector is actually selecting both here and over here, which means this service is going to actually be front-ending workloads to not only my new pod, but also my old pods as well. He's going to be servicing all of them. So here's a way that I could go through and basically sample what does it look like. In this particular scenario, if you do the math, 25% of the traffic will end up going to the new pod. So what's going to happen next? So now that we've tested and we've confirmed that the new version is viable and it is working, what would we do next? Well, again, the canary approach to doing an update is all about giving you more control. So right now, the service is actually spraying the transactions across all 4 pods. If for some reason you wanted to get more detailed and say, hey, listen, I just want to test the new only, you would then, I think you can kind of see where this is going. You'd have to be able to come inside here. You'd modify your track on your production service and let it just select stable. Copy this to another service, right? So I would copy this over to another service, swap the stable out to be canary, and then in turn, accessing my new service, I could just test the single pod. So it gives you more flexibility. Ultimately, at the end, you're going to make some decision to say, you know what, everything's good, let's go forward. So what would we do then? I would go ahead and decrease the replicas in the canary deployment to 0. I would simply now, this is where the previous stuff we talked about, the rolling update and the canary work together, I would simply edit my production deployment manifest file to point to the new one, do a kubectl apply, and let the rolling update actually go through doing what we illustrated to you before. Now, hold with me. We're going to do a couple other, one other approach before we get you into the lab. So I know we're running a little late, but just stick with me. The other approach is to do a blue-green. Now, the blue-green is going to involve the same duplication. You're going to end up copying him down here. And you could come up with a mechanism that I just explained to you about if you want to test these pods to make sure that they are somehow operational first. You could certainly go do that. You notice this selector is just selecting the top pods. So if you wanted to test the new ones down here that are running your 1.13.2, again, just copy this, do your testing. Now what happens? When you're ready, you say, you know what? It's good. Let's go to the new one. It's one simple change. You change the color here out from blue to green. That's flipping the switch. And now all the traffic is coming here. What would I continue with? I would go ahead and change this back to 0. And then I would typically leave this around so that I've got for future updates a mechanism already in place that I could use. And then this guy would go to 1.13.3. So some controls that we can do as you're doing your deployment. You can do a kubectl rollout command, and you could actually pause a deployment that was midstream. And that's what you're going to do in the labs. So you're going to get a chance to play with that. If you did need to roll back, there's 2 ways to do it. As always, we're going to show you both the imperative and the declarative. And I think we already know the warning. We shouldn't be using the imperative. You should be doing it the declarative style. So with that, there's a few parameters that you could add inside your deployment underneath the strategy. You could set values for the progress deadline in second, minimum ready seconds, revision history, or the pause parameters. All of those are going to control aspects of the deployment. Okay, how long would it be before, after a pod's up that it should be ready? Okay, your revision history, we're going to keep 10 old replica sets. Okay, that's how many we're going to keep. If you want to shorten it, set the revision history maybe to 5. And that would mean that we would only keep 5 versions for you to fall back to. So that's going to leave you guys back into doing lab number 5. Lab number 5 is going to involve you doing both performing a rolling update. Make sure you're copying that command out of the commands.txt because it's actually going to be 3 commands that you're going to do. So you're going to actually do a kubectl command, and then we've got an ampersand, bad ampersand, and an ampersand, and then we're going to go ahead and say, do something like sleep for 2 seconds, and then we're going to do another ampersand and another ampersand, and we're going to do another kubectl, and we're actually going to pause our rollout. Now, the reason we've got to stack them all up there is if you try to manually type the commands in one at a time, you won't be able to catch the deployment in mid-flight. So just make sure you're copying the commands out of the commands.txt, and then we're going to let you go ahead and play with the canary. So enjoy the labs, and I will see you back in our next module. Thanks. Hi, and welcome back. Let's go ahead and get started with our next lesson, Lesson 3, which is going to talk about additional configuration settings you could apply to your pod and your containers. Okay, these additional settings are going to make your app a little bit more, let's say, robust, and your cluster a little more reliable. So let's dig into what they are, these settings that you could set. These additional configuration options. The first one we want to talk about is this concept called a probe. There's 2 types of probes. There's a liveness probe, and then there's a readiness probe. Without these, your pod could still come up, your container will still boot up inside the pod. However, once we see that the pod has successfully initialized the container, we've told the image to pull down, we've got the image, and we've gone ahead and we've started it. The second we start that container image, we're going to say the pod is running. Is the pod/container team there really ready to accept traffic? That's what these 2 types of probes are going to provide for me. They'll say, is the container that is running, is it ready to actually take traffic? A probe, once it's defined, is going to either succeed or it's going to fail. It's one or the other. Either the probe works or the probe fails. If the probe fails, then the container would actually get restarted. Now, there is a restart policy, and the default is to always restart a failed container. It is something that can be overridden. The readiness probe is also going to make sure that do you have all of your additional services maybe running that is inside your container? Have you initialized, let's say, the cache you're supposed to initialize? The idea here is, are you really ready to take production traffic? So on a failure, the pod is removed from the service. Remember, we have the service in front of the pods. If you fail a readiness probe, you're going to immediately drop out of the service and not be eligible to take any requests or any traffic. So when you're looking at these 2 types of probes, there's 3 different styles that we have to query your container. We can do an exec, which is going to involve us running a command inside of your container. If whatever you put in your exec script works and returns a return code of 0, then we're going to say that that probe worked. It's successful. You could do a TCP socket. Not a big fan of it. It doesn't necessarily mean that the application is actually up and running, whatever you got going inside of your container. So all it's going to do is check, is the port open and is it accepting connections? The last one, depending on what your application's doing, it could be an HTTP GET. So we can do a GET against a URL string, a URL, and look for an HTTP response. Anything in the 200 or 300 range is going to mean that the probe actually worked. Both of the probes are going to be typically written by the developer. They're going to know what's going on inside the container. This is going to be a hard thing for us to add as a site reliability engineer or a Kubernetes operator to something we don't really understand what's working. So again, this should be something that we're encouraging the developers to write as well. So here's some example use cases. Maybe I want to do cache initialization. How do I know that the caches are really hot and ready to accept traffic? The only way I'm going to really know that is by writing a probe to go against it. Maybe I want to make sure my JVM is actually up and going. One way I could do that is I could do a probe against a URL, or I could run an exec and scrape through, grep through some particular logs looking for some string inside the logs and say, yes, I really am ready right now to start accepting traffic. Let's say I want to do container maintenance. We just went over doing deployments and upgrading our application. If we're upgrading our application, one of the things that's happened is I'm telling your container to shut down. I'm bringing it down because I've replaced it with a new version. Well, when you're doing container maintenance, how do I get this pod while I'm trying to get it to shut down? And there's going to be a term signal that's sent to your container. And then if it doesn't shut down and get out of the way, we're basically going to evict it. We're going to basically kill it. Well, while that's going on, somewhere in that process, you could still be getting traffic sent to you. So a good coding technique would be to have something to handle a term sig coming into the container. And then what would it do is the container can take itself out of service by forcing itself to fail a probe. Okay, so I could fail a probe. I could do something that I know is going to cause the probe to fail, and then in turn continue the rest of my shutdown process to execute more gracefully and make sure I don't have a few transactions trying to hit me as well. So that wraps up the various different styles of probes and some sample use cases on what we can do. They are tunable, so you could go ahead and add any of these 5 additional settings to your probes. Things like, okay, how many successful probes do I have to get a success back on before I consider myself alive? The default's going to be 1. A failure is defaulting to 3. Okay, so that's our default setting, that if the probe fails once, you're not out of service. You're not failing liveness or readiness. Fail a second time, you're still not failing it. Fail a third time, boom, now we consider it failed and we'll take the appropriate action. We can do delaying in seconds before we start probing after it started. We could go ahead and say, how often do we probe it? Our default is we're going to be probing your container every 10 seconds. Whatever we're running the probe against, better reply within a second, because otherwise it's going to be considered a timeout and it would count towards a failure. Okay, so all of these settings are adjustable for us to add to our probe definition as well. So that wraps up the information about the probes. You're going to get a chance to play with it when you go into your lab, which is a few slides away. Let's go ahead and wrap up the other 2 potential configuration options that we would maybe want to add to our containers. That's specifying CPU in memory. Now, there's 2 settings we could specify for both CPU and memory. One is the minimum that I'm going to need to be viable as a container. The other one is basically a limit or a max. Those are the 2 settings we could set. We could set both of them CPU and memory. So CPUs, how do we, what do we call a CPU in the various IaaS systems? As you can see, we've talked about them. In most cases, it's going to be a core. How we specify what percentage of that is by using a value system here of either a 0 point something, so a 0.1 would be 10% of a unit, right? Or I could have specified 100M, which would also specify 10% of a CPU unit, and the unit would be being defined up here. My memory, we're not using instead the 10 base powers that we're normally used to. We're actually using a 2 base system. So just so you're aware, 512 meg does not equal 512 MI. Okay, so it's easier to specify the true proper I suffix style is what you would actually specify. And this is what they would look like. In the specification section of your definition, where you're defining your containers, we're going to add right here a resources section, and we're going to put in our requests. Now, requests is the minimum. There's another one that we do down here, which is limits, and this over here would be my maximums. And that's discussed in the next one. Why are these helpful? Well, the minimum is extremely helpful when it comes to scheduling, which the scheduler is doing for us when we do our deployment. The maximum is going to help us to know who's kind of out of bounds. And if we did have a problem, anybody who's exceeded their maximum, their limit, is going to be the container/pod that we're going to basically terminate and go, listen, I'm running out of resources. This guy's not supposed to be using more than this. He is. That's the pod that's going to ultimately end up getting killed. So the minimum resources is all about scheduling pods efficiently, okay? And they're going to be scheduled only if the sum of the resources requests of the scheduled container is less than the capacity of the node. So your nodes are filling up with CPU and memory getting used out of them by pods getting deployed to run on them. If we have another pod that we want to get scheduled and there's not enough leftover resource, the scheduler is just basically going to say that worker node can't take that pod, skip it and go to the next one. And then if all your worker nodes are in that situation, the pod would ultimately not get scheduled. Versus if you didn't do it, it would ultimately get scheduled, but it's not going to really even be viable. It's not going to be something that can actually run because we can't guarantee it a minimum CPU and a minimum amount of memory. Max, again, is all about which one might be terminated if it exceeds this limit. So both of those would also be good additional options to get added, configuration options to get added to your container specifications. And again, the best person to probably put these in is going to be the developer. So with that, it leaves us a chance to play with both of those different sections. The probes, the configurations of probes, and then the configuration options for us to do our resource requests. You're going to end up inside here when you're going through doing the lab. You're going to end up doing something like creating replicas equals 10. And you're going to watch your worker nodes get filled up. Then we're going to switch this to 20, and we're going to see that our worker nodes they don't have enough capacity to have the pods scheduled on them. And it's going to involve doing some kubectl commands so you can actually see how the resources have been consumed. How would you see what resources you have left? Go ahead and try to scale it. Realize you can't scale it. Go do some investigation, and then ultimately we'll clean it up, but it will give you good exposure on what that's going to look like in your Kubernetes cluster. Then down here, the third part we're going to do is we're going to go ahead and show you some probes, and we're actually going to simulate a probe failure. Okay, so we're going to give you some kubectl commands that you could use to actually simulate the failure inside the probe. So enjoy the lab, and I will see you in the next module. Bye. Hi, and welcome back to Kubernetes Fundamentals and Cluster Operations. My name's Mark Allenbaugh, and we're going to go ahead and start Module 5, which is about Kubernetes networking. Now remember, one of the things when you install Kubernetes from the open source mechanism, that you're actually not going to get a working Kubernetes cluster until you add to that Kubernetes cluster some Kubernetes networking based solution. We're going to go over some popular choices for you. When we're looking at doing networking inside Kubernetes, we want to know how the various Kubernetes components communicate with each other and how do applications, so a pod to a pod, actually talk to each other. So you're going to have an understanding of how Kubernetes works, or how networking works inside Kubernetes, as well as external out on the physical network to get into a Kubernetes cluster to actually reach your containerized workload. So our goal is to describe how networking works between the various Kubernetes components. And then we're going to briefly recap, not an exhaustive list, but we want to show you how your CNI interface provider is going to affect what the implementation looks like of the various Kubernetes networking components that you can use. So we're going to go over the services, cluster IP, node IP, load balancer, and an ingress controller. We talked about those in the previous modules, so we're going to dig into that a little bit deeper. As well as we're going to start here with what are your choices for a CNI? So as I said to you, if you install Kubernetes open source and once you're done and you do your kubectl get nodes, you're going to suddenly see that nothing's ready. The next step you have to do, and we did this in Lab 2, is you need to install a networking solution. In our lab environment, we chose to implement Antria, and we'll go over the details a little bit about Antria coming up. These are some of the popular solutions that you can use. Okay, so Flannel Calico, that team Calico, very popular inside Kubernetes. If you're studying for your CKA, I would suggest you implement Calico and get an idea of how it works. WeaveNet, KubeNet, and then I've listed here the common choices that you would use if you were going to use one of our Tanzu offerings. So certainly, several of our Tanzu solutions feature NSXT. However, NSXT, as you know, costs money. So as a cost alternative, most of our Tanzu solutions allow you to choose Antria. They also, several of them, allow you to choose Calico. When it comes to load balancing, again, depending on what mixture you're doing, you could use the Avi load balancer. So that's now called the NSX Advanced Load Balancer. You could choose Contour maybe for your ingress controller. All of these are choices that you get to choose. Now, the underlying Kubernetes components don't care what solution you use for a CNI. Not their problem. So we're going to cover what those networking objects are, what are they used for, and give you an idea of what the flow looks like between the various components. Now, a little bit about Antria. And one of the things I would kind of comment to you when you're looking at Calico versus Antria, which a lot of times, since both of those are, a zero cost option, you're going to come down to that solution. The biggest thing I could tell you is, first of all, Antria is new. It was designed specifically for Kubernetes full stop. It's going to behave like Kubernetes, so it's going to have the Kubernetes controller architecture. It's going to implement the extensibility for the via custom resource definitions that we need. So it's very Kubernetes-like. It's newer. It has better performance, better portability, operations, flexibility, and extensibility. So there's plugins and various tools that you can use for Antria and that respective tool to give you better visibility inside Antria. So extensibility was built into Antria from its design, from its get-go. Calico has been around for a much longer time. Okay, it was doing networking before there even was a thought of an Antria project. However, Calico is not just for Kubernetes. So when you start getting into how Calico works, there's going to be a few like, well, that seems to be taking me around the block to get next door type of things. Again, remember, Calico is not just for Kubernetes. So a little, background on those two. I would encourage you to look at Antria. That's the one that we're using in our class. So if you want to explore some more options, you can. There's a note down at the bottom of the page on where you can get more details about it at antria.io. So let's get focused more on our networking with inside our Kubernetes cluster. Again, regardless of what you've chosen for a CNI, you still have networking pieces inside Kubernetes, and it's all going to end up kind of flowing the same way. There'll be some different subtleties. I'll talk to you about them when we get there. Right now, let's talk about if we had a pod. If I had a pod, obviously, once I have a pod, my pod gets an IP address, let's say IP2. Inside the pod, I have a container. Could I have multiple containers? Absolutely. Can my containers talk to each other? Yes. They're going to be using localhost, and make sure that because they're a common port space, you got to make sure that none of the containers are using the same port. Not a problem. My containers within the pod can talk to each other. Again, it's going to mimic like having multiple processes running in a VM. Good enough. Let's say I had a pod to a pod that needed to talk to each other. Now, this is where we start getting into some of the subtleties and the difference between CNIs. When you deploy a new pod, if you'll notice at this first layer up here, you notice the top three, the third IP address, octet, is the same. So how does that particular CNI end up doling out IP addresses? Is it unique per, is the range the same on all nodes? Is it different per namespace? This is a little bit where some of the subtleties when you're looking at networking come into play. So again, the point that we're mostly focused on here is not so much what IP address it was given, is the fact that all the pods can talk to each other. You'll notice the third octet is 1 here, the third octet here is 2, and the third octet is 3 here. Is there somehow some type of routing involved for them to get to each other? Are they using a /16 for a net mask and just, it's one big broadcast domain? From a Kubernetes perspective, all I care about is pods can reach other pods without NATing. So this IP address that a pod is given is routable anywhere within the cluster. Now, it doesn't necessarily mean it has to route. You might be, again, if you're on the same broadcast domain, then you're layer 2 adjacent. So depending on which solution you use, am I routing or am I just a larger broadcast domain? As I say here, the implementation of connectivity is not our problem in Kubernetes. It's the problem of the CNI. The CNI's got a guarantee to be validated in Kubernetes that as it gives out IP addresses to pods, that those pods are going to be able to talk to each other, and it's up to the CNI on how it implements that. what would happen if you looked at this picture here, for example? I've got, 3 pods here. I've got 3 here, and I've got 3 here, again, using the third octet as a way of distinguishing, the different ones in different tiers, let's say. What would happen if this pod needed to reach this other pod? But wait a second, let's say all 3 of those pods are running the exact same service. I've got 3 of them up. Why? Because I want a degree of high availability, right? High availability, so if one fails, the other ones can take over. And I want them also for more throughput. So 3 can do the work more efficiently than just 1. How would I get, if I had a multi-tier application through the stack? Okay, how would I do that? You're going to need to use a Kubernetes feature called services. And a service inside Kubernetes is a layer 4 load balancer for a group of pods. So the typical multi-tier application, we talk quite a bit about is the web app and DB tier. So here's the usual multi-tier application scenario. If up here I had 3 pods that were representing my web service, right? They're representing my web service. A transaction's going to come in from the outside somehow. So this transaction somehow going to come in and get to my web tier. My web tier now needs to reach down to my app tier, where again, I have 3 pods running for high availability and more throughput. And then down here at the DB tier, I have the same thing. How do we get this connectivity working? Well, Kubernetes provides for me this services construct that I could use. So a service, again, is a Kubernetes resource. And what does it do is it load balances to a group of pods. So in this case, my app tier would be my group of pods. My DB tier would be the group of pods that I want to load balance to. So how we actually get from one tier to the next tier to get connectivity is we're going to use one of these services. Now, the most common one I'm going to tell you in this case that we're going to use over here is going to be cluster IP. So we actually end up creating up here a service. And when this app pod wants to reach the next tier down, it calls out to the service for the app tier. How it locates that service is using internal DNS, which we're going to talk about in about 5 or 6 more slides. Then it's the app, then in this case, it's the app service that's going to distribute the traffic to the pods that it's selecting. And then when those pods need to reach down here to the DB tier, again, they're going to reach a service, and the service would fan out the transaction to the respective pods that are running inside that DB tier. So the cluster IP would be the one that we would be using here. Now we're going to cover all 3 of these coming up in the slides ahead of us. But for now, why don't we go ahead and take a short break, get up, stretch your legs, get some fresh coffee, and I'll see you back when you come back from your break. Thanks. Hi, and welcome back from the break. So before we went to our break, we had just introduced the concept of services, which we would use to be able to communicate to our pods. And there's 3 different types of services that we're going to be going over. We've got the cluster IP, we've got the node port, and we've got the load balancer. And they do behave slightly differently, so we're going to walk through each of them in a little bit more detail. So first, one thing that we've got to understand is, why do we need these services? Well, if you look in the center here, pods are ephemeral by design. If a pod fails as part of a deployment or a replica set, it's going to get replaced, and those new pods, when they come up, are going to be getting new IP addresses. We've got the ability to scale up new pods by increasing our number of replicas, and we got the ability to scale them down. So what the service does, it acts as a front-end object for us to be able to reach some of the pods behind it. And the services, again, are going to be selecting the pods that it's sending the traffic to based upon that selector criteria inside the manifest file where we define our service. Now, this particular example on this slide is a node port service that we're trying to illustrate to you. A node port, the port number that's used here, is going to be randomly generated in the 30,000 range of port numbers. If I can access the worker node and then put the node port number right behind it here, from the outside, that would actually get me through to one of the pods that are behind the service. In this particular case, he's going to forward the traffic through to one of the pods on port number 9443. So these service objects, again, they are Kubernetes primitives. They're defined in a manifest file, and you're defining what you want. You're going to give your service a name. We're going to talk about how the DNS looks, and we're going to do that as part of our lab that's coming up. We're going to be defining the protocol that we want it to forward the traffic through to, and which port number we're going to actually forward the traffic through to. Here's an example of cluster IP. Okay, so again, a cluster IP is something that you're primarily using for internal facing services. So if I've got some pods that need to go from the example I showed you earlier where we had the web tier, the app tier, and the DB tier. Once I get internal, which would be my web service, from my web service to reach down to my app service, it's actually going to be connecting to a cluster IP service. The cluster IP address is something that is generated on your Kubernetes cluster. Our particular cluster that we defined here, we said that our services range would be in the 1096 / I think it was 16 range, that we were saying use any one of those IP addresses. So this IP address is actually attached to my cluster IP. So this feels a little bit more like a load balancer, except for it's using internal IP addresses that are only reachable typically inside your Kubernetes cluster. So when one of these pods reaches out to this service, which it would do a DNS lookup, get an IP address, send the traffic through to the cluster IP, and then from there, the cluster IP would load balance it to one of the pods that is defined via labels inside of its selector. As I said, this is not designed for external access. Okay, this is only once you get inside the Kubernetes cluster that we're going to have a pod reaching out to a cluster IP service, which in turn would load balance the traffic to the pod beneath it. Node port, as we had kind of gone through already, this could be used for external facing services. There's a few caveats. One, you have to be able to connect to the worker node's IP address. So the node port is something that's defined in this 30,000 range of port numbers, and it's attached to all of the worker nodes. So all of the worker nodes are consistently using the same node port to bring traffic in, and then the node port actually forwards the traffic to a cluster IP address, which it does just what we went over, forwards it over to the respective pods. Now, why is node port typically not used? Why it's typically not used is Most companies aren't going to allow destination traffic out on port like 30,000. And a lot of companies aren't going to let that into their cluster, that 30,000 range. So typically I'm going to tell you node port is mostly just used in testing. Before, while they're testing their application, they'll typically test with a node port. And that's what we did in our lab example. So that's what the scoop is on the node port. For really external access, you're typically going to end up using a load balancer, or potentially you're using ingress, which we're going to be talking about next. So a load balancer is a choice. What kind of load balancer is a choice you have to choose when you're talking about what is going to be your CNI. Now, in some cases, some load balancers work independent of the CNI. Some CNI implementations might include a load balancer. So you got to really dig a little bit into the details. Our VMware solutions, where we use, some of our Tanzu branded solutions, when they're able to integrate with NSXT, those solutions then can use the load balancer inside NSXT. If we're not using NSXT, then several of our products, you could use the Avi load balancer standalone, and the license that we're including, for example, for TKG, you could use the Avi load balancer to be your load balancer. And then there's a variety of other ones. Some customers might choose to use an F5 load balancer because they're an F5 shop, or maybe somebody will say, listen, we're Nginx, we want to use Nginx. This could get a little bit up to personal preferences. The beauty of it, from a Kubernetes standpoint, it doesn't matter. It's always going to behave the same way. So what a load balancer is doing externally is it's going to go to the CIDR range that you've told your load balancing software to use. It's going to grab another IP address, right? So it's going to grab another IP address. That IP address is how the load balancer is reached externally. Then from there, the load balancer, and I'm just going to kind of dot the traffic through here, will get eventually somehow to the corresponding pod behind it that it's trying to send the traffic to. This is going to be very much so dependent and different based upon whose load balancer you're implementing. So for example, the NSXT load balancer, if you use that load balancer, he doesn't mess around with this node port and cluster IP. The load balancer goes straight down to the pod. It doesn't go through a node port and then through a cluster IP. It just goes straight to the pod with NSXT, since NSXT is running the segments, has the T1s, has the T0s, the edge nodes. It will be able to connect directly through it. You're basically done. Other implementations, well, they might actually, when you define the load balancer, it will auto-create the stuff it needs behind it to make it work. It will auto-create a new node port, and when the node port gets created, it auto-creates the cluster IP. So it's kind of weird when you're seeing out here when someone is saying, hey, I need to reach this particular application. When they come through, they actually go through the load balancer, which hands it off to a node port, which hands it off to a cluster IP, which hands it off to the pod. Okay, that's a lot of hopping through some things. But again, each implementation will be different. It's something you need to, evaluate when you're selecting your load balancer. The beauty again is, when I define I want a load balancer inside Kubernetes, when I define I want a load balancer, I don't have to worry about how is it being implemented. Me as an operator, I might want to know how it's being implemented, because if something's wrong and I've got to troubleshoot it, I'd like to know what all is it going through. So this is what it would look like at the end. Now, again, typically your pods run on a network that's usually not reachable, not routable from the external world. So what would happen if we want to provide external access into pods, you're going to have to use some type of service up here to be able to reach it. The typical service we would use for external is going to be the load balancer. And you could see with the selector right here, I'm selecting app, cars app. So all of these have a label that says app, car apps on them. Their pod IP address was randomly assigned via Kubernetes. That IP address is ephemeral. It can be constantly changing. If I did, remember we did the deployment where we did the update? If I did an update on this, what would happen is I'd spin up another pod, new IP address, and destroy him. He will automatically fall into the selection here. Okay, so my load balancer has a name, and its service name here is cars service. He's selecting the pods down here. He's going to listen on port 80 and target port 80 through to the pods behind him. Now, once you've created your load balancer, if you would do a kubectl get services, right? If I did my get services, I could see here the external IP address that the load balancer was given. I could go ahead over here and I could actually see the node port that this particular service is actually forwarding through to. So it's going to actually forward through. Remember how I said some load balancers go through a node port? There it was. There was the definition of the node port that it actually went through. This is what it would look like. Now, in this particular example, we are using private IP address. You can do that, but then you're going to, if you really want it to be external, you would have to have then manually created some type of NAT to get it through from a publicly advertised to come on in, or your load balancer can actually advertise a public IP address, take the traffic, and then be able to reach down either directly to the pods, or it could reach the node port and have the node port forward it to the cluster IP. Okay, we've been going at this for a while, and before I go into ingress, I'm going to slide back here and we're going to take a break. And again, I want to end with the load balancer. Okay, the load balancer depends on what you've selected. It varies based upon the selected CNI. It could go directly from external to the pod, or it could traverse through the node port and the cluster IP. Remember, all of these services that we're talking about, you're going to be putting in a manifest file and doing a kubectl apply. So with that, why don't we go ahead, take ourselves a break, stretch your legs, and I'll see you back when we come back, and we'll go ahead and explore the ingress. Thanks. Hi, and welcome back from the break. So let's go ahead and explore this final type of service, which is called an ingress. And an ingress is a lot like a load balancer, except for the ingress operates at layer 7, and our load balancer is strictly looking at layer 4, so it's looking for a port to come on in, and then it's load balancing off of that. So it's got an IP and a port that it's listening to, and it sends the traffic through. The ingress, instead, is actually looking at our HTTP headers. And you can look over here to the almost the dead center there where I just circled the URL that the user requested. So they requested foo.bar.com/foo. And then we've got another URL way over on the right where they're requesting the same URL except for it's ending with /bar. So it's the same FQDN. What an ingress is doing is it's looking in layer 7, the HTTP header, and it's actually looking to say, oh, they typed in /foo. If they've typed in /foo, let me send them to the foo service. If they typed in /bar, I'm going to send them to the bar service, and each of these services has their own respective load balanced pods that it's actually going to. The ingress has also additional capabilities, and depending on whose ingress you implement, it could be slightly different. You can do URL rewrites, you can do different distribution algorithms. They can get pretty sophisticated. The ingress, like the load balancer, is something that you would have to choose what you want to choose for your ingress. So when you install open source Kubernetes, one, you don't have a networking stack, so you got to choose your CNI. Next, you don't have a load balancer unless your CNI provides one. You probably might have to choose your own load balancer. You want an ingress? You're going to have to choose your own ingress. Any of our Tanzu products, we steer you down a path to particular ingresses and load balancers. Some cases will give you a couple of choices again, and then in turn you would have support to be able to call VMware support to help getting those respective components working or troubleshooting if you had a problem. So the popular ingress controllers that you would see would be things like Contour. That's what we're actually going to end up playing with a little bit here. We're going to talk about NSXT as an option. The Avi Advanced Load Balancer could be an ingress. However, the ingress for the Avi Load Balancer is not, that's a layer 7, is not a free license. That would be a licensed version of the Avi. You could use Nginx, and then we've got a couple other popular ones listed here, depending on where you're running Kubernetes at, that you could typically run across and see. So when you're looking at an ingress, there's actually two parts of the ingress. There's going to be a thing, what we call the ingress controller, which I'll translate that for you, control plane. And then you're going to have an ingress pod over here, which is my data plane. So the control plane is running over on my control plane or my master nodes. The ingress pod, the thing that's in the data plane, it's the component that's actually taking the TCP flow, and the flow's going through that pod. It's the thing that's opening up layer 7, looking at those HTTP headers, and based upon the rules that we wrote it, shipping the traffic in different paths. Now, an ingress controller and the whole ingress concept would be something you could use for external facing traffic. Again, it's looking at the host headers, looking for path evaluation, externally accessible, and it's configured with an ingress object. This ingress object is my YAML file. It is the file that's specifying the rules. So if you're looking at this particular picture, we're saying if you go to app-a.example.com, you're supposed to come down here to service A. If you did app-b.example.com, we want you to come over here to service B. That gets turned into a set of valid rules by the control plane, the ingress controller, that's reading the YAML file, and then it sends the programming into the ingress pod that's actually running on your worker nodes. So this is what the ingress would look like. So its kind is ingress, and then depending on whose implementation you're using, you typically are going to start seeing these annotation and values appear. You're going to start seeing them appear. This is how we're able to pass certain things into some other component to give it information of what we're looking to have happen. Then over here, this is just a continuation. So guys, this just flows up to here. Okay, but we try to put all the rules together so you could see the rules. This is the whole rules section, and here's the rules I need for my A path. What's the FQDN? What's the host name that they typed in? I don't care about the path. And then what am I going to connect to? A service with the name of service-app-A. The service would still have to be created. You would still create the service just like we talked about, and that would typically be a cluster IP service. Here it is down here for my B side, and you notice he's connecting down here to the service-app-B. So two ways potentially for us to be able to have external traffic come into our Kubernetes cluster. The two most popular ones you're going to see is the load balancer and the ingress. Some companies are just like, yeah, we don't use ingress, we just all use load balancing. Okay, that's fine, they could use all load balancing. Other customers like, no, I really need to use the ingress. Okay, you can use that as well. Node port is technically accessible. The problem is that 30,000 destination port that we're trying to get to, a lot of times enterprise firewalls don't allow it through. So that's typically why you won't use node port. We'll do some testing with it as you go through some of our labs. So with that, we wrap up our services. However, we're not done yet. What do we need to do is, how does a pod reach a service, right? Let's say cluster IP. Well, that's where we get into this thing called service discovery. So as we know, Kubernetes is this declarative API that we use to deploy both applications, services, ingress, and load balancer resources. How does one thing reach another thing? So the services, things like our ingress and our load balancer, they do provide a method to route IP traffic to an application, but an IP address can change as the workloads are created and destroyed. So that's why we want to put those services in front, because we're selecting anything based upon labels. Now, how do we connect a service name to an IP address? Well, service discovery is what solves the problem by allowing the applications to be registered in a service registry. What kind of service registry are we using? Well, we already got something, and it's called DNS that does a pretty good job of it. In Kubernetes, the service registry is what it's referred to as. It can be queried. And what we would need to be able to do is query it based upon our service name, and then we'd get back an IP address, and then the pod that's trying to make the connection would just connect to that IP address. Well, it gets a little bit trickier though. Because our Kubernetes cluster is divided apart into smaller chunks, i.e. namespaces, and anything that we run, when you do a kubectl apply, you're applying something to a particular namespace. If I create a service, the service is defined in whatever my namespace is, that is my current context. So for you to locate a service, if you're within a namespace, so if I'm a pod here, and I know that I want to reach a service called Go Web App, I could simply do an NS lookup to Go Web App, because this pod DNS is pointing to the cluster's internal service discovery DNS system. That DNS system, when my service was created, got registered inside that DNS system. And now when my pod does a simple NS lookup using the short name of the service, because it's in the same namespace, it will resolve. However, if this pod here wanted to look up this service, which is in a different namespace, it has to use the fully qualified DNS name. And we do follow DNS standards. So the example here is showing you what the fully qualified DNS name would be for that service. So it would be the name of the service out here, followed by the namespace, followed by the string SVC, followed by your top-level domain name. Now, our top-level domain name is the default that Kubernetes uses. we could have changed that. So to answer that for you, how you would change that, we've got to go all the way back to lab number 2. If you remember in lab number 2, we did a command that looked something like this. We did a kubeadmin, init, and then we did a dash dash, and we did something like pod dash network dash cider equals, and we put in a cider range here. To change this cluster local name, it's just another dash dash. It would have been a dash dash cluster domain name equals, I think it's something along those lines. If we don't specify it, then we simply get cluster.local. Normally people, a lot of times, I'm going to tell you, they don't connect their corporate DNS to their Kubernetes clusters DNS. They typically leave those two worlds apart. Again, nothing that is trying to look up something inside Kubernetes, if it's outside and it's trying to reach Kubernetes, it can't get to the IP address. So there's no point in doing a DNS lookup against it. They need to be connecting to the load balancer or the ingress. That's what they would need to be connecting to. So this is how the DNS system works, and you're going to get a chance to play with both of them when we get started with this lab. You're first going to go ahead and deploy an ingress controller. So we're going to convert our existing node port over to a cluster IP, and then we're going to create an ingress, which once we've installed it, we'll then be able to go ahead and apply our ingress manifest file and test that we can access our Go web app by simply connecting to one of our worker nodes. So our two worker nodes, .41 and .42, you'll be able to just open up a browser to that worker node. The data plane's already been programmed. It's sitting there. If it sees the proper access coming in, it will go ahead and route you on over to the Go web app. Then we're going to go ahead and we're going to explore the DNS resolution that I just spoke to you about. So you'll get a chance to do that. So go ahead, have fun with the labs, and I'll see you when you come back for our next module. Thanks. Hi, and welcome back to Kubernetes Fundamentals and Cluster Operations. My name's Mark Allenbaugh, and let's go ahead and get started with module number 6, stateful applications. So up till now, we've been using the Go web app. And if you have been actually setting up a user account and logging in and writing something on your notepad, and then you could log out, come back, let's say half an hour later, log back in, your stuff that you wrote and your notepad should still be there. In fact, so should your user account still be there. Well, our application as it's been developed so far, that is partially true, partially not true. If for some reason our backend application, our Go web app -MySQL, if that application, that pod, got terminated and redeployed, your username in your notepads that you have written would actually go away. If you want something to persist through a restart, a pod restart, you have to do something special. And that's what we're going to talk about inside here. How would you manage storage, more specifically, stateful storage for a pod/container? So first we want to review what are the concepts of stateless and stateful. And then we're going to dig into how would you go about as a Kubernetes operator or a site reliability engineer, infrastructure-wise, what would you have to set up to be able to get persistent storage into your Kubernetes cluster? So let's go ahead and dig in. We first want to make sure you understand the default behavior of a pod, which is they're stateless. Their storage persists, or it's around as long as the pod's around. The second the pod goes away, the storage goes away. So that's why we refer to them as stateless. We're going to show you inside this module how you would go about creating persistent volumes. These are Kubernetes constructs, a persistent volume, how you could potentially use storage classes, and then how you would use persistent volume claims to be able to map those components into your pod so that you do have stateful storage. Now, when we're looking at doing storage inside Kubernetes, there's really two different, I would say, roles or personas here that you need to be aware of. One of the roles is the storage administrator. This is somebody more on the infrastructure side. They're not a Kubernetes developer. They're probably not even maybe necessarily involved in the day-to-day running of, the Kubernetes cluster. And then you have the application engineers or the developers. The storage administrators, they're the ones that are going to be involved with getting storage exposed to the Kubernetes cluster. The application engineers are going to be their customers, and they're the ones that are going to be consuming the storage that the storage administrators have provided to the Kubernetes cluster. So there's a few things that you need to be aware of. And those things is how do we get the storage inside Kubernetes? And you're going to see that depending on what kind of storage you have, which there could be, Kubernetes can run on a cloud. So maybe I have elastic block storage, or I've got an S3 bucket, or I've got a particular, in my data center, maybe I'm a big EMC customer and I've got an EMC storage array, or I've got a NetApp or a Hitachi. There's a mechanism inside Kubernetes called the container storage interface, and it's available via a plugin that allows, just like we did with networking, for us to expose the storage, various different types of storage, into Kubernetes so that when it gets to Kubernetes, my application developers aren't worrying about a specific kind of storage, a particular vendor. To them, it all looks the same. So the developers over here are going to be using this pod spec so that they're going to be able to reference how they want to consume storage inside of their pod. As I was saying, the container storage interface, what it does is it provides an API from Kubernetes to the various storage providers. And again, our application engineers or our developers, they really don't care about what kind of storage we're actually running from an infrastructure perspective. So it's the job of the CSI when we're setting up our Kubernetes cluster that we implement a particular CSI into our Kubernetes cluster. And what it does is it's going to then expose your underlying storage system so that we can consume it using Kubernetes constructs. Who writes the CSI plugin? It's going to be your third-party providers. They're the ones, if you're vendor X of a storage array and you have special features you want to expose inside Kubernetes, that storage vendor would be the one writing this particular plugin. Now, if we go back and we take a look at our pod specification, and you can see I've given a pod spec sitting out here, and this would be my pod manifest file. And if I drop down here to the spec section and I look a little bit beneath the spec section, I could see that I'm actually running two containers. I'm running one which is going to be called the Nginx container, and I got another one here called the WW Syncer, okay, sitting over here. There's my two containers. to review for a second, if a pod gets deleted and redeployed, I'll give you an example. We're doing a rollout, a rolling update, because we've got a new version. That would mean that the pod goes away and a new pod gets deployed. The second that instant happens, the storage that was attached to your pod is going to go away. So any work that your pod or your container has done is ephemeral. It's going to go away. The second it's deleted, when it gets recreated, it's going to get a new chunk of storage. So anything that your pod in your container is writing is going to go away. If I want two containers in a pod to be able to see the same chunk of storage, you would have to implement the second half of each of these container specs that you're seeing here. If you look where it says your volume mounts, what this is allowing each of the containers running in the pod to be able to do is both of the containers can see the same chunk of storage. Without doing this, you could have multiple containers running inside of a pod, but they're not necessarily going to be able to read and write to the same chunk of storage inside that pod. This is giving them the ability to have shared access across the containers that are running inside the pod. And in order to do this, we're going to need to introduce a new section inside of our YAML file down here called the volume section. So what does this do? This is going to create a shared area. It's going to be an empty directory, which is effectively a scratch area. And we got to give the volume a name. We call it My Web Content. Then each of the containers up here reference that exact same name. And now both of the containers have access to a common area inside your pod that these two containers can both read and write. On one of the containers, you could see that area is being mounted to this particular directory, and a different one is being mounted to a different path. So each of the containers would have to reference the respective path, but it is the same chunk of storage. This storage is going to hang around until the pod, for whatever the reason is, gets deleted and gets recreated. It all starts again. It's all fresh storage. This has its use case, and it's definitely a valid use case to be able to use this in your application as you're developing it, to be able to have two containers writing to the same chunk of disk. However, the fact that it's scratch data and it's going to go away, maybe is not going to be able to satisfy my requirements for my application. Let's say I'm a database. Okay, when my container goes away, I don't want my database to get destroyed, and then I'm going to start all over with an empty database. Obviously, if I'm persisting transactions out there, that isn't going to work. So what would we need to do to get persistent storage? Well, that's where we're going to explore this in this section here. We're going to explore inside here that, again, to say, when a pod is terminated, all of its data written is going to be lost. So how would I have persistent storage, and how would I get it mapped into my pod? That's where we jump into this concept of persistent storage. And we're just to review the points again. I'm going to probably say when you look at all your workload that's running in a Kubernetes cluster, probably 80%, give or take inside there, is going to be running stateless. Stateless is good, But I can't have everything running stateless. At some point, I'm going to need to persist my data. And in order for me to have a stateful application, it's going to require me to treat it slightly different. And there's going to be some factors that you're going to have to be thinking about when you implement stateful storage. So, as you know, containers out of the box are ephemeral. So if you need data that needs to be persisted and you want it to survive through a restart or a reschedule, you're going to have to do something extra. And as we say inside here, if containers are rescheduled, they cease to exist on one host, and then they might be scheduled on a different host. If it was persistent storage attached to that container, but you're running on two different hosts, where's the storage coming from? And this is where we get into the complexity of persistent storage. That storage would have to be shifted and made available on the new host. We're used to that in vSphere because we've always had shared storage. So that's not a new concept to us. When you hand spin Kubernetes and you set it up, if you're going to just have local storage on physical hosts, and then you're going to plan on top of it putting, the Kubernetes host guest OS on top of it directly, you've now made it very difficult for you to do persistent storage. So the application or the container does not handle the volume and the data. What handles that shifting around is the underlying infrastructure. Realize some containers or some workloads have a strong sense of identity. So the first time they see a chunk of storage, there's going to be some type of disk ID that they're going to take a look at. They'll typically sign it and embed it somewhere inside their data. And then the next time they go to read something out on that disk, they're going to validate that it's the same. And if it's not, it's probably going to balk at it. We're very familiar with that. If you're familiar in vSphere, ever getting a warning message about the data store needs to be re-signed, we understand what that's doing when we're looking at our VMFS volumes. It's pretty much so the same situation here. If you're running a particular application that we've listed a few examples here, Kafka and Elastic, you're going to want to read their respective documentation and understand how they would handle a changing ID and what you would need to do additionally to get those to work. Hi, and welcome back from the break. Let's continue on where we left off at. So we had given you the idea of the concept of stateless versus stateful, and we started explaining about the necessity for certain parts of my containerized workloads that need persistent storage. We're going to have to do something extra, which includes implementing this container storage interface, this CSI, which is going to be the component that's going to abstract away the underlying infrastructure component that is providing my storage. Now, once I've implemented my CSI, how we're going to actually inside Kubernetes consume that storage is by creating these things called persistent volumes. And it's the storage administrator is the one that's actually doing this. The application developers or the application engineers that are assembling the application aren't writing the persistent volumes. That would be probably more our role as a site reliability engineer or a Kubernetes operator. Persistent volumes are just like the volume that I showed you could have used in a multi-container pod type of setup, except their life cycle is independent of the pod. So when you go to create your persistent volumes as the site reliability engineer or a Kubernetes operator, there's two different ways you can do it. You could do it statically or you can do it dynamically. Now, in some cases, you might do it statically. Maybe you've, just doing something real quick. But in most cases, you're going to want to do it dynamically. because it's a lot less work on our part. Statically is going to be a lot of work. We're going to actually, in our case, running on top of vSphere, we would actually end up using a VMKFS tools to actually create a VMDK file. So you could see that could be a little strenuous on us for the amount of work we would have to do. So once we've created our persistent volumes, how do we have then the application engineers or the developers start to use that storage? They're going to end up creating this Kubernetes object called a persistent volume. A PVC is how they consume the storage we have made available to them. Inside their persistent volume claim, they're going to request the specific details of what they want for storage. The size, the access mode, and so on. We'll get into some of those details. What happens inside Kubernetes is when they do the kubectl apply and request a PVC, Kubernetes is actually going to make a query out to find the best persistent volume that would match that particular request. So for example, if I write a PVC that says I want 10 gigabyte of disk, and you've created some PVs with 8 gig, 10's greater than 8, that won't satisfy the request. So he's going to keep going through the list and say, oh, I found one that's 12, 15, 20, 25. He'll use one of the ones that meet the requirements of the PVC. So you could see that the PVCs actually consume the PV resources. Okay, so it's similar to like how a VM is consuming resources of an ESX host, or how a pod is actually consuming CPU and RAM out of my worker node. So if a PVC ends up getting deleted, the data is deleted. So, warning, warning, Will Robinson, danger, danger. If you're going to delete a PVC, that's kind of like, deleting the VMDK file of a VM. You're really getting rid of the data. So the default for us is that if a PVC gets deleted, the data is also deleted off of whatever your storage mechanism is. That can be controlled by a thing called a reclaim policy. Okay, we're not going to go into the details of it, but the reclaim policy default setting is when the PVC gets deleted, the data actually does get deleted. Think about it if it was different. How would you then have to, figure out doing your cleanup? So our default is PVC gets deleted, data is deleted. So storage, some additional persistent storage options we have to configure our storage. There's another Kubernetes construct called storage classes, okay? And a storage class is a way for me to do the equivalent of persistent volumes, but it's more dynamically. So what happens here is, if you're familiar for what we're used to inside vSAN, there's a thing called SPBM, Storage Policy Based Management. And we could find a storage policy, and then when I store something, it uses that respective policy where I can control things like failures to tolerate, do I want it thin provision, do I want to do a reservation, etc. Storage classes are a Kubernetes construct that really is almost the equivalent of a storage policy inside vSphere. Now, everything we've been doing, persistent volumes, persistent volume claims, and storage classes are things that would be assigned at a namespace level. Like everything in Kubernetes, they all are actually being defined within a particular namespace depending on your context. So when you implement the vSphere plugin, the vSphere storage policies will actually be translated for you into Kubernetes storage classes that you could then choose to assign to respective namespaces where you want them used at. Developers are going to be able to see those policies in the form of these storage classes. They can't manage them, but they're going to be able to see them and then in turn be able to consume them. This is what a storage class looks like from a Kubernetes manifest file perspective. And you could see, again, the usual kind API server. We're giving it a particular name. This storage class we're going to call Kubernetes. There is some additional annotations or provisioner keys that need to be added to support your CSI. So you could see this particular provisioner key is what's telling us to use the vSphere volume plugin. And then down beneath here, you could see there's our parameters. So I'm saying my disk format's going to be thin, my failures to tolerate 1. I'm actually declaring for this storage class which data store I want it to go to. And now, one of the things they did here, remember I told you the default, if a PVC gets deleted, the data gets deleted, they're overriding the reclaim policy here, which means as developers say, yeah, I don't need this disk anymore, and they delete their PVCs, your data is actually not being deleted. So the administrator now is going to have a lot more cleanup work they're going to have to deal with. So storage classes are basically a way for us to describe the underlying storage and what features they offer. So the storage class, it needs to have things like the provisioner. That's telling us which CSI plugin to use. The parameters. If you don't specify the reclaim policy, again, it will default to delete. They also, each of these storage classes might map to different quality of service levels. Maybe backups. Maybe I've got a data store, a particular one that's being replicated to my disaster recovery location. Maybe I've got solid state and I've got spinning spindles. So you could map these storage classes to different categories and levels of performance of your storage. So here's kind of a picture that is going to pull together all the aspects of doing storage. Physically, on the far left here, I actually have a chunk of disk. Way over on the right, I have my pod that I want to gain access to that chunk of disk, and I want it to be persistent. So what would happen is the developer would need to write a persistent volume claim so that his pod could reference that persistent volume claim to get persistent storage. The persistent volume claim needs to reference the persistent volume, which is actually the definition of that 10 gig disk out on storage. This persistent volume could also have been a storage class. Okay, so if you're using storage classes instead of persistent volumes, then what would happen is when the persistent volume claim actually got executed, we would dynamically go out and create the VMDK file. So hopefully that's starting to pull together the details about doing persistent storage. Here's a typical example of showing you some storage class examples. If I'm running on top of vSphere, obviously I have my vCenter server, which I could define storage policies on. So let's just say, for example, I created 3 storage policies. I created gold, I created a silver, and I've created a maroon storage policy. Now, those storage policies have their respective characteristics. Some of them could be going, out to vvols. Some of them can be going to vSAN. Some of them can just be using tags to link to particular types of data stores out on my vSphere environment. Those SPBMs could be being consumed and used by virtual machines. Now I put Kubernetes on top. Those storage policies are going to automatically, if I use the respective vSphere plugin, will be made available for me inside Kubernetes as storage classes. There, I can actually assign a particular storage class to a respective namespace. So maybe this namespace, we'll call it namespace A. I want to assign namespace A the ability to use my gold storage. It's not exclusive. I could have namespace B here, and I could turn around and use that same storage policy on namespace B. But B, I want some more options. So I could have the silver policy also assigned to namespace B. And now my developer can choose which kind of storage makes the most sense for that respective application. So again, the developers or the application engineers can consume the storage, but they can't be the ones defining the storage classes. So why don't we take a pause here, and let's go ahead and take a short break and get up, stretch your legs, get a cup of coffee. And when we come back, we're going to dig into some of the parameters that could be defined inside your storage classes. Thanks, and I'll see you back from the break. Hi, and welcome back from the break. Let's go ahead and finish up some of the details about our storage class Kubernetes object that we could create, okay? These are going to be the respective key value pairs that you can define when you're creating a Kubernetes storage class. So a parameter such as my disk format, specifying thin or thick. The data store name, notice it's optional. The storage policy name, which could also be optional if you want to call it something different versus the actual vSphere storage policy name. You could call it differently. You can also, if you're using vSAN, include any one of these parameters. So if you're familiar with vSAN, all those parameters would make sense to you. And as you can see inside here, you've got a couple ways that you could have done this. I'm going to say most people are going to lean towards the way that we're illustrating in the book. I would go ahead and create a storage class using my Kubernetes YAML format for my manifest file. Down at the bottom here, I'm going to include a couple of parameters. One parameter that I'm going to include is my storage policy name. This maps over to the vSphere storage policy name that you want to, in Kubernetes, reference as vSAN storage class. That's what you're going to reference it in. So I'm using the metadata name tag inside Kubernetes that I'm using vSAN storage class, but that's actually mapping to a vSphere storage policy called vSAN FTT. And then they're optionally including the data store name to say specifically which data store we want to put this on. Typically, this vSphere storage policy would only be valid on type vSAN, but it's okay to specify the name. And then for the actual individual parameters, instead of putting those parameters, which I could have put a whole bunch of parameters here, since I'm referencing inside vSphere, I can just use the parameters inside the vSphere GUI instead to reference exactly explicitly what I want. So a little bit cleaner, easier way to be able to do that. So once we've created either our PVs or our storage classes as the site reliability engineer or the Kubernetes operator, what happens next is those storage classes or those persistent volumes are now available to be consumed by the application engineers, the person that's actually saying this application, this container, this pod needs persistent storage. So they're going to pick up and they're going to write this thing called a persistent volume claim. And inside the persistent volume claim, as usual, they're going to give it a name. And down here is in the spec is they're going to specify what it is they want. So in this particular case, the spec is they want access mode to be read write once. They're going to mount it as a file system. So the volume mode is going to be file system. And then they define their resources, just like we similarly did for when we were doing resources on CPU and RAM. They're going to say, hey, the request is I want 8 gigabytes. This is actually gigabits of storage. And then the storage class name inside here, they're specifically referencing a storage class name. So we've defined the storage class earlier. The developer could see which storage classes they had by simply doing a describe on their namespace. They could see the storage class names that are actually exposed to them. So now they've got a persistent volume claim. So they've claimed 8 about gigabytes worth of storage. Now inside their pod specification, they need to go ahead. Here's the typical pod spec coming down all the way here to volume mounts. And now there's some additional parameters they need to specify. The first one is how do we map this back to the persistent volume claim? That's going to be down in the volume section. So they're going to give their volume a name. It could be anything they want it to be. It will be referenced up here in the volume mount. And then here they're referencing their volume claim. And then they're referencing the claim name here, which has to match the value of their claim. This would then attach that chunk of disk to this particular pod. This pod's going to mount that chunk of disk to that particular path. So somewhere inside this application that they're running, the MySQL, they're going to access the var lib MySQL subdirectory, and that's probably where their database is going to ultimately reside at. Architecturally, what's happening when you use the vSphere cloud provider? So if you were running on vSphere, the VCP is the vSphere cloud provider. That is the functional equivalent of the CSI jumping in between Kubernetes and doing the mapping over to vSphere. And vSphere could be any one of these types of storages, vSAN, vVols, VMFS, or NFS. What happens when the PVC and the pod specification, those appropriate parameters are put inside the YAML file, it is the VCP that's actually connecting out to vSphere and mapping that into the respective pod so the pod can actually gain access to the disk that's being provided via vSphere. So the VCP, to hit the points, provides the vSphere storage to Kubernetes. It's going to support all of the storage primitives, PV, storage class, and PVC. It can expose for me the SPBM, my storage policy-based management policies, as VMDK files inside my Kubernetes environment. It allows me to do this policy-driven dynamic provisioning of my persistent volume. So I'm not running a VMK FS tools to actually create VMDK files. The VCP handles it dynamically. Okay. And those services, are available through the SPBM. So I could just simply reuse what I'm already used to doing to my virtual machines, which is applying a policy. I can now apply those policies inside my Kubernetes infrastructure. If your developers are like, again, how do I know what I reference? As I said to you earlier, they could simply do a kubectl describe their respective namespace. And what would they see down here? They would see down underneath their resources, what they would have is this is their actual storage class name. bronze-storage-policy, silver-storage-policy. Okay, that would be the actual storage class that they could then reference when they're writing their respective manifest file. You can also do a kubectl get storage classes. Okay, and you can see inside here, they're giving me the details that is the details information a little bit more about the respective storage class. I could see the reclaim policy sitting as delete. I could see what my provisioner is inside here. I could see the storage class name over here. I want to bind mode immediately, so I'm immediately going to bind to it. Okay, it gets a little more complicated when we're talking about what happens if they requested 10 gig and now they need to expand it out to 20. There's a few extra hoops. You'll have to do a little digging to see if your respective CSI handles storage expansion. Okay, that's going to vary based upon whose CSI you've actually implemented, if you could actually expand the volume. In our illustration here, we can't. So, reviewing who does what. The operator is the person that potentially is creating the storage class did, or they would be creating the persistent volumes. Okay, again, how you create a persistent volume will be different based upon what you're running Kubernetes on top of. vSphere, I would have to use VMKFS tools to actually create a disk. If you were running on a different platform, you would have to check their documentation on how you would actually, when you use their CSI, how you would create the respective chunk of disk, using a persistent volume. Then the developer or the assembler of the application would need to go ahead and start consuming the storage. So they'll probably going to make a persistent volume claim, PVC. The PVC actually references the gold class. And then when they write their pod spec over here, they're going to reference their claim that they did over here using the name that was used in the claim. And again, just to go back to that slide right inside here, this particular slide, that is kind of reiterating that. Here's my persistent volume claim. Here's my claim name. The claim name is used here in the actual pod specification. And then whatever name I give it here is used in my volume mount section. So there's one other piece we've got to talk about. Up till now, we've been dealing with a single pod specification. When we reviewed our objects, we went over that normally we're not creating a pod spec. My pod spec is getting created for me automatically by my replica set. And I don't directly create a replica set. Instead, I create a deployment, which creates the replica set, which in turn creates my pod. That's all perfectly fine if you're stateless. If you're stateful, how am I going to map storage into each of the pods based upon my number of replicas? That is for stateful storage. That's where we're going to introduce a new construct in Kubernetes called stateful sets. Okay, so when a deployment must be persistent, that's when you use this thing called a stateful set, so that each replica gets its own chunk of persistent storage. Now, when you use a stateful set, you're going to see these unique pod identifiers. It's going to look something like the example here is talking about. Your stateful set name followed by some ordinal, so it starts base 0, 0, 1, 2, 3, 4, and then your service name and namespace name would all come into play when you're looking at that. So if you did a kubectl get pods and you're seeing something that looks like they're sequentially numbered, okay, it's going to telling you that that's coming from a stateful set. What a stateful set's going to give me is it's going to give me one persistent volume per volume claim template. So let's look at a YAML file and see what that looks like. That persistent volume is sticky to that respective pod as long as that pod is running. It's going to be a controlled deployment order. So pods are created in ascending order. So this ordinal number, you'll first see a -0 come up. We'll wait until it's actually running and operational before he creates the next one, which will be a -1. Again, he waits for that to be operational and ready before he starts creating the -2. If you're scaling down or deleting, they're deleted in descending order. Okay, so 2 would be deleted, then 1, then 0. So this is what a stateful set looks like. So it's very close to your deployment specification, except for inside here, we're going to reference a service name for my stateful set. And then we're going to add this new information here, which is this thing called my volume claim template. And the volume claim template is going to still end up, referencing some of the details that my PVC would have normally referenced. So this is not actually reaching out to a persistent volume claim. It's a merging of the PVC and the pod spec all into one that we're putting inside the deployment. So you're going to actually here reference the storage class name that you want. You're going to go ahead and say which size each of the disks are going to be. And then when you deploy the stateful set, he's going to actually go through and based upon our number of replicas, which right here, my replica is only sitting at 1, he would only then create one PVC/PV pair that he's going to use for this particular pod. However, if this increased, let's say up to 3, and I reapplied it, then it would spin up a second pod using the volume claim template, grab another chunk of disk for it, and then grab a third one and continue to do the same. So stateful sets is what we use when we want persistent storage on the equivalent of what would have been a deployment specification. So that leaves you guys to jump in to do this lab. You're going to first observe stateless behavior. So make sure that you do have an account created in the Go web app. You can log in, you've got stuff on your notepad, and then up here where we're observing it, we're going to go ahead and we're going to delete the backend application. It will automatically, that pod should automatically restart for us because it's part of a deployment. And then you're going to go attempt to log in. And you're going to see you can't log in. Well, what happened to my notepad? When you deleted the MySQL pod, all the data went bye-bye. That's the nature of stateless. So you could see that, yes, it's not working. Then you're going to go ahead inside here on tasks 3 and 4 is you're going to convert it to use a persistent volume and a persistent volume claim. You're going to go ahead, you're going to provision both of those, the persistent volume and the persistent volume claim. And then you're going to go ahead and you're going to convert it to use the persistent volume claim. And then we're going to go back in and we're going to test it again, which means you are going to have to recreate your account, recreate your notepad, confirm that it's there, log out, log back in, see that it's there, log out, and then we're going to actually delete the backend pod. And what's going to happen? Well, it's a deployment, so it's going to get restarted, but now you'll be able to log back in. So take your time, enjoy the lab, and I'll see you when we come back to our next module. Thanks. Hi, and welcome back to Kubernetes Fundamentals in Cluster Operations. I'm Mark Allenbaugh. Let's go ahead and get started with Module 7. We're going to talk about some additional Kubernetes resources that you would typically see in enterprise deployment. What kind of resources are there? Well, you're going to see these additional types of objects appearing called config maps, secrets, jobs, cron jobs, and a daemon set. Okay, they're all going to be typically used in an enterprise deployment of various different types of applications. So you need to know a little bit about what they are, what do they do, and how they're going to aid in getting higher reusability of your Kubernetes containers that you're running in microservices by using config maps and secrets in turn. So we've got two lessons inside this module. We've got dynamic application configuration, which we're going to hit next. So we're going to actually get into these things called config maps and secrets. And then we're going to wrap it up with additional types of workloads, which you can see. And that's where we're going to cover the cron jobs, cron, as well as our daemon sets. So this is a short lesson, but let's go ahead and go through it. It's an important piece for you to have a good understanding of. So dynamic application configuration. And let me kind of give you an idea of what this would be used for. Let's say I'm writing some application, and the box here represents my application. And in my application, which is going to be, developed inside of a container, what do I want it to do? I want it to come over and reach out and connect, let's say, to an FTP server, log into it, and see if anything new's been posted there. If something new has been posted there, go ahead and say maybe move it to another subdirectory on the FTP server, and then I want it to send out some type of SMTP email to some group saying, hey, something's come in, you need to go look at it. Well, inside my code, how do I know where the FTP server is? What's the FQDN to connect to it? What's the username and password I'm going to use to log into the FTP server? What subdirectory should I be looking in for new files? Was there a path to that? Where did you want me to move the files to? How do I connect to the SMTP server? Do I need to connect just on port 25? Do I need to authenticate? What's my username? What's my password? What's the group I should be sending it to? Maybe what's the subject line that I should be putting in there? What's the message I should be embedding? Developers have been told never hard code anything inside of your code. Well, these type of configuration options would be a perfect candidate for me to put into a config map. The password, the username that I'm using to log into the FTP or my SMTP server, those would be great candidates for me to use a secret object for, so I could not post the password in clear text. I would have a config map maybe while I'm testing it as the developer. Then I'd have a different config map that maybe I would use when I go into production. So this dynamic application configuration is something that we would use to pass those type of parameters in. What we're going to cover is how do you create a config map? How do you pass through the config map information into your respective container so we can pull that information up. We're also going to talk to you a little bit about what secrets are for storing sensitive data. So the first thing you need to think about is in your application is when an application is being reused. So you've got a container image that you're going to go ahead and say, I want to reuse this. This is an application. Should that container image have maybe some type of default values that are acceptable for some of the values inside of it? And then additional configuration values is something that I could be supplied by Kubernetes and the environment to inject into my container that when it boots to say, I want you to use these parameters instead. Well, this is going to involve the developer. This is not something we could use as the site reliability engineer or the DevOps team or whatever to be able to just say, you know what, I'm going to start using these. It actually has to be changed inside the code to say, look for the parameters in a specific location via a config map or accept them via an environment variable. Now, the coders that are writing the application need to make some decisions here. There's really two basic approaches that somebody writing the code needs to decide. Should they provide inside the code default values and start the container/application even if no configuration values are provided to use to override the default values, that you're just going to boot whatever this container image is and run it with the embedded default values? Or do you require the configuration and basically fail to start if required values are not provided? Based upon our security protocols that we should all be really focusing a little bit on is making sure we do have a secure environment. I'm going to tell you, I opt for the second one. If it was me working on a team, I'm going to say, listen, all of our stuff, if the configuration values are not fed into it, do not start. Don't run with the defaults. If you look at a lot of the breaches that have occurred, or penetrations that have been done on networks, it's because people are running stuff with default values. And then in turn, the hackers know what the default values are, username, password, and they're able to penetrate into that particular application. So my vote would be work with your team and say, listen, we are going to pass the configuration details into the container image. It's going to pick them up from there. If it's not passed in, fail. And the developers will probably immediately know what we're talking about. So how do I get values into my application? Well, what we would use is we would use in Kubernetes this thing called a config map. And you could see the construct over here of two different config maps. One config map you could see just by its name I'm using in my quality assurance cluster that maybe I'm using to test the application to see how it's working. Then I have a different config map over here that I would maybe use for prod. Now in this particular case, this type of config map that I'm doing, I'm actually creating two files. One file called server.properties, and inside that server.properties file, I'm putting in two values. I'm creating a second file called job properties, and inside of it, I'm putting one, key value pair inside there. And then the same ones are used over here in the production, but you notice they're different values, 100 versus 25, true on TLS, false versus TLS, number of threads 10 versus 5. So inside of the code that the developer's writing, they're going to need to look in a specific subdirectory, and they're going to look for two files, one called server properties, one called job properties. And in those two files, they're expecting a series of key values that they're going to use inside of their code. Now, config maps, like everything in Kubernetes, is namespace specific. You could specify here, I could right here specify the namespace for this config map, or I could have left this off and just made sure that my context was the correct namespace and kubectl applied it, or I could have done the -- namespace parameter and specified it. Okay, either one of those would typically work. But like everything in Kubernetes, it is namespace specific. When you create a config map, it is going to be getting created in whatever your default namespace is or wherever you target to be created at. So now that we've created our config map, how do we actually get the config map into our pod where our container's running? Well, in your pod/container spec, in the spec section, right below possibly where you've referenced the image you want, you would include some additional arguments. And there's two different ways that you can do this, two larger general ways, and then there's more specific in each one of them. So let's first talk about one way to bring your variables out of your config map into your container image. One could be using environment variables. So in your Docker file, for example, I would actually do an env key and specify a particular environment variable that I'm going to be setting. If we go back to our specification, we could see right down here, those three that I put the red around would actually be my environment variables. So I would actually, in my Docker build file, do an env maxapp _max _ threads. And in my Docker build file, if I wanted to give it a default value, I could go ahead and set it equal to 25. Now, when it comes to mapping my config map in where I want to override that, I could go ahead and use the environment from, say that it's going to come from a config map, and then I would use the name of my config map. So if I go back to that slide, you could see right here is my naming. Now in this case, we're actually using the name on this side. So I'd be loading up all of these values as environment variables that in turn my container image would be go ahead and grab those and use those for the values for the application. If I didn't want to load all of them, as an alternative, instead of doing environment from, I would just say environment, name the environment variable. Here's my name that I'm giving my environment variable, and I'm setting that value equal to, and then again, I'm going to do a value from config map key reference, specify the config map name, and then the key that I'm referencing out of my config map. So this is one way that we can get them in. If my application is expecting environment variables, then I would do it this style. So if our container was not set up to process these values from environment variables, but instead they were designed to go ahead and read them off the file system, we could still map our config maps through into the file system by following this type of syntax. Two different options. Do I want to load all the keys that I've loaded in my config map, or do I want to just load individual keys? If it's all the keys, again, in my spec section of my deployment, I would go ahead where I'm normally specifying my containers. I've named it. I'm saying which image do I want. Right inside here, I'm going to add a volume mount. This volume mount is going to have a name that corresponds to the volume that I'm telling the pod that I want it to include. So below in the volume section, those two names, they just got to be equal. Okay, they just got to be equal. And then what I'm saying is go find a config map with this name. Everything that's in that config map will now be placed in a file inside that respective subdirectory. So it's up to the container, the application, to know to go look in the app/config subdirectory for a specific file, and then that file that I specified in my config map when I created it will be existing in that subdirectory. My application will open up the file and read the values out of it. Similar concept here for loading individual values, except for down below, after I've specified my config map, you notice the config map again is equal, the name is equal. Instead, I'm going to add an additional section called items, and then inside there, I'm going to specify the individual items that I want added. So in this case, look for a key called server properties and load that in, and then that would in turn get loaded inside of this corresponding subdirectory up here. So that kind of wraps up some of our configuration, our config map in two different ways to do it, via environment variables or to use it via mounted directories. This is a comparison between the two. So if you're going to use environment variables, that's great. It doesn't rely on the file system nuances. It's easier if you are running containers outside of Kubernetes, because that system might not be able to handle a file system getting mounted inside it to expose it. However, if you do use environment variables as your methodology to get your values into your container, realize that if you said, wait a second, I need to adjust a config map value. If you adjust a config map value that has your environment variables inside there, you do a kubectl apply, your container is still using the old values. The only way it's going to see the new values is if you restart the pod. So that's the one downside of using environment variables. If you're using mounted volumes, the second you make the update to the config map, that's immediately reflected in the mounted volume, but it doesn't necessarily mean that your code will pick up those values. It's depending inside the code how it's processing those values. Okay, if it's only done once at startup, when it's done its config, you would still have the same requirement. You could potentially have to restart your pod. So last but not least, before we throw you in the lab, is talking about secrets. Secrets is where you would be using to store sensitive data, things like password tokens or even a key that you wanted your application to have. Now, all of them, whatever you're putting inside of a secret, must be base 64 encoded. So it's a simple command to, base 64 encode a string, but realize that's really not very secure. Base 64, I could decode that, lickety split. So it's not the best, a security tool using base 64. But what secrets do for us is they set up a platform where we could integrate with a third-party solution that's managing my secrets. A very common one is HashiCorp Vault. Okay, so via HashiCorp Vault, he could go ahead and publish out secrets and have Kubernetes, because he's publishing the secret, it's just a secret, you could then use it inside your Kubernetes platform. So these secrets can be exposed to a pod either via environment variables or mounted volumes. The same technique we already spoke to you about. As I said, there's many third-party products that would do that. Here's an example of a secret file. You'll notice down here both the username and the password are not in clear text. So those have been base 64 encoded. We're going to give you a chance now to work with both of these. So in the lab that's coming up here, you're going to go ahead and revise the front-end application, which is our Go web app. We're going to go ahead and build a new version that's going to be looking for an environment variable. So we're putting that in our build, in our Docker file, which is our file we use to build the image. This value here that we're going to be using, we're then going to go ahead and pass that in via the config map that we're going to go ahead and create. We're going to create a secret object as well to pass that into an environment variable, which is going to be the password we're going to use. And then you're going to need to update the deployment with the appropriate YAML statements to say how you want to expose them into the application. So it's a good lab. Enjoy it. The one thing I do need to tell you that when you're done with this and we tell you to test the application, you're not going to see anything different. Okay, you're not going to see anything different. It's just how we configured it behind the scenes is different. So go ahead and enjoy that. And when you come back, I'll see you in our next lesson. Thanks. Hi, and welcome back. Let's go ahead and dig into lesson 2, and we're going to talk about some additional workloads to finish off this particular module. So what other types of workloads could potentially be used inside of a Kubernetes deployment? And you've actually already seen one of these. you'll notice in some cases pods show a status of completed. They don't show running. They don't some show error some state. They show instead the status of completed. What are those? Well, in some cases, if you think about if you have an application, I might need something to start, run, do a series of steps, and then stop and not run again. Those would be the types of things that we would create as a Kubernetes job. They run, they start, they execute, and then they finish. They're not perpetually running. I can also have a counterpart to that, a thing called a cron job. Let's say I need something to run once an hour, once a day, once every 15 minutes. That would be a logical cron job. It's not perpetually running. It's getting scheduled to run at a certain time. We can also have another type of object called daemon sets, which we'll explain all three now. So what is a job? As I said to you, it's something that needs to be done once. Maybe I need to initialize something. So the job is going to run in a pod. So it is still a container. You write your code using container style development. I go ahead and I create an image out of it. And then I simply am going to schedule that image to run as a Kubernetes job. The container code runs to completion. So if you can think about it, it's the old legacy style code top down. As I said, it will be container or pod based. And the job that is running, my container workload that is actually running, needs to execute with a successful completion. That means that a successful completion means it exit with a 0 result code. If it doesn't give us a 0 result code, then what's going to happen is Kubernetes is going to think your job failed, and typical style Kubernetes, it's going to keep restarting that job and let it keep trying to run until it completes with a successful result. Now, jobs, when you run them, we're going to keep the pod and the job resources around. Why are we keeping them around is so that you can view logs, output, and so on. So if it ran successful, you'll be able to access the logs. If it failed, you'll be able to access the logs and see why it's failing. So this is one of those where you're going to have to figure out how you're going to implement your cleanup rules and what are the parameters for your cleanup rules. So we're leaving that up to you to implement. This is a typical manifest file for a job. We simply are saying kind is job. We give it a spec like we normally do. So again, it's a spec of a spec. We're giving it our container section. We're creating inside here our details. Our pod's going to be called, our container's going to be called Pi, just like our job's going to be called Pi. We're going to pull the Perl image, and we're simply going to run and compute what pi is to 2,000 decimal places. And this is actually going to be our lab in a few minutes. So the cousin of the job is a thing called a cron job. And what the difference is it's something that needs to be scheduled. So it could be a nightly job, an hourly job, an every 5 minute, etc., whatever you need it to do. So typical cron style scheduling, same parameters, the 5 different arguments that you would use. The characteristics of my cron job, well, my cron job actually creates a job resource. So if I had a cron job running every 15 minutes, when the 15 minutes came up, it would actually schedule a job to run, and then it goes to sleep and it waits for another 15 minutes. And then again, it would schedule another job to run. So cron jobs produce jobs. Jobs actually create a pod, which is where the code is actually executing at. Now, unlike jobs, cron jobs by default will keep 3 successful jobs and 1 failed job, okay? If it's run more frequently, the older ones are just getting automatically purged as part of the structure inside Kubernetes. And then finally, here's an example of what a cron job looks like. So the schedule here is typical Linux cron style. In this case, this guy's going to run basically every minute. So he's going to come through. He's going to, here's my container spec on what he's going to do. He's going to use the BusyBox image. He's going to execute, get into a shell, and he's going to send a command through that says, type the date, and then echo out hello from a Kubernetes cluster. And that's literally all it will do. So it will spit out a job. And again, you'll get a chance to briefly play with it in our lab environment. Finally, our last type of additional workloads that you can run across is a thing called a daemon set. And if you think about our Kubernetes cluster, right, I look at my Kubernetes cluster. Inside my Kubernetes cluster over here, I've got the typical 3 control plane nodes, right? These are my control plane nodes. And then over here, I've got some worker nodes. These are my worker nodes. Maybe I'm starting off over here with 3 worker nodes. If I want a pod to be on every one of my worker nodes, the easiest thing for me to do is create a daemon set. And what it will do is it'll make sure that all the nodes that have been added to the cluster, a specific pod will be deployed on each one of those worker nodes. Now, this is commonly going to be used for administrative functions. Things like logging and monitoring code that I want on every one of my worker nodes. So if I suddenly came in after the fact and said, as the Kubernetes operator or site reliability engineer, I go, listen, this cluster needs more worker nodes. And I suddenly came in and I created 2 more worker nodes. Because I've set up a daemon set, what would happen automatically, the second I added those worker nodes to the cluster, is the additional pods would be created for them, on them, because that's what a daemon set does. So, hopefully you're ready to go experience these last couple inside here. We're going to give you a chance to go ahead in Lab 10, go take a look at jobs and cron jobs, get a chance to play with them. And when you're done with them, I hope to see you back for our next module. Enjoy the labs. Hi, and welcome back to Kubernetes Fundamentals and Cluster Operations. My name's Mark Allenbaugh, and let's go ahead and start Module 8, where we're going to talk about some of the security features we could use inside Kubernetes to be able to protect our workload that's running in our Kubernetes cluster. So the goal of this module is to go over and show you the different types of resources that Kubernetes has to help us implement different kinds of security controls that we're going to then use against our containers to protect them. We're going to talk about the different security controls inside Kubernetes, and then we're actually going to do a lab and we're going to implement several of those security controls, so you'll get a chance to get your hands on it, play with it, see what it does. So the first one we want to talk about is a Kubernetes object called the network policy. And what a network policy is, I could translate it real simple for you. It's very simply your firewall rules. You're writing a set of firewall rules to say, what traffic do you want to allow through? So when you're writing your network policy, you're first going to have to select, a group of pods. And you want to choose that group of pods that you're going to be applying the policy against. And then from there, we're going to dictate what traffic is allowed into those pods and we're going to select those pods based upon the labels that are attached to the pods, and then we'll write and define our rules that will specify the traffic that's allowed to those selected pods. Now, normally, a piece that you want to be aware of it when you start off with your Kubernetes cluster, and if I draw this big box that represents my Kubernetes cluster, and any box that I put inside here are various pods. Okay, they're just a series of pods. By default, inside Kubernetes, all pods can talk to all pods. There's nothing blocking them. So by default, everything can talk to everything. And as we know, that's probably not the security posture we want to take. We would rather instead have a zero trust policy where we're going to explicitly say what traffic is allowed in, and then anything else, if it's not in our list, is going to be denied. So, as I said to you, by default, pods are non-isolated. That's the default. They will accept traffic from any source. Internal or external, they're going to accept traffic if it can get into the pod. Now, pods can become isolated. How would you get a pod to be isolated? Well, one way you could do it is you can define a network policy. Like any other object in Kubernetes, a network policy is going to be applied in a namespace. And in turn, in my namespace is where my pods are typically running. So a pod can reject connections that are not explicitly allowed by a network policy. That would one way that a pod can also become isolated, right? I apply a series of rules, and whatever that traffic is that I have not included in my rules to allow will then be rejected. That pod could potentially then be actually isolated. Also, when we're looking at a namespace, other pods in that namespace that were not selected by the network policy would continue to accept traffic. So when we look at our Kubernetes cluster, we've got our Kubernetes cluster, and as we've drawn out before, one of the things that we're going to be defining in our Kubernetes cluster is we're going to be defining namespaces. So let's say this is namespace 1. I'm going to go ahead and create another Kubernetes namespace. And again, the namespace goes throughout the entire Kubernetes cluster, and this is namespace 2. Now, within a namespace, I can have a series of pods. So in the green namespace, namespace 2, I've got 5 particular pods that are running that are green. And then I've got 5 other pods running in there as well in the namespace 2. When I write my network policy, I need to select which pods I want to apply the policy to. I'm going to do that again by selecting based upon labels. If my selection criteria says select all of these black pods that I just circled around, my policy would now be applied to those specific pods. Whatever my firewall rules definitions allow in is what will be allowed into those pods. Whatever my firewall rules allow those pods to send out, egress, will be allowed to egress from those pods. What about the green pods? Those pods were not selected in the network policy. So these green pods here, these green pods are actually going to continue to operate with the default behavior accepting traffic from any source. So let's start to look at a network policy so we can get a feel for it. So here I am writing my YAML file for my network policy. You can see up there the kinds network policy. This particular policy actually has the namespace added inside of it. So it's explicitly saying which namespace this network policy would be applied to. I would still have to do a kubectl apply it, but it's saying which namespace to apply it to. Then underneath the spec, my spec is now going to start off with a pod selector branch. I'm going to say my pod selector says match labels. So I'm going to match pods that have a particular label. The label key value is tier, and then the value would have to equal back end. So these are the pods that this policy would be applied against. What kind of networking policy do I want to create? In this particular case, we're going to create an ingress policy. So this is going to control the traffic that can come into pods that match that selection criteria. Now, remember when you're writing a firewall rule, there is a source and then there's a destination. A source and a destination. In our case, my selector section here is effectively setting the destination. The ingress, the source, that over here is being defined down here in this ingress section. In the ingress section. Now, this particular ingress branch that we're on is selecting traffic coming from, so the from here is my source, and I'm saying it has to be coming from, and what is he doing here? He's doing a namespace selector, and he's saying anything that is in the default namespace, that's where I'm applying this at, and it has a label on it of project go web. So any pod that has that this section here is what we're saying would be my source. Oh, I've got another entry from source, and in this case, they're at the same level underneath a single from. That now turns into an or it could be a pod's coming from anywhere, a pod coming from any namespace, as long as it has the label app go web. So my source is actually an or in this particular case. And the traffic that's coming from source to destination would be needing to come in on TCP. It would be destination for TCP port 3306. That is defined down here. Network policies can get a bit long and they can get a bit complicated. There's lots of tools available online to help you validate your network policy. Make sure that you're getting all the appropriate stuff. They'll try to interpret your rules and give you a spit out, an output of what they think your firewall rules would end up looking like. So here, for example, is a network policy. And in this particular example, we're only looking at the inbound. So going through the manifest file, the kind here is network policy. I've given my network policy a name, and this particular network policy, I've said exactly which namespace I want it to apply to. I would still need to do a kubectl apply, and it would then go against and be applied against the default namespace. Now's when we start formulating my typical firewall rule. And when you look at a firewall rule, it typically has a source, it has a destination, and then it has, what service it's going after. Okay, so I'll go ahead and say the service, which is going to correlate basically to a protocol and a port. Now, this particular network policy, how it's written, we're doing a pod selector here. this pod selector turns into the destination. So what are we doing? We're matching pods in the default namespace that have the label tier, and a value of that label would be backend. What kind of policy am I writing? We're only writing an ingress policy. So now these rules here, the ingress, are going to start filling in the other two key areas in our firewall rule. The first being the source. Where does the traffic come from? Well, here you go. We've got our from key here. Again, we're in our ingress section. And in this particular case, we're actually going to do a compound selection of our source. It could be anything that's coming from the default namespace, because we're using a namespace selector that we're currently in, and we're saying match any labels in the namespace that this was applied to that have the key project and a value of GoWeb. So that's this first one here. Now, the namespace selector and the pod selector are at the same level, so that turns into an OR. Now it's saying match or any pod anywhere else as long as it has the label app with the value of GoWeb. So this information here is turning into my source column. That's where it's coming from, my source column. Then down here, the ports and the protocol, that is fulfilling my service in my firewall. So if you're used to a typical 5-tuple firewall rule set, that's how I'm ripping this network policy apart and putting it into the appropriate source, destination, service. And then by default, anything in a network's policy is going to be an allow. There will then be right behind that rule, there's going to be another rule right down here. That other rule is the same destination column, and it's going to be an any block. So whatever you haven't positively allowed through, there's an implied any, wherever I'm applying it to, any service, block rule sitting right behind the original rule. Here's a little bit more of a more restrictive rule. In this particular case, everything up to here is the same. It's the same as before. But now I'm doing an and between two conditions. You notice I'm doing two froms. Two froms. So in this case, when I'm looking at my source field here, right, my destination field is still the same. My destination field's coming from this to there. But now my source field here is going to say, well, I'm using the current namespace that I'm in, or whatever the namespace that this was applied to, and I'm matching the same thing, project, Go Web App, okay? So that is coming up here. But now I'm doing an and here, and the pod would also have to match the label app Go Web. Okay, so it's any pods in the default namespace that have this, and any pods in any namespace that have the label app Go Web. So there would be a double, there's two values, but it's an and it's the same protocol and port over here for my service. Do my pods that I'm applying this to need to talk out? Well, if they do, here's how I would take that same policy I've already been working on, but I'm going to now add outbound traffic. So everything up above here was the same. We removed a lot of lines. This is not complete. But what have we added is we've added an egress rule. What is it allowed to talk out to? So what am I saying? Well, again, I am saying that it's going to be something. This is all my ingress rules from here to here. So those rules are the same rules we saw in the earlier example. Nothing's changed from my ingress, my inflow. what have we added is we've added down here egress. Now, the egress in this case, you're going to have a source, you're going to have a destination, and you're going to have your service. In this case, the source field here was the original source field up here to wherever I applied it on. If we go back a slide, it's this pod selector. That's what would be your source in this case because it's an egress. Where is it going to? The destination? Well, that's over here. You'll notice it's real simple. I'm defining my egress and I'm saying to, and I'm specifying a CIDR block. And what should the traffic be coming out and its destination, where it's going to? It's trying to reach out on port 389, which would be LDAP in the clear. It wouldn't be LDAP-S, but it would be LDAP. And again, that would be an allow. And then again, right behind it is an implied anything else block. So before we take a quick break, I want to go over and ask you to be thinking about, you're writing these firewall rules. How are they getting implemented? What's actually doing the enforcement of the firewall rules? Well, depending on what CNI you've used is going to determine what's actually implementing or doing the enforcement. So several of our Tanzu solutions that support NSXT, the network policy rules are actually enforced by the NSXT platform distributed firewall rules. For other projects like Antria, Project Calico, and other solutions, they're going to be implemented and enforced by whatever solution you've chosen to implement. In our particular case, Antria is being enforced via the Open vSwitch. Project Calico is actually writing IP tables rules to actually do the enforcement. So it helps to understand how would you actually troubleshoot these rules. You would have to be able to dump your IP tables if you were using Calico. Antria, there's actually extensibility built into Antria, so there's actually an interface you can look at in Antria to see your network policy rules that have actually been applied to the various ports inside an Antria implemented CNI. So with that, why don't we go ahead at this point in time? Let's take a short break, stand up, stretch your legs, and when you come back, we're going to continue on with the other sections of our security module. Hi, and welcome back. Let's continue on with our security lesson. And one of the controls that, an additional control that we can put is when your container is executed on the host container OS, what privileges do the processes that you're running inside your container have? Well, we're all familiar, you log into Linux, sometimes you have to, do a sudo or switch user to root to do a particular command or a function. This allows me to control basically what your user ID is going to be, your group ID, and even your file system group ID if I'm starting to implement specific security controls in the actual Linux distribution that I'm using to be my container host OS. So this is going to involve around this thing called a security context. And it will define the actual privileges and various access control settings for the pod or for the container. So remember, bigger picture here is we have your pod. Inside of your pod is running your container. Your pod is actually running out here. Again, there could be multiple pods running. It's actually running on our worker node And our worker node is our container host OS that's running out here that's actually hosting the pod. Now, in this particular case, when I want to define security settings, I could tell the pod you're going to use a particular user ID, or I'll set some security context on my pod. If I don't set a security context on the container would basically inherit that user ID security context into the container. I could individually set it on the container itself. So the pod spec section is going to be defining the respective container privileges. They'll define first, if we define it at the pod level, that will become the default for all the containers that are running inside of the pod. Pod level privileges can be overridden, so you can define privileges at an individual container level. And you can enforce these various restrictions with another construct, which we're going to cover a little bit later, which is called a policy. Okay, so we're going to cover what the policies are in a later section in the class. So here's some ideas of some examples. I could do a security context setting of run as a particular user, run as a particular group. If I'm using security enhanced Linux, I can put specific examples to activate features in my security enhanced Linux. I can restrict which Linux capabilities that your container or pod is actually able to gain access to. And I can even control the host paths that could be mounted in your pod. Remember when we were doing our volumes and our mounts, I can control what host paths can be mounted and accessed. So we're not going to cover all of these. We're just going to introduce a few of them to give you a feeling. So inside here, this is a pod manifest file. And right here, I'm starting my spec up. So the first thing I'm doing above my containers section, I'm setting a security context and I'm saying run as user ID 1000. Now I'm going to start my container sections up. So as I start my container section up and I start coming down here, this one particular container, I'm setting some features. I'm setting a security context to say allow privilege escalation of false. So if somewhere inside your code, you're trying to escalate your privilege, maybe by doing an SU, I'm going to say, nope, it's not allowed. I'm denying it here in my security context section. This particular container that's running in this pod, it has a security context section, and he's saying run as 2000. So in this particular case, I've got a pod that I've defined. The pod has the run as user up here. I'm saying the pod is user ID 1000. I've got a container running inside my pod right here. I'm saying don't let it escalate privileges. I didn't specify a user ID, so this user ID at my pod level will actually inherit inside my container. I've got another container here that I'm running. That's this container definition here. And this guy's going to be running as user ID 2000. Why? Because I specified it down there and I overrode what I put in the pod. So you're going to get a chance to play with the security context in the lab that's coming up. So hopefully that's making a reasonable amount of sense to you. We also got another area of security we need to talk about. And that is, how do we control API access? So I've got my API server. Here's my API server. And out here is somebody sitting on their laptop, and they're running a kubectl command. The first question is how to identify who that person is. How am I going to do authentication to authenticate the user? Where am I going to authenticate against? Next, now that I know who you say you are, how am I going to control authorization? What are you allowed to do? If you are allowed to do something, admission control will go ahead and say you are who this is, you're authorized to do this. It will then grant access to the nodes to do whatever you're authorized to do. See whatever you're authorized to see. We're going to go through all of those components now at this time so you can understand how those various things are actually being implemented. So the first one, Kubernetes does not manage or authenticate directly inside Kubernetes. Your users are not. We have to tie to something else. We've got to tie to an external identity service. That external identity service needs to be able to generate what we're calling as a trusted token that we could then use to communicate to the API server. The API server supports a standard called Open ID Connect, OIDC. And that's what the user would be given once we've authenticated them, whatever the system is we're going to use. It needs to generate for us this OIDC token that we would then in turn let the user store in their kube config. Now, how are we going to do this authentication against a system, and what system is that? Well, that's going to depend on your Kubernetes solution and what you've chosen to use. Our Tanzu products, okay, depending on which one you're using, can either go directly against the platform services SSO domain and whatever you have it connected to. Most of us have our vCenters authenticating against Active Directory. So this particular solution here would be the vSphere with Tanzu, okay? With vSphere with Tanzu, it's a very quick and easy thing for me to link it up to the platform services SSO domain. My other solutions are going to give me the ability to connect to LDAP is typically going to be the solution, and you're going to have to install some stuff to be able to do that. Okay, so Pinniped, Index, TKG, TKGI, we can go directly against an AD or an LDAP source. Okay, so both of those are options for us. Pinniped and Dex actually would go against LDAP or Active Directory as well, but it is some additional steps you would need to set up to get them to authenticate. Each vendor solution you choose, this is going to look slightly different. There's another common pair, it's called Dex and Gangway. Our current version of TKG, we're using Dex and Pinniped. It's just easier, cleaner solution to be able to connect to your authentication, your external identity service. Now, the authentication method that we're using is going to involve both client certificates, tokens, and external authentication. Your client certificates are typically going to be used against the various cluster components. So how does kubelet and the API server authenticate that they are who they say they are? They're using client certificates. When you did your kube admin init, if you would have catted out your kube admin out file, you will see that it's going through a series of phases. And one of those phases is it's generating client certificates for all of the various Kubernetes cluster components. Tokens are going to be used for service accounts. They're generated automatically when a service account object is created, and then the token actually gets mounted inside the pod at this particular path so you can see where the token would be, and then it could present the token when it needs to authenticate against the API server. External authentication, that's where we would use to authenticate our users. So depending on what you've chosen to use, in most cases, when the user tries to do something, then they're not authenticated. A form opens up. They would have to type in their username and password, and then the system would reach out to the external authentication mechanism, validate they are who they say they are, go through some other steps, and ultimately end up generating an OIDC token that would then be the user would use to do future authentication to the API server. So I know you are who you say you are now. So let's focus for a second here. Either via user or group, you've been able to successfully authenticate. So I agree, you are who you say you are, but now what are you allowed to do? And that's where Kubernetes RBAC comes in, role-based access control. Same concept that we've used in all of our other platforms, okay? Everywhere, every other platform out there, not just VMware, is using role-based access control. So it defines what is somebody allowed to do. So I first need to identify the user. I then need to identify the what can they do, right? So the role here is saying the what can they do? What can they do? They could create, they can update, okay? I need to bind these two things together. So that's called a role binding. So you need all three of them, the who, the what, and then the joining together, which is your role binding, to get your RBAC in place and to be able to get it operational. So the first thing is this thing called a role. A role is going to define the what they can do. So what can they do and against what? Okay, so in this case, the API group here being blank, that's just basically the core groups, which would be anything with an API version of V1. So if your API version is V1, that is a core group. Now, what can you do? What resources in that core group can you reach? In this case, I'm saying they can actually, this role, they can look at a secret. Remember the secrets we just created? What can they do against the secret? They could get one. And you're going to have some built-in roles that are already done for you. And then, of course, you can create your own. So this particular role, without the word clustered in front of it, this particular role would have to be applied against something. So I would go to a specific namespace and do a kubectl apply, and then this role would be active in this namespace. In this particular case, if I kubectl applied it, regardless on what my current context is, this role is being applied to the default namespace. So they're actually selecting the namespace that it would be applied against. Roles, like everything else, are namespace specific. However, there is a thing that is both words combined together, a cluster role. So a cluster role is not defined or applied to a namespace. It is, by its definition, cluster-wide. So a cluster role spans the entire cluster. Same things, we give it a name, we select the API group that this is going to be applied to, and then the resources within the API group, and then I would specify the verbs of what I allow this person to be able to do. Remember, this is access to use kubectl against the API server. So I could say you could get, you could watch, you can list. Then we're going to be starting up here with role bindings. But I realize I've been going at this for quite a bit. Why don't we go ahead at this point in time before I start into the binding section? Let's go ahead and take a break. And when we come back, we'll finish up the security thing, walking through the various bindings. I'll see you when you come back from your break. Thanks. Hi, and welcome back. Let's pick up and finish the rest of our role-based access control section in our security lesson. So we first have been able to authenticate somebody. So we've set up an authentication mechanism. Then we're working now on doing authorization. What is somebody allowed to do? We previously discussed what is a role. A role is going to define for me, if you look inside here, this particular one is actually a cluster role, but it's saying to what API group, what resources in that API group. So the quote is the core V1 API group, which is the core of Kubernetes. Then a specific resource, so I could have put pods, I could have put replica sets, I could have put deployments, any of the resources that we've already gone over. And then I'm specifying which verbs they could do against those objects. So this one could do a get, a watch, and a list, which is telling me they can't modify it, they can't delete it, they can't create it. There's two types of roles, both a namespace specific role and a cluster role. Namespace specific, you have to apply it to the namespace you want it to be on. Cluster role, cluster wide. Now I need to join together the who and the what by using this thing called a binding. There's two types of binding. There's a role binding, and then there's a cluster role binding, just like we had roles. A role and a cluster role, a role binding and a cluster role binding. So what am I doing here? Role bindings are going to be namespace specific. So I'm saying in which namespace. I don't have to do it in the YAML. I could have left it out, and then whatever my context is where I applied this is where it would be applied to, or I could have done the -- namespace parameter when I did my kubectl. All of them would work. Then here are the subjects. This inside here is the who. Now, typically, what we're going to want to do in any of our bindings, the who should always be a group. That way you're not doing constant add, move, delete type of Kubernetes busyness. You set it up once, use your group and AD. Maybe the AD people have to work with us and help set up some additional groups. But then when we want different people to have different rights on our Kubernetes cluster, it's just a matter of moving them in and out of the respective AD groups, and then their access would be appropriately activated off of my role binding. The role reference down here, this is actually referencing the role. Now, in this particular one, we're actually referencing just a role, not a cluster role, a role that was created. Here's the name of my role that I'm assigning it, and in this case, I'm assigning this to a service account. Versus a cluster role binding, I am binding this access to everything in the cluster. So my cluster has several namespaces. If I bound Jane in this case, using a cluster role called pod reader, Jane would have whatever the privileges are of the cluster role called pod reader in all namespaces on my Kubernetes cluster. So it's global to the cluster. Whenever you see cluster in front of a role or a role binding, it's global to the cluster. Now, all Kubernetes installations are going to include some default cluster roles that come with it out of the box. There's 4 of them. Cluster admin versus admin, the only difference here, okay, inside here, what's the big difference? The cluster admin can basically do any action on any resource, where the admin access is intended to be granted within a namespace using a role binding. So what can the admin do when I apply it to a namespace? They can read and write almost all resources in the namespace including the ability to create roles and role bindings within that namespace. What doesn't it do? It does not allow write access to resource quota or to the namespace itself. So they can't change what's going on inside the namespace, and they can't get to these things called a resource quota. We'll talk about those in a module, I think, one away from where we're at now. Admin role is going to give them read-write access to most objects in the namespace. It is not going to allow viewing or modifying of roles and role bindings. Where admin up here could, edit can't. View, well, name implies they could read anything. And again, the view role is going to give them read access to most objects in the namespace, but there is going to be some ones that we're a little bit more sensitive to, things like secrets. Like, no. If you want access to secrets, it's a specific resource that you've got to grant access to, because that we would consider to be sensitive data. So let's try to put this all together. Let's say, for example, over here, Jack needs read-only access to the cluster. So cluster-wide, Jack needs read access to everything. How can I go about implementing that? Well, I'm going to create a cluster role binding. I'm going to give it some name. I'm going to say the who. Well, the subject here is Jack. And then what can I give Jack that would give him access? Well, this is happening because of two things that we're doing. First, we're doing it using a cluster role binding. That means this access is going to be cluster-wide. And then I don't need to create a special role for this, because if I want him to have read-only, I can just use the pre-existing cluster role called view that we covered, and Jack now can see everything inside the cluster. Let's go one step further. Let's say that there's a particular namespace that Jack's going to be involved a little bit more with. So I want Jack to be able to do stuff in that particular namespace. So what do I want him to do is I want him to have edit access to a namespace called foo. So what would I do? I'm going to create a role binding, which means it's namespace specific. In this particular case, I'm actually putting the namespace inside my YAML file. I'm going to say the who, Jack. And then what am I going to simply do? Well, why don't I just use the cluster role that already exists called edit? Even though it's a cluster role, I'm binding it to a specific namespace. So in this case, it's actually namespace specific because of my role binding being namespace specific. So guys, we've covered a lot. We've covered a whole bunch. The lab that we're going to go through, the steps seem kind of brief, but there's a lot for you to do some playing around with and looking at some stuff. We're going to start off doing some security context in pods and containers. I'm going to suggest when you're doing these, you'll notice the book refers you to the commands.txt file, which is on your student desktop, because how we're going to test that is going to involve a pretty long kubectl command. So if you copy it out of the commands.txt on the student desktop, it would be very easy to paste it into your putty session and get moving with your lab. And then we're going to conclude it with taking a look at some network policies in the pods. So you're going to make sure that your Go Web App application is working before you start task 3. The book's going to walk you through that. Once you get it working, go ahead and apply the network policy, and you'll notice it's going to stop working. And then we're going to play around some more with our network policy. So we've covered quite a bit in this module. The security controls that we have in our Kubernetes platforms, and we're actually going to do some labs implementing them. We started off again with our network policy. Right? We went over our network policy. That's going to create firewall rules for us. We looked at our security context. Right? We looked at our security context. we're not implementing everything in the security context. We're doing a few things, run as, read-only file system. We're just doing some basic. There's much more for you to look up in the kubernetes.io documentation that you can go take a look at it. And then we ended it setting up RBAC. Okay, all of those are various different kinds of security controls. So enjoy the lab, and I hope to see you back in our next module. Hi, and welcome back to Kubernetes Fundamentals and Cluster Operations. My name's Mark Allenbaugh, and let's go ahead and continue on with our next module, which is going to be Module 9. So this module does mark a distinction point or a demarcation point where we're getting more into the operations of a Kubernetes cluster. So really, it's the second part of the title of the course that we're starting to transition into. So we've got to start thinking about the things when it comes to operating our cluster. How do we want to do things like gathering logs out of the environment that we're running on? How do we want to go ahead and implement a monitoring solution, be able to track how's my cluster doing? Is it running out of CPU? Is it running out of RAM? Is it running out of disk space? Do I need to scale it up? Have I over provisioned it? Do I need to bring it and scale it back down? So in this module, we're going to go over and understand how both my logging and my monitoring are going to help me to be able to troubleshoot what's going on inside my cluster. When we're looking at logging, one of the things we got to recognize or understand is which logs do we want to use and how do you implement logging? We're going to go over the different scenarios, and we'll give you what we think would be the most likely best solution for just about any Kubernetes cluster. And then we're also going to examine several different monitoring tools. And then we're going to actually do a lab with a particular monitoring tool so you can get a feel for what you can see out of that. So we've got two lessons we're going to go over. Logging first, and we're going to do a lab with that. And then we're going to jump into monitoring, give you an overview of monitoring, and then we're going to get a chance to do a lab with that as well. So let's go ahead and get started. Our first one is about logging inside Kubernetes. And as we started off in the introduction, what type of logs are there in Kubernetes, and how would you go about gathering those logs? Now, a piece that you've got to be aware of is if we look at the layers that are involved to where our Kubernetes is. So if we're saying, hey, this is my Kubernetes cluster up here. Now we know my Kubernetes cluster is made up of a series of various VMs, my control plane and my worker nodes. But the point is, the cluster is actually running on top of something. Typically, this would be our hypervisor. Our case, it would be vSphere. Beneath the hypervisor, we actually have some physical infrastructure, as well as, we're going to have down here not only physical servers, but we're also going to have a lot of my stuff like my routers and my switches that are sitting, that my hypervisor is running on top. Do we want to segregate those kind of logs apart? Depending on what you're doing, maybe these logs go to one logging collection mechanism and these logs go somewhere else, or do we ship them both to the same spot? So when you're troubleshooting a problem inside Kubernetes, maybe you're going to see a log screaming by saying, hey, we just had an ESX host failure, or, something happened to my SAN, something happened to a switch or a router. So think about the holistic approach of everything that is going on in the environment. And obviously, I think we could see if something down here boo-boos, that boo-boo's going to surface up very likely inside my Kubernetes cluster. So as we said, what type of logs do you want to capture? You could see inside there that Kubernetes itself has different logs that we would be able to use to troubleshoot specific areas revolving mostly around our application stack, which is going to be our container logs. The Kubernetes components that make up my cluster would be things like my host OS and my control plane logs. Inside Kubernetes, we've got event messages that are firing. We went over what those are. These are probably, should be getting your mind kind of racing, going, oh yeah, I'm definitely going to want all of this. You're going to want all of this in some logging repository that we could query. But let's go a little bit deeper. Do we want things from my underlying, operating systems that are running various in VMs that are running? Do I want stuff out of my hypervisors? Do I want security related logs, other IT infrastructure? Not just this. That's going to really depend on up to you. From our perspective, if they both end up in the same syslog gatherer, then you would be able to query logs across all of it. If you decide to segregate, so be it. Again, the same steps to get logging working in Kubernetes would be implemented. You're just going to send it to a different destination. So when we're looking at our container logs, we can real quickly see, yes, my container logs are going to have things like a timestamp and a log message. I'm probably going to need more. Like what? Well, how about the namespace that it was running in? The pod name, the container name, any labels that were on it, maybe the image it was using, maybe the node, the worker node name. So we're going to call this, we need to enhance the logs with additional metadata. And our logging solution that we're going to talk to you about is capable of doing that. It can actually enhance the logs with additional details, because we're going to want that when we go to do troubleshooting and problem analysis. We're going to want to know, oh, I see this is all happening with, this node name, or, a particular namespace something's going on into. So we're going to want to gather that additional information. How would you want to query the logs? So here's some examples. I'm not going to go through all of them, but imagine how you would want to query them. And you could clearly see when I say I want to query logs from nodes with a particular label, if my log entry wasn't enhanced with the node name, you couldn't query that. So if you think about how you'd want to query the logs, you could see why it would be imperative that we enhance our logs with the additional metadata so that we have that information when something's going wrong, that we could query the logs and get the results from it. Now, Kubernetes has built in the ability for us to query logs interactively from the kubectl command. And I will tell you, having worked a little bit with Kubernetes, a lot of times I'll start here. Something isn't right before I go over to the syslog server, which sometimes feels like you're looking for a needle in a haystack type of thing because there's so many logs inside there. I'm going to quickly just say, okay, I know this particular pod, something isn't working right. I could quickly, from my kubectl command line, just do a kubectl logs, my pod name, optionally do the -f or the not -s, which would just continuously stream them to me. Everything that's going on, the logs that are happening from that pod. So what are those logs? That's anything the application is dumping out, standard error. I'm going to be able to get those logs back right from my kubectl command. Just so you know, the logs for each of your containers, if we remember, we've got a pod. The pod, in turn, is running my containers. My containers in my pod are streaming stuff out to a log area where he's logging at. The standard out, standard error logs, where's the pod running at? The pod's actually running on a worker node. Right? It's running on a worker node. If I SSH into my worker node, if I SSH into there, I could go to this subdirectory and I would see down here all of the logs entries that are going on for my pod. I would actually be able to see them there. That's a nice backdoor. But again, in most production environments, people are not going to be able to SSH into a worker node. And that's pretty much so locked down. I could actually give myself an SSH session into the pod by doing a command like this. kubectl exec -IT, right? Interactive TTY terminal, my pod name, double dashes, and then bash. That will immediately go ahead and give me back a SSH section effectively into that pod. So a couple of different ways. Now, for an enterprise implementation, we're going to want to have these logs and be able to preserve them. So how do we get our logs out to a logging backend? Well, you've got several different ways you can do this. And we're going to go through each of the choices, and I'm not saying they're all good. In fact, I would say this one would be a big no. I would not implement this style of logging. What am I doing? In my actual application container, I'm putting logging logic. That logging logic says, wherever you're running, send your logs to some logging backend. People have done it. It's not the preferred way to do things. Another option we could use is we could say, no, let's bust that logging logic out. So what they've done is they've written another container, which is nothing but a logging agent, or they could have implemented some of the open source solutions and bundled that inside of it. And this is what we call a sidecar container. So every time I deploy some application container, I'm going to add an additional container, which is going to be designed to stream logs out to a logging backend. This is what we call a sidecar container. It's not the best. Let's just put it this way. It's not the best. It does work. Realize every time you're deploying a container in a pod, you got to add this as a sidecar. So if you're running 100 pods, let's say across 10 worker nodes, so that would be 10 on each worker node, right? That would be 100 pods. Your logging backend would end up having 100 connections coming into it. Not necessarily the best thing. If something I wanted to tweak on my logging agent code, you're tweaking it 100 times, right? Because it's going to be multiple different deployment files where you're specifying that second container. Again, not the best. The next one we have inside here is doing what we talked to, I believe, a couple modules called a daemon set. Now, what does that do is the daemon set's going to make sure a particular pod is on every worker node. As you know, each pod, standard error, standard out, is going to a logging file that's on the worker node. This pod is able to read that subdirectory, send the logs there off to a logging backend. So in this case, my backend logging, if I had 10 worker nodes, would only have 10 connections connecting to it that streaming logs on in. Now, this only works if your containers are logging through standard out / standard error, okay? It is the most common implementation of how logging is occurring inside Kubernetes. So this is the one you should be focusing on. Now, what is this? What is this down here? What is my daemon set? A very common solution is FluentBit, and that's what we're going to do in our labs. So you can also tweak it some. Let's say your application has some special logging that it's doing, or some debug code that the developer's trying to do. You could put in some type of streaming container to take those logs. This is more of a bookend type of logging solution. This would be a very rarely used, but it is capable. Have it take whatever it's streaming to it or wherever it's logging to. It could be actually reading it out of some unique logging file, and just have it stream it to standard error, standard out, and then let this guy pick up the balance of it. So he's not attempting this connection. He's letting your logging agent, your daemon set, do it. So before we go to break, let's summarize. You've got 4 different ways you could do logging, okay? And I'm going to pretty much say this is a big fat no, but it is an option you could see. This is another option. This is what I would call a kind of a sidecar type of logging, okay? It's just not the best. The bottom 2 here are going to be the winners. This is going to be the most common one you will see. And this one up here would be just used when it's absolutely necessary, using a sidecar that you would stream it to and have it be directed to standard out, standard error, because the code inside the application container, we're not going to change that to log somewhere else. So we've covered quite a bit. Why don't you go ahead, step away from the monitor, take a break, stretch your legs, maybe get some fresh coffee. And when we come back, we're going to dig a little bit deeper in some additional logging things we need to consider. So I'll see you when you come back from the break. Thanks. Hi, and welcome back from the break. So let's go ahead and continue where we left off at before we took our break. We had summarized the different types of logging scenarios that you could go through. And as I said before the break, these 2 down here, using a logging agent, typically using one of the open source solutions, is where you're going to end up at. And really, I'm going to probably say almost 90+% of your logging is going to be happening in that bottom left quadrant. There will be some exceptions where you might use something like this or maybe something like this. These 2 would be lesser used. So as you could see, the bottom 2 are using some type of daemon set to pick up the logs. A very common framework that is actually being used simply because it's all ready to go. This is more of a utility service that everybody says, hey, if you've got a Kubernetes cluster, you got to implement something for logging. Why reinvent the wheel every time? People are just going off and using FluentBit logging agent. It's open source, it's free, it's part of a project, so and it works absolutely wonderful. What's it designed to do? It's designed to process Kubernetes container logs. And as I said to you earlier, it can enrich the logs with the Kubernetes metadata. So I can get things like the namespace, the pod, the worker node name, etc. I get the additional information added to my log entry. And then you would use this logging framework, right, to output the logs to fill in the blank, okay? So, we're giving you some examples. We can do vRealize Log Insight. We have our own in-house copy that we're running, so we can log to that. You can see Elasticsearch, InfluxDB, HTTP, and other logging services. So you're basically just saying a protocol and a port where you want me to send the logs to. Really, anything that would be syslog compatible, you can log to. This is the common logging solution that's going to be deployed within the majority of our VMware Tanzu solutions. The difference is, depending on which solution you use, how much effort you have to do to actually get it to install inside your Kubernetes cluster. Our lab environment, if you remember, we're not using a Tanzu product. This is open source Kubernetes, so we're going to make you go through and do a manual install, which you'll find really isn't too hard. How does it work? So the FluentBit daemon set is running on each worker node because it's a daemon set. So that pod would be deployed on every worker node. As your pods and containers start to log stuff, they're logging to the common subdirectory on the worker node. FluentBit simply reads these logs and then ships them off somewhere. In this example, I'm saying it's going to Elasticsearch. In our lab environment, we're going to send this to vRealize Log Insight instead in our lab environment. Before it sends the logs out, it's going to add the following metadata. It will add this information into the log entry, so when we get to our logging backend system, we can now query based upon pod name, query based upon container name or the namespace that it's in. A little bit about this. This FluentBit is a lightweight log aggregator. As you can see, it's written, it uses a very little bit of memory. It's designed for very high performance. Okay, so it was written in C. That's what makes it lightweight and very fast. You can see the rest of the features that's available from it, and it's coming out of the FluentBit project, which is an open source engine, and you could see some of the details architecturally, if you're into that, on how it's actually able to do its job so efficiently. So that leads us to another question. Where do I put my logging backend? Where should it live at? Do I want my logging backend inside the cluster? Well, then you're only using it per cluster. This is my logging backend. This would be my syslog server, my, vRealize Log Insight, my Splunk. Or should it live outside of the cluster? Standalone. Guys, there's not a right or a wrong answer here. It depends on your design. We don't care. At the end of the day, for us, this is an IP address and a port number that I'm sending data to. So you need to be thinking about where that is. Or do you want to use a third-party service? There's a lot of cloud offerings that do a great job of processing your logs. As you can see, with vRealize Log Insight, we can pick up the logs and make those logs available for both the application and developers and the application owners, as well as for the platform reliability or the SRE, the engineer, right? The app people are going to want more app-specific logging. Us, as a site reliability engineer, we're going to be looking, I need to see this stuff from the infrastructure. I need my vSphere logs. I need my vCenter logs. I need my ESX host logs. I need my vSAN, right? vRealize Log Insight can accommodate both. So he can do application logging, per application only. He can do the logging with Sidecar, at the pod level. He can do it via daemon set. So those are the different scenarios. You can implement whatever style you want, still using the FluentBit to do that for you. If I want to get out of just the application logs, right, I have my worker node, which is also a host operating system. I could install node agents on my worker node and on my control plane nodes to get OS related logs out of them into vRealize Log Insight. Okay, so think about it. There's other logs that might be important from the control plane nodes as well as my worker nodes, just not my application. Well, think about, what depth you want to be able to see. So the Kubernetes logging integration with vRealize Log Insight would aggregate, tag, and ship all the logs to the Log Insight system that I'm going to want. Things like control plane worker nodes, the Kubernetes cluster events, the standard pod standard out and standard error logs. That's what we're already getting from our applications. So that means inside vRealize Log Insight, I could have searchable tags for a specific Kubernetes cluster, a pod, a namespace, a container. It does do encryption before it sends the data over if you turn it on, and it can do log ingest rate limiting. That's part of vRealize Log Insight. We can implement that if we've got really a lot of logs going on. So this integration happens through our Tanzu offerings. So that's one of the things about the Tanzu offerings is it's going to automatically set up getting the control plane, the worker nodes, and the Kubernetes cluster events logs into Log Insight. If you're spinning it yourself, you would have to manually set up the node agents of FluentBit on these respective nodes. Choose a Tanzu product, it's done for you automatically. So, some components, as you know, don't run as pods. They're, an additional service that's going on, let's say on my control plane or on my worker node. So Kubelet does not run it as a pod, right? The container engine's not running as a pod. It's an actual process running on the worker node. Potentially etcd is not running as a pod. How would you need, and what are their logs? Well, to get those logs, this is where you would have to implement some type of system component level logging. You can add your favorite agent, and you would need to add it to your machine setup if you're setting up the machine. So this is more of a do-it-yourself type of thing. So if you're DIYing your Kubernetes cluster, you would need to be aware of that, okay? You would then use the host operating system to do log rotation on whatever your container and whatever your worker or your control plane node is. Again, if you're using Tanzu product, this is automatically set up for you. The event messages out of Kubernetes, right? Remember, you can do a kubectl get events. So if something's happening inside Kubernetes, let's say you're draining a node, so that means pods are getting term sigged and they're getting rescheduled somewhere else. That Kubernetes related tasks that are going on show up in your Kubernetes events. They're only around for 60 minutes by default. Yes, you can increase the number, but you don't want to go crazy or you're going to bog down Kubernetes. What do you need to do? You need to get those event messages and you need to stream copies of those event messages into some type of external system for long-term storage. We need an audit trail. What happened, right? Inside my Kubernetes. So both the event messages that triggered, and then also we're going to talk about the audit logs as well, so we can know who actually invoked something. Here's the audit log. So on my control plane nodes, if somebody over here does some kubectl command and they send the kubectl command to the API server, right? What did they send? What time? Who was this person that told it to, scale the number of replicas to 20? Okay, so the audit log is going to track all the user and component access that they're accessing. We probably need to get the audit log also shipped off into our backend logging. So we've covered a lot. There is probably a lot more logging going on here than you probably first imagined. Hopefully it all made pretty good sense to you. Now, when we created our Kubernetes cluster, when we activated it, we did a kubeadmin init command. If you want to get the audit logs, you would remember when we did our kubeadmin init, we added a dash and we said something like pod network cider equals something, right? And we said API server advertise. We added these dash parameters. That's how and you can only do that when you're building your Kubernetes cluster, okay? If we want our audit logging, these would be the additional -- arguments you would need to add when you do your kubeadmin init. If you don't specify these, you would need to consult your current build that you're using of Kubernetes to find out, does it have a default value? Does it create an audit log by default somewhere? Or if you don't include it, does it not do any audit logging? So if you want the audit logging, you would have to include these. And again, this is if you're doing a do-it-yourself Kubernetes spin, which that's what we're doing inside class. So where it leaves us at this point in time is a chance to go play with the logs as well as vRealize Log Insight. So the lab's pretty straightforward. You're going to first log into Log Insight. Make sure it's working for you in the lab environment. Username and password are all inside the lab guide. Get a feel for it. Then what are you going to do is you're going to actually go ahead, review and apply the FluentBit configuration. So we're going to add FluentBit logging to our Kubernetes cluster, which would mean if our Go web application is sitting inside there, we should start to be picking up logs now from the Go web application. Okay, so go ahead and get that up and going, and then you're going to circle back into Log Insight, look at the dashboard, and take a look at the application logs. A little heads up, the time between here to here is going to be around 5 minutes, so you might need to give it a little bit of baking time before you're going to be able to query the logs. So go ahead and enjoy them, and I'll see you when you come back from doing your lab, and we're going to go ahead and continue into our next module, which is going to be Lesson 2, Monitoring in Kubernetes. So I'll see you soon. Hi, and welcome back. Let's go ahead and continue with our next lesson, Lesson 2, in the operating section of the Kubernetes Foundations and Cluster Operations class. So we're going to, again, it's about monitoring a Kubernetes cluster. And this is something you would have to consider as you evaluate the best solution to help you operate your Kubernetes cluster. So we want to talk about the different monitoring solutions that are available and how would you go about implementing that solution inside your Kubernetes environment. So when we're looking at our monitoring goals, here's some questions you've got to ask yourself. First of all, can you define when you look at a Kubernetes cluster, what would be considered a normal state of the cluster and what would be considered an abnormal state? For example, if I looked at my Kubernetes cluster over a period of a week and I said, listen, the majority of the time, my worker nodes rarely exceed 50% of CPU usage, and maybe they're consuming, 50% of the available RAM. Now, suddenly, you look at your cluster because you're getting complaints, and you start seeing your CPU load is sitting up at 80%, 90% at times. Your RAM, maybe you've used up all of it, 100%, right? Realize each cluster normal is going to differ from cluster to cluster, based upon the regular scheduled workload on there. And once we know what's normal and once we know what's abnormal, we'd be probably wise to set up whatever our monitoring solution is using some type of alerting system in our monitoring solution that could send us proactively an alert to say, listen, we've just gone to an abnormal state here. Now, it doesn't mean my applications are down, but I've defined the parameters of what is normal. When we're looking at monitoring, what would be the relevant logs that we would want to be, monitoring? Could it just be the same logs that we just talked about in our previous module, which was our logging? Maybe we're just going to go after those logs. Some monitoring and logging solutions do integrate together. So that would be something you would also want to evaluate. So when we're looking at monitoring tools, one of the things you've got to consider as you look at this slide is really what are you trying to observe and really what is each person's respective role, right? So if I'm an operator, I'm going to need to see all the way, potentially, again, it depends on what, the scope of my role is. Do I need to see all the way through my hardware, and maybe my boundary ends at once I get Kubernetes operational? Is this the range that I'm interested in monitoring? If I'm an application developer, I'm going to maybe be up at the very top stack up here saying, I need to know how long and what's, the typical latency for me to go from one microservice to another microservice, etc., through my application, because somewhere inside there, one microservice is maybe adding that delay that's causing me to get some complaints. So as you could see, based upon the layered scenario that's going to comprise your Kubernetes cluster, it's not potentially this is the best tool. It's where is the focus at of what you're trying to observe. So Tanzu observability, which we're going to cover what that does, that's really at the higher end of the stack. Is Kubernetes itself struggling? That's where maybe a tool like Octant that will show you could come in. And guys, these are not the only ones. We're going to summarize other potential tools. We could go over monitoring tools for a couple hours if we were going to talk about each one. We're just picking a few out. And then, of course, we've got our, if we're a vSphere shop, odds are pretty high we're probably already using vRealize Operations Manager. You could see he covers quite a bit of space that he can give us insight into. So let's start hitting each one of them. How would you go about and do the Octant dashboard? And remember, Octant's going to be really focusing from Kubernetes up through the containers slightly into your application stack. First of all, it's a free tool. You can go ahead and get Octant software at the URL that I've listed there. What you need to be able to do is you're going to install the version that matches your platform. So if my laptop is Windows, I would download the Windows version of Octant. I need to make sure that I can connect to my Kubernetes cluster using the kubectl command. If I could kubectl get nodes to the cluster I want to monitor, then what do I simply do as I simply run the Octant command? The Octant command is going to use my kubeconfig, which my kubectl's using. It will connect to the Kubernetes cluster, and boom, I'm going to have an interface to allow me to observe things inside my Kubernetes cluster. This is what the Octant dashboard looks like. And from here, it's a web-based UI. You can do more than just monitor. You can actually deploy stuff from here. You notice there's an apply YAML. So if I've got a YAML on my desktop, I can hit apply YAML here and actually apply it to my Kubernetes cluster. You notice I could switch my namespaces. I can even switch my TKGI clusters. If my kubeconfig says I've got access to different clusters, I can right here do the equivalent of changing my context. You've got a drop-down menu over on the left-hand side where we can look at applications, namespace overview, cluster overview, and I can install plugins. And some of those plugins would actually show me interrelationships between containers. And if I was wanting Antria, I can actually install the Antria plugin and get more details about my networking stack. It's a great tool. It has its pros and cons. You're going, again, depend on where you're trying to monitor in the stack, but it's a great free tool right in the middle of the stack, real quick and easy to deploy it. We're going to go ahead and play with this in our lab environment. You can see some additional screenshots here as I start to move through it. I've switched over to my applications. I clicked on the workload section over here, and it's showing me my various workloads inside here. Green, good. Yellow and red, probably bad, right? Now we transition over to our next guy here, which is going to be VROPS. Okay, so what can I do inside vRealize Operations Manager? Well, it has an extension that we can add to VROPS to allow it to see Kubernetes clusters. And then I could select a particular Kubernetes cluster down here. And then over here, once I select it, this is wired to this. So whatever I select over here, this is going to come up and say, for that cluster, you've got 2 nodes, 2 namespaces, 18 pods, 28 containers, and 10 services running. And as normal behavior in VROPS, as you keep drilling down, if I select like a series of nodes here, additional portlets, they're actually interwired together, start to update. So I can see my relationship between objects. The biggest beauty of VROPS, if your team already knows VROPS, there's like very little learning curve then to implement VROPS to manage your Kubernetes clusters. Okay, so you can see the picture keeps going on. What are we looking for here with monitoring? Red bad. We need to find things out. What's going on? What's wrong? So VROPS has the ability to do key performance indicators. It's a single monitor that I can monitor both my Kubernetes clusters as well as all my infrastructure running my SDDC. I can have VROPS has the ability for me to find alerts. So going back to what's normal, what's abnormal, when I get to abnormal, send me a message ahead of time so I'm alerted about it before the ticket's even open. So it's being much more proactive. There is the entity relationship. So you can see here, he's kind of forming an entity relationship between what I'm looking at, what's maybe some of the physical stuff beneath me, what's the stuff above me that I'm actually running. He has as typical VROPS has capacity planning. He could basically tell you from past history, as you keep putting more containers and pods on this cluster, he can project forward when you're going to run out of CPU and RAM on this respective Kubernetes cluster. This particular product, super easy to integrate with TKGI. Okay, it's just literally a checkbox, put in a few fields, hit OK, and then anything TKGI deploys will automatically show up inside VROPS. The other Tanzu solutions have their own small sections, but the installation isn't, I'm going to say, as straightforward and simple as TKGI, but by no stretch of the imagination is it hard. It actually goes pretty quick. Here's some more screenshots when you look at it inside VROPS. So you got a real quick dashboard that we can go to when we select our dashboards here. What am I looking at? I'm looking at the top 10 nodes by memory usage, the top 10 nodes by CPU usage, the top pods by memory and CPU usage. So I can identify basically who are my hogs in my environment. Right? Who's right now more committed to running pods on them from a node perspective. Also inside there, as you go a little bit further inside here, you can look at, key node metrics as I'm looking at a particular node. So we've drilled down a little bit, deeper inside here. What's my utilization index? You can see this guy is pretty utilized, 100% utilization index. Right? If I select something, it tells me here the host it's running on, the kubelet version it's running, the OS version that is actually running that particular container, that particular worker node. What is it running? You could see inside here, this host name, this worker node inside here, what all is it running? And you could see down here, here are all the pods that it's running. And I could see I've got a pod here that's sitting red. And again, as I keep selecting things, these things start interwiring together and I could see what's going on, my memory usage, CPU, disk, IO, read, etc., as it's going up and down over time. So a few more pictures to go through, what are the least healthy pods, pre-built dashboards to show us stuff. Why is it unhealthy? We can start digging through what's going on inside of it. And the typical VROPS dashboard that, if you've used VROPS before, this is a very common one. It's a very early on dashboard that comes up. Real simple approach, green good, red bad. So I can immediately take a look at a Kubernetes cluster and say, wow, I've got, a bad Kubernetes node. red. That's really truly in an error state. The orange and the yellow, okay, something's wrong. Maybe that red could be spilling problem over to the other ones, right? I could see that problem looks like it's isolated down to a particular namespace, right? I can just click a pod here and get details about why is this pod in a red state. Same scenario you would have in a vSphere cluster looking at VMs on it, okay? So it's following the same paradigm. So with that, what we're going to go ahead and do, and we're going to take a break in a second, but before I do that, I want to go ahead and make sure you understand something when you're looking at a monitoring solution. And that is, as you scope out the different types of monitoring solutions, you've got to realize that, and sometimes if the monitoring solution is pulling information out of the environment it's monitoring, and it's doing that at what time interval? At what time interval is it doing that? I could be looking at stuff that's 15 minutes old. Yes, that's how it was 15 minutes ago. Depending on what this collection rate is or interval, you could be getting closer to real time, further away from real time. So it's going to be really up to the solution you choose, and in some cases, the collection interval that you chose. Some of them they're configurable. Collect my stats every 2 minutes, right? And it might be doing some averaging of those stats across the 2 minutes. He might get, let's say, 4 intervals. They're 4 30-second sampling. It's an average across a 5-second sampling in the 30 seconds that it's actually polling. So the intervals is something you would want to consider as well. So for right now, why don't you go ahead and stretch your legs, take a break, and when we come back, we're going to go ahead and continue on and talk about Tanzu observability before we get into our labs. Thanks. Hi, and welcome back from the break. So let's go ahead and continue with our last monitoring solution that we're going to talk about with again, a small amount of depth up to it, and that's Tanzu observability. Now, Tanzu observability, for those of you that have been tracking some of the VMware Kubernetes solutions, this used to be the product referred to as Wavefront. It's now called Tanzu observability. So all of the Kubernetes stuff has been rebranded or renamed with Tanzu and then something after it. Tanzu observability is a software as a service offering. Okay, so it's actually running up in our cloud environment. You actually install something locally on your environment. That collector is shooting the information up to our cloud platform, where the tool's going through all the analysis that it needs to start doing things like being able to alert you for that out of norm condition, being able to help you visualize it, troubleshoot it, predict and even automate solutions to your existing workload that's going on. So what's happening over here is the tool is actually able to do full stack collection. So we could look at applications, microservices, even serverless type of workloads on any cloud, doing containers, infrastructure, and even Internet of Things. So the collections over there, it's almost near real-time ingestion of the data. That data then is shipped up to our cloud platform. That's where the data then goes through all this, analysis that's going on. It's designed to scale to an extremely large number of data collection points, and depending on the granularity that you want it to be able to see, in some cases it will involve adding additional libraries to the developer's code. That would give us this huge, deep look as to what's going on inside the stack. Here's some additional, screenshots that you can take a look at it. Okay, so with it, you can observe. You can observe across multiple clouds. If you've got Kubernetes for some of the, enterprise people, multinationals that are going on, their app might be running, across multiple continents. They need to see what's going on, bigger picture. Again, observability has a way to do that. Okay. These items down at the bottom are, again, all of the features that you're going to be able to get out of the tool. So the big one for me is being able to visualize, being able to do alerts on, if the delay on my database, let's say, is getting above, 150 milliseconds. For me, that is an eternity. Something's wrong with my database. Maybe I need to scale it. I need to reindex. I don't know, but I need to do something. You could set up those type of alerts. So a difference between using this, and this is some stats that, the product is going to be using as, features or selling points inside here, is using the tool. The teams can do what? They can do 10 times earlier issue detection. They've got an 80% mean time to resolution of the problem. It's a single stack for them to view everything on. Again, 30% reduction in the tooling complexity using this tool across all of them versus individual for each ones. And again, I told you it's set up to do massive ingestion. It could do 500 billion data points daily. Okay, so it's a really optimized engine designed to optimize a lot of data points, pull them all together, show you the path through the microservices, and start giving us alerts on where things are experiencing some type of latency. Again, some additional dashboards just so you can get a feel for it. So across the top of it, once you're inside observability, you've got, this what a lot of us recognize as a tabbed interface. We can say, okay, show me namespaces. Boom, it's going to show me my namespaces. Here's my 4 namespaces. And then it's given me, a pod count by namespace, container count, memory usage. Another screenshot down here. Okay, so this is just 2 screenshots on one screen. I'm selecting my deployments. I could click at my deployments over here and see what's going on. Okay. Replica count per deployment. Okay, so I can see what's going on. Are all my numbers equal? Is my available and updated equal? That's what I want. Unavailable, not good, but as long as my available and updated are good, I know that Kubernetes is able to reconcile and bring everything into my desired state. Again, more screenshots, pods. I can take a look at what's going on with my pods. And then you've got the other ones to go through. I'm not going to bore you with each one. Each of these are just screenshots of different things. So here's the services. This would be my node port, cluster IP, load balancers, and even potentially I could be looking at my ingresses. Here's my replica sets that it looks like several of these were created from a deployment. So I could see what's going on. Is my replica set in its desired state? So I would suggest going back to the beginning picture that we talked about. There was 3 different sections in there. The very top section, which is very tied to the applications and the containers and down a little bit into Kubernetes, is where a tool like Tanzu Observability is going to look at. And it's designed to look at the detail that I really need there. VROPs down at the bottom from the hardware stack all the way up slightly into Kubernetes. Both of those are going to be fee-based solutions. Octant, free solution. It could see a little bit into the IaaS environment, so slightly below a little bit of Kubernetes, all the way up into my containers. It could see what's going on. Now, there's other tools, and I don't want you to leave here thinking that's the only thing there is. So there's a whole bunch of do-it-yourself stuff you could do. There's free solutions that you could look at. I've mentioned a couple inside here. There's also third-party paid solutions to take a look at. And depending on where you're deploying at, if you're picking an AWS deployment of Kubernetes or a GCP deployment, GKE of Kubernetes, some of them are going to actually come with their own monitoring solutions. So all of those are also pretty popular. I will tell you, as a paid service, Datadog is very popular. Okay, there's also tools like Prometheus that you'll see as well that you can be doing monitoring as well. So remember when you're monitoring stuff, some of the things you're going to have to deal with is how to interpret the data. What is normal? What is abnormal? And again, it's going to change cluster to cluster based upon the workload you task that cluster to run. So really, the absolute values maybe aren't so significant. It's more important about the trend. Is my CPU usage doing this? If my CPU usage is doing that, dude, I'm going to have a problem. It's just a matter of when. So some things that you would want to start looking at when you're looking at your, some of the statistics that you can get out of monitoring. What's the average time for a deployment of application X? If I have to redeploy it, what's the average time it should take? What's the disk utilization like of my worker nodes, etcd nodes, etc.? Right? What's the response time if you did a kubectl get pods? How fast is that coming back to you? If that's coming back slow, your API server's bogged down, which could mean your etcd database is slowed down, which could mean all of it slowed down because the control plane node isn't getting scheduled on the appropriate hardware it's contending for CPU. In some cases here, I need to see what my vSphere cluster utilization is like, because if the vSphere cluster that's running my Kubernetes cluster is slammed, my Kubernetes cluster is going to be slammed, right? We're running on top of infrastructure. So when we're looking at monitoring tools, it does help to see that view down into your IaaS stack, your vSphere, to see what's going on. So hopefully most of this is starting to make pretty good sense to you, and you should be able to, with the information we covered, make the appropriate decision for your company. So where that leaves us with is we want to conclude with reminding you about alerts. When you're doing monitoring and logging, is there certain conditions that when they occur, gee, if I would have known about that, I could have prevented this problem from happening. So pay attention to setting up the appropriate alerts. And remember, it's not a one and done. You will be constantly fine-tuning with your team over time. Additional alerts, changing the threshold for the alert, etc. Okay, so, you're logging and monitoring. You might be looking for something like, a deployment taking longer than, or error levels inside certain logs for an applications. Are you getting X number of 500 response codes back from something? All of those should be, variables that I could be using to send out alerts to alert me before the application goes down, before the help desk ticket is generated. I could go ahead preemptively take care of that problem ahead of time. So let's go ahead and jump into our monitoring labs. Lab number 13. We're going to go ahead and up till now, just so that we're kind of clear in our lab environment, we have our Windows, right? Student desktop. That's where we've been doing the majority of our work at. From there, what have we been doing is we've actually from here been launching an MT putty session, right? Over to our SA master, and that's where we've been doing most of our work. So over here via our SSH session, we actually have been running our kubectl commands. As you know, kubectl has a kubeconfig file that tells it where to reach the API server. So the first step we're going to do here in task 2 is we're going to need you to win SCP over, right here, we're going to do a win SCP. We're going to copy over the kubeconfig from our master node back to our Windows student desktop. Once you've done that, if you want to make sure it's working over here, open up a command prompt and go ahead and do a kubectl command, kubectl get nodes. Once you've copied over the kubeconfig, kubectl will now work directly on your Windows desktop. So we're going to install and start Octant. Octant here will be for the Windows distribution, right? And once it's installed and we run it, Octant's going to go through the kubectl kube config to actually reach over to the Kubernetes cluster, and you'll have an interface that you can take some looks around inside your Kubernetes cluster and look at the Go web app. So once you're done with that, we've concluded here our monitoring solutions and implementations inside Kubernetes, and that concludes this particular module. So I'll see you once you're done with that in our next module, in our final module. Thanks. Hi, and welcome back to Kubernetes Fundamentals in Cluster Operations. My name is Mark Allenbaugh, and we're getting ready to start our last module together about cluster operations, some additional things that you would need to consider. So, in order for you to be effectively be able to operate, I'm going to say really anybody's implementation of Kubernetes. This is not a product-specific concept. This is a concept that applies across whoever's Kubernetes solution ultimately ends up winning out to, for you to run Kubernetes on. So some things that you're going to need to know to successfully operate, troubleshoot, and maintain those Kubernetes clusters, right? First, one task that you've got to be aware of is you're going to have to add additional workloads and users to the platform. So that's an ongoing operation, right? Kubernetes is going to take off just like, virtualization did. It's going to suddenly go, we can just get new VMs, and you start spinning up more and more VMs, right? And we take off on that rocket ship. Same thing's going to happen in Kubernetes. You're going to start seeing more applications, more developers, more people needing access to it. How do you onboard them? Okay, so that's going to be an important thing. It is going to be important for you to get the skills in using whatever the monitoring tools are that your company decides to implement. So we should be familiar with how to look at the monitoring tool to help us troubleshoot potentially a particular problem area, or even give us a heads up to say, listen, in 90 days, I think we're going to run out of resources, so that we could start getting the right things in motion so that we can add more capacity, that physical CPU, RAM, disk, and networking that I'm going to be able to need to expand my cluster or even deploy new clusters. You're going to need to understand what all does a particular problem impact. Okay, so if something breaks, what will that impact? If a control plane node goes down, what's going to happen? So we're going to go over some of those things. We're going to talk about using kubectl, some additional commands that will help you check the cluster status and some of the details about the cluster. We can use him to also look at some of our cluster API logs and resources. We're going to need to talk about a very important piece for you to be aware of is upgrading and patching. What does the release cycle of Kubernetes look like? Okay, for most of us, this is, if you're new to Kubernetes and you're doing a new Kubernetes deployment, most people say, yeah, we don't do things like that in our company. Well, you're going to have to change slightly. Okay, there's no such thing as installing Kubernetes and just letting it be. You're going to be constantly upgrading and patching this thing, or potentially within 9 to 10 months, you've just fallen out of support. You did hear me correctly. You install something, latest version today, 9 to 10 months later, you're out of support. You're going to have to be comfortable doing upgrading and patching. And in order to do that comfortably, you're going to need to understand what a Kubernetes feature called cordoning and draining means, and what it could potentially mean to your application. Okay, we don't have vMotion here. So when we do a cordon and drain, is my application going to take a hiccup, or is it just going to keep on running? Well, that depends. So we've got 4 lessons we're going to go through. We're going to first talk about onboarding new applications or new people, both of them together. go over some things you need to be aware of and, plan for appropriately. Then we're going to jump into some more details about troubleshooting. We're going to talk about maintenance, where we're going to talk about how do we do upgrades, patches, cordon, and drain. And we're going to do a lab right down inside here. And then we're going to wrap the class up with a little more detailed going over some of the Tanzu portfolio and what each of the respective products do and why you would want to consider them. So let's go ahead and get started. Our first one here is about onboarding new applications, and I'm going to somewhat say also new people. So what information would you need to evaluate if the new workload was given to you to say, hey, deploy this on the Kubernetes cluster? Maybe a new developer's hired, okay? They need access to the Kubernetes cluster. How is that going to happen? What do we need to do? So as you can see, this is very much so about cluster operations is what we're about. So additional developers need access to your Kubernetes. What do they need access to the API server? That's the only way they're going to be able to use your Kubernetes cluster. So what do we need to start asking? Well, what type of account is this new person and how are we going to give them access? We really want to try to avoid giving them access as a user. I think we've all administered enough, IT systems. We know doing it a user at a time, that turns us then into that add, move, delete, grind that takes up a lot of our time. We'd be much better off to say, oh, they need access to the Kubernetes cluster. Why don't you just go ahead, add them to a particular group that we've already got set up? That would be the easiest way to handle that. Is their access going to mirror that of somebody else? Might or might not. Okay. In some cases, they might have their own namespace that is unique to them. And if that's the case, then yes, I am going to specifically give them access to their own namespace. Depends on how your company rolls. So if we're onboarding now most of this stuff that we were talking about here, you want to go back and read the module in the security module where we were talking about RBAC. So this is where we'd be doing stuff like roles, cluster role, role bindings and cluster role bindings. That's what we would be doing inside here. If that was already done and you just need to drop them into an AD group, there would be no modification to my RBACs. They're suddenly now a member of a new AD group. They would immediately then be able to authenticate to the API server and gain access to it. Let's talk about a new application or a new project starting. Well, they come with you and they say, hey, we've got this new application. It's the expense reporting system. We need it deployed inside Kubernetes. That's where they tell us it runs at. Or maybe it's an existing application that they're expanding. This is phase 4 of this application. We're adding this, and these features. Okay, fine. I get what you're saying you need. So we need to start understanding what specifically is required in this list. If it's a new application, what kind of network access it is. If it's a modification to one, is there going to be different types of network accessing? Does the pods that are running in the containers, do they need elevated privileges? Do they run with my normal security profile or security contexts? Or is there going to be a modification? What kind of resource requirements are they going to need? And this goes all the way down to CPU and RAM, minimums, maximums. What kind of storage are they going to use? Do they need a persistent volume claim? If so, I'm going to have to add stuff to my backup jobs. How many instances are they going to be running? What's their replicas look like? How many different deployments are there? Okay, all this is going to come up because at the end of the day, they're sucking up your CPU, they're sucking up your RAM, and they're starting to use your storage. We've got to be able to make sure that we've got adequate resources to do that. And certainly when they're hitting storage, we want to make sure that it's getting backed up appropriately. So how do we do those things? We gather the information from them, and then what do we do over here in Kubernetes? Well, we're going to have to start defining things. If it's a new application, I'm going to probably say, okay, I'm going to give the new application a new namespace. So maybe I'm going to segregate applications by namespace. That's a logical approach. I get what you've got for CPU and RAM. I'm going to go in and I'm probably going to set some resource requests and resource limits that I want to make sure those are being applied to each of their pods. I want to know the minimum for my scheduler, the maximum it should be using, so I can appropriately handle better scheduling of those respective replicas. If they're going to be using storage, that means they're going to be using a persistent volume claim. I'm going to want some details about that because that's what I'm going to need to be backing up. Do they need escalated privileges? Well, that's where I would be setting stuff in the security context inside the deployment. Number of pods that are going to be done, that's how many instances they're running. That's going to help me when it comes to scaling things out. Continuing on. Do I want to restrict the CPU and RAM? Do I want to restrict the object counts? You told me you were doing 4 deployments. You needed 2 load balancers. You needed, 4 cluster IPs. You were going to be doing 2 persistent volume claims. That's what you told me. Do I want to enforce this? This concept of a resource quota is some of the details that we're used to when we make a resource pool inside vSphere. Okay, it's kind of like it. Okay, but we don't really care about how many VMs they're running. When we do my resource quotas, I can actually put details down on the object count. So I will go ahead and say it to you. I think the resource quotas that we do inside Kubernetes is much more granular control than a resource pool inside vSphere. So when I'm creating a resource quota, we're going to race through a bunch of them. Here I'm doing a resource quota for compute resources. So what am I saying? They could do 4 pods. They have this amount each pod can do 1 CPU, 1 gigabyte of RAM. I'm going to limit what they can do to 2 CPUs and 2 gigabits of memory. So this is a hard limit. When I sum up all of their pods that they're deploying in this namespace, I've taken the resource quota, I've applied it to the namespace. If they try to exceed this, their pod won't get scheduled. You've reached your max. Here's another one where I'm doing individual counts. So I'm actually saying, listen, you could only do 10 secrets. You could only do 10 services, 2 load balancers, right? How many persistent volume claims? How many config maps? So again, I would write the resource quota, apply it to the namespace where the application is, and I'm setting a ceiling to say, you can't go above this. I can also do a pod security policy. Okay, it's optional, but it is recommended. So I could put this pod security policy up, apply it to the namespace, and I'm saying inside here for what would ultimately be defined in the pod as a security context, I'm putting what are the allowed parameters. Okay, are they allowed, for example, to run as root? I'm saying no. If you try to schedule a pod and you say you were going to run as root, I've got a must run as non-root, your pod's going to get rejected. It won't be allowed to start. And you could see the various other settings that we could tweak inside what's going to be allowed inside the security context. So additional Kubernetes objects to think about for network access, right? That's where I would want to have an appropriate network policy controlling what pods can talk to what pods, what can come in, what can go out, right? For the people that are going to be playing with this application and accessing my API server, I would do my appropriate role binder or cluster role binding if it's unique to a namespace. Setting my limits again, I would go through and use the resource quotas that I could set CPU, RAM, number of pods by doing counts in the resource quota. I could set my pod security policy to make sure they're not violating an elevated privilege request. Now, one of the things that you're going to want to start considering is doing some type of template or script, because what's going to happen once you get your Kubernetes environment up and running, and then somebody comes to you and says, hey, we got a new app. Okay, fine. You ask all these questions. You do the appropriate things. We talked about all the respective objects that need to get created. What's going to happen right behind that? Somebody else is going to come into the office and go, hey, I got this application. I need it deployed. Again, you're going to have to create those respective objects. So you might want to start thinking about doing some type of namespace templating. So some script that you can run that maybe I create a namespace, I run this script, it creates, makes appropriate copies of all the appropriate objects, manifest files that I need that I could start going in then and editing. Okay. So also, you're going to want to think every time you're deploying a new application, labels for that namespace. Everything that's getting deployed, should it have an appropriate key value label pair that's identifying it? So I can do labels on the namespace, my network policy, my role bindings, my resource quotas, all of those things I might want to consider, because a lot of those we're going to be able to filter out what's inside my Kubernetes by doing kubectl commands, and I could actually select based upon a label value. I can do reporting off of label values. So think about your namespace templating as well. So this finished our first lesson. Hopefully most of that stuff kind of gave you some food for thought, and that's all we were looking inside here, is just calling additional considerations that you need to be aware of. So why don't you stand up, stretch your legs, take a break, and when you come back, we'll get into lesson 2, and we're going to talk about cluster troubleshooting. Thanks. Hi, and welcome back. Let's go ahead and continue with lesson 2, where we're going to talk about cluster troubleshooting and some things that you should be aware of as you operate your Kubernetes clusters. So first, we want to go over what specific kubectl CLI commands could you use to query your Kubernetes cluster for things like resources and logs. Now, some of these commands we've already gone over. We're also going to talk a little bit about some common Kubernetes cluster problems that you can see as you operate your cluster. So a quick divide and conquer when it comes to troubleshooting. What kind of problem is it? Think about it. Is it a cluster problem or is it an application problem? If it's an application problem, then typically it's going to be relating to pod problems that I'm going to say the owner of the application should be able to resolve. I don't know if it's code inside their application. To really troubleshoot that application, you're going to have to be very familiar with it. And if it's a cluster problem, they're not going to be able to fix it, because that's going to require some type of administrative privileges to get into the details of the actual cluster. A regular, let's say, application owner is not going to be able to do certain commands against the Kubernetes cluster. If it is a cluster problem, you're going to probably see multiple applications would be affected by whatever the underlying cluster problem is. So, for example, if kubelet's down on a particular worker node, it's not going to affect a single application, it's going to affect multiple. So the next thing you want to try to think about is, how is that problem typically discovered? If a user is going to report the problem, could ideally I have a monitoring system that's actually sending me an alert about something? So as you look at the stack that represents my Kubernetes cluster, as you can see up till here, These are the 3 layers beneath my Kubernetes cluster. I could have a virtualization problem. I could have a hardware problem that turned up. My Kubernetes layer lives on top of whatever type of provisioning system that I'm using here. If it's inside Kubernetes, it could be related to a problem anywhere in the layers beneath it. So you're going to probably want to see, where is the signal coming from? If I've got a monitoring solution that's firing an alert to me to say, hey, all the worker nodes are sitting at 85% CPU utilization. Yes, my worker nodes are sitting here in my Kubernetes layer. However, down here is where they're getting their CPU. Do I have a vSphere issue where for some reason my vSphere cluster, if I check it out and it's sitting at 80-90% utilization of CPU, I might be overcommitted. So it kind of helps to identify the layer it's at. Anything above the Kubernetes layer of the infrastructure, that's where we're going to be getting into our pods and our containers that are running there. And those are the things that are actually providing what the user sees, their respective application. So some guidance when we talk about troubleshooting. First of all, establish as many alerts and dashboards as possible so that we can be alerted when certain situations arise. Secondly, be familiar with where you're going to actually go look at. Am I going to look at a dashboard? Know how to get there. Am I going to use a kubectl command? Great. What are they? What's the context I need to be in to be able to see what I need to be? If it is a node-specific issue and you're able to isolate that, then the first thing you're going to want to do is you're going to want to remove the workloads from the node and then debug what's going on with the node. Now, we're going to cover how to do that removing in our next lesson that we're going to go over. After you've successfully resolved the problem and you said, oh, this is what happened, and yeah, we didn't get an alert for it, determine if a new alert or potentially a new dashboard should be created or potentially modified to include those additional conditions so that we could more quickly resolve the problem, or even better, be alerted that the problem's occurring before we even get a report from the user. So another aspect you can look at when you're doing troubleshooting is determine the impact of the problem. Okay, so you're going to ask some things inside here, is the control plane offline or down? Well, can you do a kubectl command to it? If the control plane kubectl doesn't reply, your API server's down. What is working? Are my applications working? Your entire control plane can be down and your applications can all be behaving perfectly normal. Right? So it's going to help to understand, what's the impact of the problem? What are you seeing aspects are broken versus what are you seeing working? Can you get into your logging platform and begin searching inside there? I would say, what is broken, right? So the 2 big questions, what's working, what's broken? If deploying or changing an application, if I'm trying to do a kubectl apply with the deployment file that has a new version of my application and it's not deploying, that's going to start to show me where the problem is. Am I recovering from a node failure? Real quick one, do a kubectl get nodes. If you do a kubectl get nodes, the last column is telling you how long that node's been up. If you're seeing that's been up for a minute, oh, well, that problem that just happened is because the node got restarted. What caused that? Is something unreachable, right? Is the container runtime unreachable by kubelit? Is it up? So how are we going to explore some of those, some of these questions and answers to get answers to them? Well, the first thing we could do is certainly do our kubectl get nodes, right? My kubectl get nodes. And as you can see here, I'm showing you the age of the node. If the node was restarted, it would have a very, young age attached to it. Are they all in a good status? Uh-oh. Looks like we've got the second one here. This worker is showing not ready. Now you'll notice he can be running, but he's showing is not ready. So what are we going to do now? Well, the easiest thing we could go ahead and do is describe the node. Do a kubectl describe on your node and get more details about it. At the very bottom of it, you're going to see a section down here that's going to be the information that we're interested in. Where's my CPU sitting at? Well, 12%. Okay, that's my request. That's what my requests are. I don't really have a lot of it in use right now. If I want to see who's using most of it, I could see it right here. There's the pod that's running in a respective namespace. It's one of my Calico pods that are running out on this particular node that's using up 12%. It's requesting up to 12% of the CPU that's available. Be familiar with the conditions up here, okay? False is not bad in everything that's sitting here. Network unavailable, false, good. Network unavailable, true, bad, right? So you might want to go through and be familiar with what is a good and a bad state. I could certainly down here, it's showing events as none, but there's typically down here a series of events that have happened on your node. That would give you a little bit of a telltale of what to look at. And guys, that's pretty much the ending of some general troubleshooting. I could go ahead and just say, there's more commands, but there's commands that we've already gone over. If I think something is wrong with this particular pod, then remember we've got our kubectl logs command to go fetch the logs of the pod. Now in this case, it's in a different namespace, so you're going to have to do a -- namespace, right? And specify that the namespace equals, what's it in? Cube system, right? And then I could go off and fetch that Calico pod logs to see if there's something inside there to help me. So that kind of wraps up some of the commands that we could use, and also a little bit of the methodology of where to look at. Where's the problem at, maybe which layers it's coming from, what all does it affect, what is broken, what is working, to help you pinpoint where the problem is. So why don't we go ahead and again take a short break, and when we come back, we're going to go ahead and talk about cluster maintenance, and there's a lot of good information inside here that we are going to need to be aware of. Thanks, and I'll see you when you get back. Hi, and welcome back. Let's go ahead and continue with lesson 3, where we're going to talk about doing cluster maintenance. So, what kind of maintenance would we be doing? The most common maintenance we're going to be doing is doing some type of upgrade or patching to our Kubernetes cluster. So before we can do that, you need to understand what is the Kubernetes release cadence. How is new code being released? And this is where it's going to be a little bit of a change that some organizations aren't prepared for. Kubernetes releases and the frequency that you're probably going to have to be updating your Kubernetes cluster. Lots of enterprises are, once we install it, we do, 2 times a year updating, or once a quarter or something type of updating. You're going to find this is a quick cadence that you're going to have to be familiar with. Now, if we are going to be doing patching and updating, we're going to have to understand what is a Kubernetes drain and accordant feature, and how do they affect, most importantly, my production workloads. For a lot of us, we've become very comfortable with doing maintenance on our ESX hosts, because for us, it's a real simple, put it into maintenance mode, vSphere, DRS, vMotion, boom, all the VMs get vMotioned, 0 downtimes, right? And we could go off and patch and maintain our ESX host, do a flash BIOS, do whatever we need to do, bring it back online, and our applications don't know any different. That's not going to quite be the way it works when we're talking about our workloads inside our Kubernetes environment. So we're going to need to talk a little bit about that. We're going to actually do a drain in accordance so you could see what it looks like inside Kubernetes. And then we're also going to do a lab on doing a cluster backup. Show you some tools that are available. It's not the only tools, but it is a tool that you could use to actually back up your Kubernetes cluster. So the first thing is the idea of the Kubernetes release cadence. The Kubernetes release cadence, as the icon's trying to show you here with this person running, it is at a rapid pace. When you're looking at a Kubernetes number, it's comprised of 3 different numbers. It's the major, which is anything to the left over here of the period. So we're in major version 1. Our minor version here in this illustration is 15. Now, just to let you know, we're up to 22 right now. Then there's a patch version that's sitting over here. So remember, any vendor solution that you're using for your Kubernetes deployment is getting Kubernetes from the Kubernetes project. So what's available for me in the Kubernetes project? Well, the Kubernetes project is going to maintain release branches for the most recent 3 minor releases. Minor releases are happening every 3 months. So that puts us into, if we look at a timeline, a kind of interesting dilemma that we're going to have to deal with. Let me clear the feedback and let's walk through this together once so that we can kind of understand what's happening. If I went ahead and I did a timeline, let's say I drew out a timeline here. And let's go ahead and say that here in the timeline right here, I decided to deploy 1.15.5. And let's say that's the latest version available of Kubernetes. I'm running the latest and greatest right now. 1.15.5 is the latest. Now, that's not true, but let's, for this scenario, say it is. And let's go ahead and say that here's the 3-month window. So right here is when 1.15 as a minor release got released. And then from here forward is 3 months. This is my 3-month when Kubernetes is releasing new versions. So what's going to happen? Here, 1.16.0 is going to get released. And then just to stay here, so I can just keep drawing 3 months lines, 1.17 gets released here. This is another 3 months, right? And then we're going to go ahead and say another 3 months out here. 1.18.0 is getting released, and there's another 3 months. Per the Kubernetes project's rules, they're maintaining release branches, right, for the recent 3 minor releases, which means right now they're maintaining 1.15. They'd be maintaining stuff behind, but let me just move the timeline forward so we can focus on what we're trying to illustrate here. Here would be the 3 minor releases that when I get to here and whatever the timeline is, they release 1.17. They're saying, okay, we're going to support 1.17, 1.16, and 1.15. That's what they're supporting. So through this period of time inside my Kubernetes project, through this period of time, my 1.15 release is being supported. They're maintaining 3 releases, and they'll continue to maintain those 3 releases until I reach here. Once I reach here, once I get to this point of the project and 1.18 is released, my 1.15.5 is no longer going to be supported. Well, here's 3 months, 6 months, 9 months. When I get here, if there's some, vulnerability, problem, program, bug, or whatever in 1.15, Kubernetes project is not fixing that. So it kind of opens some eyes here so that people understand that you're going to have to be doing pretty regular maintenance to your Kubernetes cluster. And let's move forward and talk a little bit about that. Okay, versioning, right? What's acceptable for me to do an in-place upgrade with? Well, I can do an in-place upgrade from 1.13 to 1.14. I could go from 1 minor release up 1 minor release. I cannot do this. This is not allowed. You have to go from whatever your minor release is plus 1 to the next minor release. Downgrades are not possible. And when you're upgrading your components, you're going to upgrade first your control plane nodes, and then you're going to upgrade your worker nodes. That's the order of the upgrade. Now, we've got tools to help do this. And you also got to think a little bit about, which style of upgrade do you want to do? Do you want to do an in-place upgrade? A lot of shops are going to favor that. It's the traditional approach. It uses the existing installation and the machines. If problems arise, though, they can be difficult to mitigate those problems because you've kind of started your upgrading your cluster, and if it fails somewhere partially way through it, you're partially upgraded. So it in its own regards has its own pros and cons for you to consider. We could certainly do a forklift upgrade. So what do is we create a new cluster with new versions, and then what do? We migrate our workloads over. Difficulty ranges, okay? It ranges on what the difficulty factor is there to migrate your workloads over. Okay, there's load balancers that would potentially be recreated. They're going to get new VIPs, new IP addresses. We got to re-advertise stuff in DNS, right? How am I going to move over my persistent data? Okay, each style has its own respective pros and cons. I want whatever you decide to do, I need you to understand the Kubernetes commands that you would use to aid in either case. How would you go about doing these upgrades? A forklift does promote a multi-cluster deployments, which means if you're doing a forklift style upgrade, you're spinning up a second cluster, you're migrating stuff from the first to the second. It's not uncommon, as I said at the beginning of the class, to end up with multiple Kubernetes clusters. You can perform validation on the new cluster and on the new version before you deploy your workloads over there, so that's good. If I was doing an in-place upgrade, how do I know my apps are going to run? Well, hopefully you deployed a new cluster with the new version, you tested it there, then you reverted back and did your in-place. So Tanzu upgrades are going to automate quite a bit of this for you. Okay, so just so you can kind of understand, if you're doing a Tanzu upgrade, if you're running vSphere with Tanzu, how does that upgrade occur? Well, it's actually done through the vCenter server upgrades. So that particular solution might raise a little bit of eyebrows. It's like, why are we so frequently now upgrading our vCenter? We used to only upgrade it when we had a critical patch or whatever. Why are we suddenly constantly upgrading our vCenter? Because that's how we upgrade our vSphere with Tanzu deployments. Some people running vSphere with Tanzu, just so you know, will sometimes deploy a separate vCenter just for those Kubernetes vSphere with Tanzu deployments. TKG upgrades are done through a content library, and then you would do a simple kubectl apply to apply that to your TKG workload clusters. TKGI, it's done through an actual product version upgrade. So those products were worth mentioning so you can understand how the upgrades are performed. Now, regardless of which platform you're using, what's happening underneath the covers is the thing you need to be aware of, because they're all doing something underneath the covers, and what they're doing is they're actually calling upon Kubernetes features, commands, to invoke the upgrade. So what they're going to be using underneath the covers is a cordon and a drain command. Now, just like vSphere maintenance mode, what a cordon feature does, which when applied to a worker node, is going to tell the scheduler, don't put any more pods on me. I'm trying to go into some type of maintenance mode. So when you cordon something, it's the equivalent of vSphere host entering maintenance mode. So DRS won't vMotion anything to it. You can't power on a VM on that host. It's basically saying nothing new. So once a host has successfully been cordoned, which will happen pretty quickly and easily, there's not a lot of stuff it has to do. It just basically annotates something on it, taints itself, and says, don't coordinate, don't schedule me anymore. The next part is, here's my worker node that I first cordoned. So I says, don't put any more workload on me. But you'll notice he's got 3 pods already running on him. The next function we're going to need to do is we're going to need to drain it. Drain it is basically saying, get the pods off of me. So when a node is drained, we're instructing each of the pods and the containers that are running inside those pods to terminate. Now, here comes the billion-dollar question. What's going to happen to my application? What's going to happen to my application? Your application might experience an outage. What's it going to depend on? It's going to depend on the number of replicas. I've got 2 of these pods running. They're a replica, which means I probably have a service or a load balancer in front of it. So my service or my load balancer that's sitting up here is knowing to distribute workload to this pod or to this pod. Well, when I drain it, what happens? I tell this pod to terminate, to go away. My application can still stay up because traffic can come through and go to this other pod. Now, if you're looking at this drawing, you could see that the blue guy has 2 replicas. He should be good, but my green guy looks like he's only got 1. Well, when I terminate him, what just happened to your application? You just experienced an outage. So what's happening as we told all these pods to drain and go away, right? The deployment is looking and saying, I'm supposed to have 2 of the red ones. So what does he do? He reschedules him to run over here. My service just says, oh, it's now deployed over here. My service, which was up here at the top, now sees he's available and can load balance to them. My blue ones would in turn, get rescheduled somewhere else. The service for those 2 would work. The green would come back online and the application would be back available. But what kind of outage did you experience? So the real moral of this story is, pay attention to the number of replicas that you have running. 2 would be the absolute minimum. Most people are saying replicas of 3 is the minimum that they want running to make sure that their application is highly available. And then finally, we're going to jump in when we come back from our break and talk a little bit about what we would need to do for our backups. So let's go ahead, take a short break. This subject's going to go on for a little bit, and when we return from our break, we'll dig into the backups. Thanks. Hi, and welcome back from your break. Let's go ahead and finish this lesson 3 talking about cluster maintenance and operation type of functions we would be doing to our Kubernetes cluster. Certainly backups are going to be something we need to discuss. So the question is what really elements need to be backed up? You've got things like resource definitions inside here. We've got our deployments, we've got our services, our config maps, and so on. Do these actually need to be backed up? Because the question's going to come down to, those are a bunch of YAML files, and are those YAML files checked into source code control? Is your source code control system being backed up? If it's being backed up, do I necessarily need to back up those resource definitions? Do I need generated events? Things like events, any type of augmented fields that is going on inside Kubernetes, things that are actually realizing some state because they're running. Okay, maybe those might need to be backed up. Certainly my persistent volumes, that's my data. This is going to be the big one that there's an absolute no debate on that. And we're not even going to cover how you back that up. That's data that's being written somewhere out to your storage. You're going to have to figure out what your storage is and what backup tools you have to back that up. Do my secrets need to be backed up? Again, those potentially are nothing but another manifest file. Do they need to be backed up? Are they actually being generated for me out of some system like HashiCorp's Vault? Is it actually generating the secrets for me? And I could very easily just go back to him and say, reproduce those secrets and reapply them. So really, how much backing up's required? Your stateless workloads, if I've got the deployment file on them, I can just redeploy them. Now, the question really is do you know what files need to be deployed? That's the bigger question. Your stateful applications, absolutely. Those are going to need to be having some type of backup. However, do I just need to be backing up the persistent data? And then I could easily just read kubectl apply my stateful sets or my deployments that are using my stateful data? They're all good questions, and we can't give you a definitive answer. Okay, we can't give you a definitive answer. You're going to have to make those decisions based upon your environment. I'm just pointing out some things that you need to consider. Now, when it comes to doing backups, you've got a couple of different options. My whole Kubernetes cluster desired state is sitting in the etcd database. That's the desired state that I want. So you could use the built-in Kubernetes tools to actually back up the etcd database. There's some pros and cons to that. Yes, the tool's been built right into Kubernetes. I can use that tool. It does require access to the etcd server. It's low level, very manual. Restoring is not controlled or modifiable. You're just simply doing a restore. It's going back to a very specific state, the state you were at when you backed it up. There's another tool you could use, which is kind of popular, called Reshifter. That tool's great, but it does also require access to the etcd server, which again, we're not going to maybe give that to everybody. It is more automated than Clearly Above. And the cool thing about this tool is it has a UI. So that is actually wonderful when we go to do our labs, which are going to be coming up, which we're going to be using Valero to do our backups. You're going to see that the command line syntax can go on for a little bit. So it's great when you have a UI. The cool thing about Valero is it does not require access or a dependency on etcd. What is it actually doing is it's using the API service only. So it's making API calls to the API server, and it's retrieving back the details about what is actually stored in etcd by making the appropriate calls to the API server. So give me a listing of all your deployments. Give me a listing of all your replica sets. Give me a listing of all your pods. So he's actually querying and pulling stuff out of the API server. Valero actually runs in the cluster, and it can be done at automated intervals. So you could say, do a backup of whatever's in etcd once a day. The output is in JSON format. It's JSON based, and you can use it for other purposes besides doing a restore. So here, because it's JSON based, I could query what's inside of it, filter out certain things that I want, and I can do partial restores, for example, which is what you're going to actually end up doing in our lab exercise. I do need to point out to you a few things, though, that when you go to use Valero, the syntax is pretty long, so we're going to go over that before we do our labs. Now, if we're doing node maintenance, the first thing people are always going to ask is, well, do you have it backed up, right? Before you change anything, do you have it backed up? So we just went over our backup solutions. To review, why would you be doing node maintenance? Well, here's some of the reasons why you'd be doing maintenance to a node. Maybe I need to patch the host OS, the container host OS. That is an OS in our lab environment. That's an Ubuntu VM that I've created. Well, maybe it's got a bug or I need to patch that. For me to patch that, I've got to put the node into maintenance mode, which means I'm going to cordon and drain it, get the workload off because I'm going to be patching the operating system. Maybe I need to do an upgrade to Kubernetes, for example, right? So again, you've got Kubernetes and container engine upgrades and patching that could be going on. Maybe I just need to replace the hardware. Now, in this particular case, when we're talking about a hardware replacement, we're alluding to the fact that you could have been running bare metal on hardware, right? So now, if I'm replacing the hardware, my host, my node, my worker node is completely going to be a new worker node. So I'm going to definitely get everything off of that. So the commands that we're using to cordon would look something like this. Kubectl cordon or kubectl on cordon, and then you would put your node name over here. That would be the node that you want to cordon or on cordon. To drain it, I'm going to use a kubectl drain, and again, I would specify the node name over here that I wanted to drain, and it would go through the steps that we talked about in the previous slides before the break, where we're telling the node to terminate. You're going to give it a term sig, letting it go ahead and do the appropriate shutdown. If it reaches its timeout and it hasn't terminated, then we're going to actually kill the pod, which then in Kubernetes, we're going to see desired state and current state don't equal, so the pod actually would get rescheduled somewhere else. Some tips when you go to do maintenance, okay? It would help you to put labels on your nodes. If you're doing a DIY and you're spinning it itself, it would help to put labels on your nodes. You don't have to. Some examples would be like which rack the node's on, the OS version, subnets, and so on might help. If you're using a Tanzu solution, it's probably not going to be a super beneficial thing to put labels on your nodes, okay? What the labels do is it makes selecting easy if I want to do bulk operations, okay? Our various solutions have different mechanisms to help you do controlling of things like horizontal striping of particular nodes, targeting where you want things. You can use host groups in vSpheres, for example, in TKGI. So this is some way so that you can control what you're patching and what you're moving stuff to. And again, it just depends on how you're deploying Kubernetes, on how useful or irrelevant that particular statement is. A few things, though, that are going to apply regardless of which Kubernetes platform you're using is, there is built-in checks in progress that, built-in checks in progress inside your process. So if you're doing it manually, you would cordon it first, and then you would drain one node at a time. This is going to end up getting automated by whatever platform you're using. I'm assuming you're not going to do a DIY Kubernetes cluster. You're going to use a solution, let's say a Tanzu branded solution. He does this for you automatically. He will cordon and drain a node, wait for the node, for all the pods to be evacuated, do whatever patching we need to the node, and then bring the node back online, uncordon it, and let the workloads continue to get distributed back to the new node. So all of the Tanzu solutions do that for you automatically. And then in turn, they would move to the next after all the deployments are rescheduled. So some of that's automatic. If you're doing a DIY, you would do it yourself. And you could actually watch that going on when you're using one of the solutions, and you actually go through and do some type of maintenance to your cluster. So with that, we're going to give you a chance to go ahead and actually play with this some. We're going to allow you to do the cordon and drain functions. I don't really have anything to add to the instructions to be aware of when you do that. However, do pay attention. What we're actually doing inside here is, if you look at what we have working, we have two worker nodes, right? We have two worker nodes. We have got an O1 and we've got an O2 worker node. In this particular case, we want you to identify which node is running MySQL. Which node is running MySQL? If MySQL is running on this node, then you're going to cordon and drain this guy. Okay, so you end up cordoning and draining whichever one doesn't have MySQL. So pay attention to that step in the book, and then the lab should go pretty fine for you. My second tip for you is, when you're doing this task number 3, you're going to have to set up and install Velero and get Velero running. And when you do that and you get it up and running, let me bring my desktop over here and show you something that you need to be aware of when you're bringing it up. The command line to get Velero working is in your commands.txt. So you're going to want to use this commands.txt file. And way down here on lab 14 is your Velero. This is all one command. It's all one command. So make sure you copy it and it pastes okay from the commands.txt when you run the command from your SA master 01 SSH session. So make sure you're able to grab all of it when you put it inside there to actually get Velero. This is actually bringing up the Velero processes that we need to do. You can see it's doing the install. And then once it's up and running, you'll actually run a Velero backup command. That would be the Velero CLI to invoke the command to go against the server and actually perform the backup. So with that wraps up your lab number 14. And in this particular lesson, we've talked about the release cadence. We've talked about the upgrade process that's going to involve our cordon and our drain features inside there. And then down here, you're actually walking through the lab environment and actually giving both of those features a try. So go ahead and work on the lab, and when you're done with the lab, come back and join me for the final lesson where we're going to talk about the Tanzu portfolio and give you some details about those products and highlight some of the Kubernetes features that are being implemented inside of them. Thanks. Hi, and welcome back. Let's go ahead and get started with our next lesson, which is lesson 4 and the final lesson of this class, VMware Tanzu Portfolio. So what we've covered so far is a lot of components and features inside Kubernetes and what would be required for you to run an enterprise-grade Kubernetes platform. This lesson that we're going to go through is we're going to go over the various Tanzu products inside the portfolio that are going to help us to be able to get our new workloads, containerized workloads, how we can efficiently build them, how we can run them, and how we can manage them. So our goal of this lesson, the objectives, is describe the various products and the services that are inside the Tanzu portfolio. So this graphic is probably a very easy way to describe the various products inside the Tanzu portfolio. If we can go ahead and categorize a product in as either something that's going to help us build our new cloud-native applications or something that's going to help us run those applications that we've just built, or something that's going to help us manage our containerized workflow platform. That's an easy way to summarize the various different products inside the Tanzu portfolio. So we're going to start and we're going to go over each of the solutions in the build category, and then we're going to transition over to the various products to help us when it comes to running the containerized workloads, and then we're going to go ahead and explore the things that are going to help us manage. Now, we've already in the manage category went over when we were looking at monitoring solutions, Tanzu observability. And throughout the class, we've talked about various solutions to help us run either vSphere with Tanzu, Tanzu Kubernetes Grid, or Tanzu Kubernetes Grid Integrated. And from the build perspective, let's start there. The first one is how do we get the various products? Well, you get in your license for the products in the Tanzu portfolio by buying a particular edition. So Tanzu Basic is going to give you very simply a smaller selection of products that you could use. So Basic, for example, includes the vSphere with Tanzu offering. And then as you move your way up the various editions, you're going to get basically more products that you're entitled to use. So Tanzu Standard is going to give you both the ability to run TKG, it's going to give you the ability to run TMC. Tanzu Advanced, again, is just going to include more products. So as you go to the Tanzu.vmware.com page, you'll be able to get more details about each of these editions and which particular products are included inside of them. Let's dig into our first category, Spring. Spring is a popular framework, and it involves using a particular programming language, which is Java. If you're a .NET shop, using and licensing in the using Spring is not going to help you. It's all about Java. If you're a Java shop, then, and also you've got to kind of understand that there's different functionalities when we're talking about building cloud native applications. There's the developers group, and I don't mean to categorize them differently, but they are a different group. Their goal and what they do is different than the job of somebody that's a site reliability engineer. And if I go back for a minute to this table, one of the things I kind of want to point out to you is our role as an SRE is sitting down here on this side of that line. We're tasked with different things that we're responsible for. The developers are on a different side of the line, and it is intentional that I put through the Tanzu build service in the application catalog that area is a little bit of both of us working together. The developers are going to be looking for solutions to help them do what? They want to be able to write high-performing code that's easily testable. Now, if they're using it in .NET, Spring's not going to help them. If they're writing Java code, it would. It would help them accelerate cloud-native Java development, make microservices quick and easy for them to be able to develop, and it is using an open programming model. The goal is we want to reduce their development time, help them use the Spring platform to help them build their applications, including things like Spring Framework, Spring Boot, and other functionalities. So this is a conversation that the developers would be having about how it could help them and if it's the right decision for the company to bring in or not. The next one inside the build category is the Tanzu application service. This used to be called the PKS application server. Okay, that's what it used to be called. It's been rebranded. Now, this particular platform of the Tanzu application service is about running applications, and from below running my applications beneath it, it involves different respective runtime engines, services that allow me to run my application. So for example, I need data services to be able to persist data. I need a way to be able to run the application, so I could use Spring Boot, Steel Toe, Spring Cloud Services. And then, of course, I'm going to need a runtime system to run those applications. This is a possibility, but I'm going to say it's not necessarily purely cloud-native Kubernetes, okay? This could be a transitional service that maybe a company can use when they're from maybe an old legacy style development system. They could transition through the application service as they're trying to get over to Kubernetes. It is an option. You can talk more with the VMware team about how it would fit for your respective company. The build service. Okay, the Tanzu build service is about creating the container images. And realize that once we've built a container image, how do we keep up with that image? If it's requiring middleware, we might need additional updates over time that need to happen. This is about offering the ability for you to develop and automate containerized software workflows, and we can do it securely and at scale. It will execute reproducible builds that would keep within your corporate standards, and it would keep your corporate images updated. So I'm not running an image that was built 1.5 years ago that's including middleware that has a series of CVEs that have already been reported against it. The application catalog. This is the old Bitnami application that services that we built. Remember, when they're building a container, it's coming from something, right? How do we know that the from, or what we were including inside there, is the most current, and that if it's not the most current, how do we test the most current and make sure that the current would work if we decided to use this? So with this particular service, it is a service. It's giving the customer this curated catalog of these pre-selected by the customer which apps they need in their environment. It will constantly keep up with building, packaging, testing those particular apps that they've chosen, and then making them available for them to consume. It does integrate directly with popular CI/CD pipelines. So again, both the build service and the application catalog, that's really a cooperation between the developers and the operators inside the Kubernetes realm. Now we're moving over to the run solutions. vSphere with Tanzu, remember the vSphere's got to be version 7 in order for this solution work. It will not work with vSphere 6.7. It won't allow you any Kubernetes platforms on any other IaaS but vSphere. Now, I do like this service. This particular vSphere with Tanzu, I'm going to tell you, is the easiest way to get Kubernetes running buying a VMware product. It also kind of is a 2-for-1. Why? I get both the ability to run vSphere pods, vSphere with Tanzu, that gets that tightly integration with vSphere 7, so I'm going to see a lot of Kubernetes-related things appear inside my vSphere client, which I already know is SRE, but it also includes Tanzu Kubernetes Grid. So I get the best of both worlds. Tanzu Kubernetes Grid is something that's going to allow me to run a consistently deployed Kubernetes cluster on vSphere, including 6.7, AWS, not quite yet out yet, but GCP, it is coming, it's been announced, and then Microsoft Azure. So I would have the TKG service provisioning clusters on any one of these IaaS platforms. It would be a consistently deployed Kubernetes cluster. It would allow me to do lifecycle management of those clusters, and this solution is using Cluster API. We spoke a little bit about what Cluster API is a little bit earlier. What are you getting? You're getting a Kubernetes cluster that's been deployed via TKG. Now, as we know, Kubernetes clusters don't necessarily out of the chute give me everything I need that's enterprise grade. TKG is going to include signed and supported versions of many of the popular open source applications that will provide networking, authentication, ingress control, and logging services, and in turn, the ability to call VMware tech support if you need help in getting one of those solutions working, configured, or even afterwards for post-implementation support. TKGI. Very similar to TKG on where it can run at. However, TKGI is not using Cluster API, it's using BOSH. It's via BOSH that it is doing things like the lifecycle management, which includes the provisioning of the cluster, the updating of the cluster, the scaling of the cluster, and even the destroying of the cluster. So TKGI was the old product called PKS Enterprise. This is our primary older product that's been doing Kubernetes for us for the past 5-6 years. It's been around for a long time. It's got lots of deep integrations with VMware products, very easy to integrate with solutions like Log Insight, VROPS, even Tanzu Observability. At this time, it's the only product that allows us to run Windows worker nodes. The other products for the run, vSphere with Tanzu or TKG, at this point in time, you cannot run Windows worker nodes. TKGI is the only solution that allows that. TKGI, guys, is still going to be around. Okay, it's still being maintained and upgraded. There's no end of life on it announced. It is going to be maintained, into the future. So the difference is it's using BOSH. Now, when it comes to managing our solutions, we've got a product called Tanzu Mission Control. And the big thing about Tanzu Mission Control is it is centralized management platform. You could be running various different versions of Kubernetes. You could be running a OpenShift Kubernetes cluster. I could be running a Rancher cluster, a Mesosphere. I could be running a homemade spun Kubernetes, as well as the various Tanzu products. What's happening with this is if I have several Kubernetes clusters sitting out here, so all of these are Kubernetes clusters. All of them are Kubernetes clusters. And again, they could be all from a different, way of getting that Kubernetes running. One could be OpenShift, Rancher, etc. Normally, if I'm over here on my laptop and I want to manage these Kubernetes clusters, I'm constantly changing my context to each cluster in order to invoke some change policy, etc. Tanzu Mission Control makes that much easier to be able to do. What Tanzu Mission Control does is it forms an umbrella over all those clusters. I add all these clusters to Tanzu Mission Control. Again, it doesn't matter if it's Kubernetes and you've got admin rights, cluster admin rights to it, you can do a kubectl apply and add it to Tanzu Mission Control. Now, what does that give me the ability to do? Instead of me individually connecting to every cluster, I connect once to Tanzu Mission Control, tell it this is the policy I want in place, and Tanzu Mission Control programmatically connects to each cluster and invokes that policy. So it's about better, easier, more consistent operations and management of your Kubernetes clusters. Again, this is a cloud service offering, so it's software as a service. And if you are using the Tanzu solution, it can do things like manage that solution. It could scale it, upgrade it, provision it, etc. Other solutions from third-party vendors, we can only do limited management to them, but we can't do lifecycle scaling and upgrading, but I can certainly be pushing policies out to them. Tanzu observability. Okay, we spoke about it before in the monitoring section. This is delivering this enterprise-grade observability and analytics at a massive scale. And the idea here is with detailed controls. So you would be able to actually dig down deeper inside the code to see what's going on inside of your code. It does that by collecting data from the many services and sources across the stack. And then you could use that to create charts and dashboards with. It enables you to create alerts, query the data, and use distributed tracing to trace and investigate problem areas. Tanzu observability, I would suggest you look back at the monitoring section to see what's going on there. So that wraps up our last and our final one. I'd like to go ahead and suggest a few other things to you before we wrap up. And one of the things I'm going to suggest to you is you take a look at a solution which is open called VS Code. Okay, VS Code is going to help you to be able to edit and author your Tanzu manifest files. Okay, it's a great solution. It's free. It works on both Mac, Linux, and Windows. And once you have it configured and you put in the appropriate plugins, you can actually right from there do queries against your Kubernetes clusters, be able to do a deployment of a manifest file that you're actually working on and editing. So I would certainly take a look at that. There's tons of YouTube videos to get you started. Please don't hesitate. If you've got any questions, I would love to hear from you. You can get my email address. It's m.allenbaugh. My name's appeared on several of the intro plates that they put up. Please don't hesitate to email me at vmware.com. Thanks, and I hope you've enjoyed the course. Bye.